for questions. All right?
Okay, thank you.
Well, in fact, I think at 20 minutes, meaning 15 plus 5. So.
Sorry, I can see that he's scheduled for half an hour.
No, should not.
Let me check again, because
I can of course.
No, because my talk is the third one. So between
Oh,
10 and 10.
no, I am talking about the first speaker. Sorry.
Oh, right. No. Since you were talking to all speakers,
I was talking to the first one.
Okay.
All right.
Sorry.
So we just have 1 minute. But only 1/3 of participants. This is bad.
Yes, I think we have to wait some few minutes.
No, because then we shift everything. No coffee break.
Okay.
Barbara.
Come on, participants can stay in bed and watch it, huh?
Not with the camera switch on.
But who asks them to switch on?
We.
No.
Yes, of course. Everybody has to keep the camera on if possible.
Okay. So, all right, it's up to you how many minutes we wait. It doesn't, I mean, the number doesn't grow practically.
Okay, let's start.
Right, so time is 9. Welcome everybody to the first session of the last day of our workshop. And the first speaker is Shunzo Kumano from KK, and he will speak on polarized structure functions of spin-1 deuteron in Drelian, so of extreme interest for us. Yes, please, Shunzo, floor is yours.
Okay, thank you very much for allowing me to talk. So I discuss structure function spin-1 deuteron, and mainly based on with collaborator with Kinta Song. He was a graduate student at KK, and then he got a staff position in China. So my talk is based on this one, including today's archive paper. I'm sorry. So I briefly discuss introductions to the structure function spin-1 hadrons. Then I discuss tensor polarized pattern distribution function, and it is called B1. And then a few years ago, we calculated standard, based on the standard deuteron model, we estimated B1. So if experimentalists can find deviation from this calculation, we may have interesting physics opportunity. And for the especially for the Fermi-Drelian, by maybe saying formalism should be the same if you can prepare the polarized deuteron target in compass experiment, since proton is unpolarized. So in your case, it's pion. So the formalism should be the same. I discussed tensor polarized PDF in the proton deuteron Drelian. Then I discussed gluon transcapacity. This has not been studied at all experimentally. There are only few theoretical papers. So I introduce this topic. Then I also explain the current status of the letter of intent to measure this quantity at JERAW. Then I discuss possible Drelian measurement at Hadron accelerator facilities, including Fermi-Lab, NICA, and also possibly compass. And then in the today's archive, we submitted a paper on the TMD for the spin-1 hadron. So I comment on this topic and summarize my talk. for the last 20 or 30 years, we have been studying the origin of nucleon spin. And in the same way, we could investigate so-called tensor polarized structure function B1, which I will explain in a few minutes. If deuteron is a proton-neutron bound state, and if it's only S wave, B1 is 0. And we know that it's about, we have about 5% of D wave admixture. So in this, if we use this kind of simple deuteron model, the B1 is finite. So if we find any deviation from this theoretical prediction, it should be interesting. And in fact, we are finding a very different result from the current existing experimental data. The B1 is very different from the F1 and the G1 structure function. We have to polarize the deuteron, but the electron or muon does not have to be polarized. So this polarization is for the spin 1 deuteron, and we take this kind of tensor combination to obtain the B1 structure function. And the B1 is a twist-2 structure function, so it is expressed by the tensor polarized quark and anti-quark distribution in the leading order. Of course, in the next leading order, gluon could also contribute. And another topic I discussed today is gluon transversity. In our case, we denote delta TG, but as I explained, if you explain the next page, there are various different notations, so it's slightly confusing. But in any case, if we look at the helicity amplitude of this type for spin 1 hadron and gluon, it's the compass has been investigating the quark transversity, so you know the definition very well. It's a spin flip amplitude. For quark cases, spin flip is a unit of change of the spin unit is 1, because quark spin is 1/2. But the gluon is spin 1, so this spin flip means a unit of 2 spin. Therefore, the nucleon, spin 1/2 nucleon cannot have this kind of quantity. But on the other hand, for the spin 1 deuteron, it is possible. This amplitude is not possible for the spin 1/2 nucleon. So in this sense, it's interesting because proton and neutron are spin 1/2 particles, so they cannot contribute directly to this quantity. Therefore, if experimentalists can find any finite gluon transversity, it could be interesting physics beyond this kind of simple nucleon band system of deuteron or in general nuclei. So I believe it's interesting physics. First, I would like to discuss tensor polarized structure function spin 1 hadrons based on this result. There was already experimental measurement by the Hermes collaboration a long time ago, in fact. They used positron beam and polarized deuteron, and their experimental results are shown here. This is x times B1 as a function of x in the logarithmic scale. This is B1 itself. And the Q scale value is around a few GB square. So it's interesting they found some finite value. And a long time ago with Frank Cross, we proposed that integral or some rule of this B1 is related to this quadrupole moment, but there's a T factor, so this should vanish. So if finite, this B1 sum is found, then it would indicate this tensor polarized anti-quark distribution. That's why this is an interesting result. in fact, they found a finite sum for the B1. And this summary is very similar to the so-called Godfrey summary you know very well, as it was found by the violation was found by NMC. And the deviation from 1/3 indicate U bar minus D bar finite distribution. So this will be interesting for future investigations. And in order to find the standard model, to provide standard model prediction for the experimentalist, I calculated together with Wim Kosin, Yubin Dong, and Mark Misaksassian on assuming the very standard convolution model by using the S wave and D wave of the deuteron. So it's a standard convolution model. So we calculate the quark distribution in a nucleon convoluted with the nucleon dipole momentum distribution within the deuteron. So this is the equation. The B1 in the convolution model is given by the F1 of nucleon convoluted with the tensor polarized nucleon distribution. So we have S wave, of course, does not contribute. So we have S, this is X as a function of X, B1 as a function of X. This is a ST contribution, ST interference. This is a D wave contribution. The total looks like this one. So this curve was obtained up to 2.5 GB square, but it's average of the Hermes Q square. So the tendency is very different. So of course, experimental errors are too large, so it may be consistent, but the tendency looks like very different. So we may see that the interesting physics if JLab or COMPASS can measure this quantity. And for the experimental prospect, this is the figure supply from JLab. They have already conditionally approved the experiment to measure B1, and I was told it's will be around the middle of 2020s. These are the Hermes results I just showed, and their expected data are these. So it seems they can measure this B1 rather accurately. On the other hand, we have Hadron facilities, including COMPASS, Fermilab, and NICA. So by using this Hadron facility, it would be nice this kind of experiment can be done. But however, a few years ago, we didn't have any formalism to investigate the tensor structure at Hadron facilities. So by the request of the Fermilab people, we provided our estimate for the, this is the spin asymmetry, tensor polarized spin asymmetry in the Fermilab kinematics. But this is unpolarized proton, so the formalism is common by replacing some pattern distribution for the COMPASS people. What we did is that 10 years ago, I tried some fit to obtain a tensor polarized pattern distribution function from B1. It's not a global analysis. We have only several data. But in any case, what I obtained from this analysis is that I obtained valence tensor polarization like this one. And I also had anti-quark tensor polarization like this one. So this seems so far the optimal distribution. If I terminate this anti-quark distribution, I cannot fit this region. So I evolved this distribution to the Fermilab kinematic 30 GB square. Then the valence distribution, which this dash curve is 2.5 initial distribution, and this is the 30 GB square. And same way for the anti-quark. And even if we assume the gluon distribution vanish at this small q-scale, due to the q-scale evolution, finite gluon tensor polarization appears. Of course, it has not been measured at all. So if compass people have a good idea, you may measure it for the first time. And this is a figure I showed that this spin asymmetry, actually the tensor polarized spin asymmetry, and it is proportional to the tensor polarized quark and anti-quark distribution. And our estimate is about few percent, of course, depending on the kinematics. So it will be a very tough experiment. And there is already approved experiment, as you know, it's called SpinQuest. It's for the proton target. But they are interested in this deuteron experiment by changing the proton target for the deuteron. So there is a good possibility. And so what I see, I don't know that about situation compass, you may comment on later. So this is maybe may not be in near future, but 5 or 10 years later, EIC is 10 years later. JERA will obtain some results, as I explained, in the middle X region. And Fermilab, they are also interested in this experiment, and they can measure probably the anti-quark distribution part in this X range of 0.1 to up to 0.3 or 4. And EIC, they can measure this small X region. And also NICA people, they are interested. They have a deuteron, polarized deuteron acceleration. So they can, in principle, can investigate this topic. So it will become much better situation in the next 5 or several years. So this is just a summary of this part. So we may find new exotic mechanisms beyond the standard model of the deuteron. And Jerry Miller suggested it may be connected to the delta-delta or hidden charm. Of course, if a hidden charm is found, it's exciting, but I don't know, it's a possibility. So it's just a possibility at this stage. Next, I discuss a possible study of the gluon transversity. And this is based on this paper, but I joined this NICA collaboration to propose deuteron spin structure, and it will be submitted to this paper in 2 or 3 weeks. As I explained, gluon transversity is associated with a spin flip amplitude, so it doesn't exist for the spin 1/2 nucleon, although the quark transversity exists. You have been investigating in the compass experiment. So if a finite value is found, it's connected to a new mechanism in the deuteron. However, the situation looks, I should explain the definition theoretically. It's the linearly polarized gluon distribution. This is the linear polarization direction of the gluon in the linearly polarized deuteron. So it's a slightly complicated distribution. And the notation is even more complicated in the sense that the notation of the gluon transversity is almost the same as the number of papers, theoretical papers. Some people then say delta 2G, H1TT or something like this. This is linear polarized. It's not longitudinal polarized. But in our case, we use delta TG. And the physics, the interest point of physics is that, of course, if you are serious and if you have a good idea, you may write a paper. Because this experiment will be proposed at the Fermi level, I explained. So if this seems to be the only paper to indicate a finite gluon transparency, namely a delta can contribute to this gluon transparency. So it may be interesting. Almost no theoretical paper like this one was written for almost 30 years. So, so this is a situation. The situation would change because there was a letter of intent 2 years ago at JERAL, and they expect, if it is approved, they expect to start in the middle of 2020s. And this is their formula, but this is the almost scaling limit formula. So the situation could be much more complicated. In any case, they use a polarized deuteron target. Since the compass has a muon beam, so you can also do the same thing. You can propose the same project. And if one can measure the cross-section as a function of azimuthal angle of this deuteron spin, then this factor proportional to this cosine 2 phi is proportional to this gluon transparency. However, it is integrated over the Bioken variable. So, and the polarized deuteron target is in progress by these people. And what I was interested in is to use Hadron facility, because we have various Hadron facility, including compass, Femra, Nika. So we hoped provide opportunity to investigate this topic by the Dory-Young process. And so this is Dory-Young process of proton deuteron, but in compass cases, it could be pion polarized deuteron. The formula should be the same. And since various pattern distribution function contributes to this process, this is for the quark in the A means proton, or pion in your case. In the pion case, there is no spin. But in any case, this is for the deuteron. There are many distributions. However, if we take the linearly polarized deuteron and take some difference, this gluon transparency term can be extracted together with unpolarized one. The formula is slightly complicated, so you may follow our paper if you like. And what we obtain is,
Yeah, please continue. 3 minutes you have.
And this is the Dory-Young cross-section in the linearly polarized deuteron, x direction minus the cross-section with y direction linear polarization. Then the leading term is this quark and anti-quark distribution in the proton together with the gluon transparency. And the gluon transparency, of course, there is no distribution. So we assume it is given by the longitudinal one. But of course, this will be the overestimation, as you may imagine. But in any case, we showed some cross-section depending on the QT of the dimu transverse momentum. And we also showed this spin asymmetry, and it looks like less than a few percent. So in any case, it's a very tough experiment. But this Fermi experimentalist spokesperson of Sequest, Dustin Keller, informed they will propose the experiment in this December. So it's very nice. So I comment on this linear polarization. Yeah, in the compass experiment, I believe you have this transverse or longitudinal polarized target. So even if we have transverse polarization X or Y, we have contain some tensor polarization and also linear polarization component. So in order to extract this linear polarized part, we have to extract the linear X and linear Y polarization difference, take the difference to remove these things. But in any case, by looking at this kind of polarization, we can extract the ground transversity. And as a Hadron facility, FEMRA, JINR, they are certainly interested in proposing this experiment. And Dustin Keller is preparing this proposal for the FEMRA Park in December. So hopefully this will be realized at least at FEMRA. And the NICAP experimentalists are also interested in, and they are writing this report for this deuteron experiment. And so I also joined this project. So it will be interesting also if you can. This is summary, and since I don't have time, I just comment on TMD for spin-1 hadrons. TMD, this you don't need any introduction, so I'll skip. And this one also, you know, so it's of course, TMD is a very good process to prove the color flow direction because of this link. And the interesting point of this physics is that, as we discussed at KK workshop, Paquette and our KK member,
well,
of course, it's
over.
Yeah, I know, it's 25. And we know around Bohm effect in QED. If we turn on or turn off this magnetic field, this interference pattern change. And of course, it's very similar to the Sievert's effect we have been investigating. So it's an interesting effect. And another interesting point is that it's connected with the color flow. So of course, this kind of factorization breaking is very difficult, but if we have an interesting theoretical proposal and experiment, this color entanglement would be also interesting. And TMD for spin hadron was investigated by these people, and it's already listed. Finish it 1 minute. Okay, and
I think you have to stop here. I'm sorry.
Yeah. Okay. What we found is this twist 3 and twist 4 TMDs. So you may look at that paper. Okay, I stop here. You may read the summary.
Thank you so much. It was, the last item was very interesting, but unfortunately we didn't have time. But I can see Daniel Bauer raising hand. Please, Daniel.
Yeah, hello. I have a question about this, the Drell-Yan. You calculate basically 2-to-2 scattering, and and you apply it to very small transverse momentum.
Yeah.
Is that actually allowed? So maybe you can go back to the slide with the process, this one. Yeah. So you do 2-to-2 process, and of course Q squared is large, but you take QT.
QT isn't so large, yes.
Yeah, 0.2 GeV. Is that allowed?
Yeah, in the FEMRA experiment, their QT is rather small in this range, as I calculated. So
But I mean, is it theoretically allowed to apply this this calculation to that low QT? Don't you need some recoil for the 2-to-2 process to be applicable?
That's I have not looked at it. You may have better idea.
Okay, thank you, Daniel. Gunnar, please.
Yeah, hello. You talked extensively about the B1 inclusive structure function.
Yeah.
Is there anything one may learn about the CDIS B1 asymmetry, so for semi-inclusive DIS, the tensor asymmetry?
Yeah, semi-inclusive DIS. I personally have not looked at the semi-inclusive DIS, but Christian Weiss might have looked at it in connection with B1. I do not remember very well. Well, of course, semi-inclusive DIS, it is possible to extract B1.
Ask Christian.
All right, no more questions? No, thanks to Shunza and those who asked questions. Thank you. And the next one now will be part on distribution functions from Lattice. Savvas Zafiropoulos from CPT Marseille. Please, Savvas, you have 25 minutes and you will be warned 3 minutes ahead of it.
Okay, hello everybody. Thanks for the introduction. I hope that you can see my screen and that I'm heard properly.
Yeah.
Okay, so today it is a great pleasure to be here to talk to you about the extraction of light cone pattern distribution functions from lattice QCD methods. I would like to start by thanking the organizers for organizing this very nice symposium. Of course, we would all like to be in Trieste and do this in person, but okay, I guess this is better than nothing. This is work done within the Hadron collaboration, members of which are listed in the first page. So PDFs, we all know that are of paramount importance because the uncertainties of pattern distribution functions are the dominant theoretical uncertainties in Higgs couplings, alpha strong, and the mass of the W boson. Of course, beyond the Large Hadron Collider, PDFs play an important role, for instance, in astroparticle physics, such as for the accurate predictions for signal background events at ultra-high energy neutrino telescopes. And PDFs will always keep playing an important role for any future high-energy collider involving hadrons in the initial state. Therefore, improving on our understanding of PDFs also strengthens the physics potential of such future colliders, such as the electron-ion collider in the US and the Future Circular Collider at CERN. So the very measurement...
Savvas, because people do not seem to see any slides. I also see just you in front of the blackboard. Should it be? Are you sharing?
Share screen.
In the bottom margin, you have share screen. All right, now it comes.
Oh, okay, I'm really sorry for that.
Thank you.
So this was the first slide with the members of the collaboration. This is the introduction. Okay, so the measurement of PDFs is actually made possible due to factorization theorems. And intuitively, these factorization theorems tell us that the same universal non-perturbative objects, the PDFs, which are representing long-distance physics, can be combined with many short-distance calculations in QCD to give the cross-sections of various processes. So in terms of an equation, we have sigma, the cross-section is F O times H, where F are the PDFs, capital H is the hard perturbative part, and O times denotes a convolution. PDFs truly characterize the hadronic target, and they are essentially non-perturbative. When we think of non-perturbative calculations within the context of QCD, the natural thing that comes to mind is QCD discretized in a space-time lattice and simulated numerically in a supercomputer like this one. However, PDFs are defined as an expectation value of a bilocal operator evaluated along a light-like line. And clearly, we cannot evaluate this on a Euclidean setup where all the lattice simulations are taking place because the light cone in a Euclidean space collapses to a light point. So what has the lattice community have been doing traditionally up to now? The lattice community has been employing the operator product expansion in order to associate many moments of the PDF, such as average x to the power k, to matrix elements with local operators, such as this one, where we have the insertion of a gamma matrix and a string of k covariant derivatives, and this is associated after subtraction of traces and symmetrization to average x to the power k. In general, computing the moments of the PDFs is not a problem at all in principle, and this would not be an issue if every moment were accessible to a lattice computation, because we know that the probability distribution is completely determined once all its moments are known. However, these lattice studies are limited to the first few moments, let's say 3 in order to be generous, due to the following 2 issues: bad signal to noise ratio and power divergent mixing on the lattice. So with these traditional techniques, the lattice is not able to go beyond, let's say, the second or the third moment. Here we see a compilation of results for the average X from different lattice collaborations with a traditional method. And of course, one needs to say that in the meantime, when the lattice is trying to develop new methods to access the PDFs, there's a huge ongoing effort from the phenomenological community, where the determination of PDFs is performed by fitting experimental data from several scattering cross-sections, and one combines the most PDF-sensitive data and the highest precision QCD and electroweak calculations, always under the working assumption that the standard model holds, and by employing a statistically robust fitting methodology, one can fit and extract the PDFs. Actually, this way, one can achieve quite high precision for the cases, though, that the data are abundant. And this is the case of the nucleon and in the case of unpolarized PDFs. Of course, there are cases where the data are not abundant, the experimental data, and the method of global fits has issues. And therefore, that's a reason why we would like to have an ab initio determination of the PDFs. This is a compilation of results of global fits from different collaborations. You see that they are in agreement with each other, grosso modo. There are still some tensions, but there's a common feature which has to do with the explosion of the error budget in the large X regime. And I will try to convince you in what comes next that the large X regime is precisely the regime that would be the first to be easily accessible on the lattice, then the intermediate X, and of course, last, the small X regime. Okay, some comments about the large X discrepancies, both for the nucleon and the pion. In the first plot, we have a compilation of results for the D with respect to the U quark PDF from the JLab 12GV measurements. And these are, in the yellow, we have the projected uncertainties. And over here, we have different expectations based on different models for QCD, models with or without SU6 symmetry, models based on Dyson-Schwinger equations or perturbative QCD. And the situation is kind of similar for the pion, which has been extracted in this experiment at Fermilab. Of course, it's one of the goals of COMPASS and of this experiment at JLab. And by looking at this exponent, you can have an idea of what different models predict about the PDF around x equals to 1. Therefore, for all these reasons, it is clear that an ab initio non-perturbative QCD calculation is actually timely and very imperative. Okay, so what do we do when we try to compute the full X dependence of PDFs on the lattice with these new methods? So the starting point is the equal time hadronic matrix element with the quark and anti-quark field separated by a finite distance z. So this matrix element was written in this paper by Moose and et al. In 2010. It was not noticed as much. Of course, this whole field exploded after the seminal paper of Shandong-Zhi in 2013 with the introduction of the quasi-PDFs and Lamet. And later on, of course, with this paper by Radiushkin, who is our collaborator, and we are following his formalism, which goes under the name of pseudo-PDFs. So this is the matrix element that, that everyone is studying on the lattice. We can use Lorentz invariance in order to decompose this matrix element into two matrix elements, M sub P and M sub Z. The first matrix element is mainly related to leading twist, but it has also some contaminations due to higher twist effects. The second part is entirely related to higher twist effects, and we want to get rid of it, and we can do it so by a smart choice of kinematics. This matrix element depends on two Lorentz invariant quantities, minus z dot p and z squared. And this Lorentz invariant quantity nu, which is given by minus z dot p, is going to play a crucial role in what comes next. And it's called the Ioffe time. And you can physically understand it as the Fourier dual of the Bjorken X variable. So when I was saying before that the lattice can be of help in the large X regime, it's because large X means small nu, and small nu means, let's say, moderate momenta, and therefore the lattice can achieve quite good signal. So what we are studying are these Ioffe time distributions, which are the Fourier transforms of the regular Bjorken X PDFs. Okay, so how can one obtain in practice this Ioffe time distribution? One can try to brute force this singular limit, z going to 0 of this matrix element. However, large order z-square corrections are prohibiting such an extraction. However, one can profit and form a ratio, because in a ratio, z-square corrections, which are related to higher twist effects, tend to cancel. And apart from that, the ratio gives us an extra huge advantage. This matrix element has been shown to renormalize multiplicatively. So when we form a ratio, we end up having a finite quantity because all the renormalization constants have exactly cancelled. And when we compute this quantity on the lattice, this is actually renormalization group invariant quantity. And finite, we can extrapolate to the continuum limit, take the cutoff to infinity at fixed Ioffe time and z-squared. So let me take a historical approach, and I would like to walk you through our different works so you can have an idea of how this field evolved. So in this first paper back in 2017, it was just a case study. We wanted to see if the idea of radiation made any sense at all, and if we could get a PDF out of a numerical simulation on a Euclidean lattice. So in the first paper, we started from a very unphysical setup. And of course, in the end of the talk, I will go to a very physical setup. But let us follow this historical path. So in the first paper, we worked in the quenched approximation on the lattice. Due to some technicalities, this is forcing us to work with heavy pions. Of course, then we got convinced, and I will try to convince you that this approach makes sense. Then we started using lattice ensembles with 2+1 dynamical flavors of Wilson, Clover-Wilson quarks. In a lattice calculation, you have different limits that need to be taken. You need to take the lattice spacing A to 0, so you need to have different values of the lattice spacing. You need to take the pion mass to the physical pion mass, the volume of the box size to infinity, so you need different volumes for a different value of the lattice spacing, and so on and so forth. And we have been doing this throughout several publications. But let us have a look at the first results of the first paper. These are results for the real and the imaginary parts of the reduced Ioffe time distribution, and I have plotted for eye guidance the cosine and sine Fourier transforms of these ansatz. And as you can see here, the real part is well described by these ansatz. The imaginary part is also well described. Well, not quite, because if we see here on the hump, there is some sort of a discrepancy. There is some sort of a gap between the data and this ansatz. And in order to understand the origin of this discrepancy, one can consider CP even and odd combinations. An even combination is precisely this Q valence. However, we see that the odd combination has an extra contribution from antiquarks. So by hypothesizing a non-zero antiquark contribution, we can nicely fill in this gap. And here we have a nice description both of the real and the imaginary part. But for those of you who are quite picky, you can see here where I have plotted the data as a function of the Ioffe time, that there is some sort of a residual z-dependence in the data. And this is more visible when for a particular value of nu, we have several data points corresponding to different values of z. But different values of z-squared for the same value of the Ioffe time nu correspond to the Ioffe time distribution at different scales. So a natural question to ask is if this residual scattering data points is consistent with DGLAB evolution. We solve the evolution equation in the leading order. It relates the off-time distribution at the scale Z prime to the off-time distribution at the scale Z. It's only applicable at small values of Z, of course. And this is the situation before and after evolution. We see that there is a drastic reduction on the scatter of the data, and evolution can indeed collapse the data into a universal curve. This is for the real part. Same is true for the imaginary part. And then what we did in the first paper, we took the evolved data points for the real part. We fitted those data points with a cosine Fourier transform of these ansatz. We picked up some exponents. At that time, we didn't know how to match to MS bar, and we didn't know how to set the scale. Now we know all these things, of course. And by bringing all the points to a common reference scale, and by knowing the value of the lattice spacing, we said, okay, that was the PDF at the scale of 1 GV. We evolved our PDF up to the scale of 2 GV. This is the blue curve. And despite the crudeness and the numerous amount of approximations involved, actually we obtained a quite decent looking PDF compared to the very high precision extraction from global feeds. The next sanity check that we wanted to perform in the next paper was actually to go ahead and extract moments from our data. And we proposed this method. One looks at the derivative of the off-time distribution with respect to the off-time at 0 off-time. The advantage of this method is that because of the fact that this ratio, the reduced off-time distribution, is an RGI, normalization group invariant quantity, it knows nothing about the lattice regulator and all the pathologies with the mixing that the lattice brings into the game. So in principle, if one can resolve properly this derivative, one could go beyond the second and third moment that the lattice could go traditionally using the local operator. So in this paper, we compute, for example, average x and x squared, and we compared with the literature for results with similar values of the parameters. Okay, so that was the next sanity check. And before showing you new results with dynamical fermions, I would like to talk about one of the most pressing systematics that one is facing in all these kind of extractions of the lattice, and that everyone needs to have in mind. So as I said, every lattice computation has many systematics. We need to take the continuum limit, the infinite volume limit, but the community has developed a lot of experience on how to take those limits and how to address those systematics. You need a lot of computational resources and a lot of manpower, but you know, it's doable. However, there's one type of systematics that made us think a lot about it. And this is the key point of this paper. So what we compute on the lattice is this E of a time distribution, and we have only a handful of lattice data for this quantity. And we want to solve for this QV. As if this was not enough, the cosine here is integrated from 0 to 1, and it's not an orthogonal basis function in this interval. So taking these two issues together at face value, render the extraction of the QV, solving this inverse mathematical problem, very ill-defined. In the next slides, I will try to convince you how ill-defined is this problem. So the first thing that one would try after any kind of class on numerical methods would be to, let's say, first discretize the Fourier transform by employing, for example, the trapezoid rule. This is how the Fourier transform looks like. One can cast the problem in linear algebra language, so M equals C dot Q. And the conditioning of the problem is easily elucidated by considering the eigenvalues of this kernel matrix C. And here's the plot of the eigenvalues of this matrix. And I start by these orange data points, which is what I call the absolute science fiction scenario. So if magically we had data extending from 0 to 40 pi, then all the eigenvalues of this kernel matrix would be of order 1, and there would be no issues with the inverse problem at all. The same thing would be true if we magically had data in of a time extending from 0 to 100. But this we're not going to happen even in 10 years from now. What we have right now is data from, let's say, almost 0 to 10. And you see that there is an exponential degradation of the spectrum. We have almost 0 eigenvalues if you look at this axis. This matrix C is extremely singular, and we cannot invert it. And in order to keep arguing why this naive reconstruction is a no-go, let us try to go ahead and perform it. So here we play with mock data. We have the original data, and we are in this science fiction scenario, 0 to 40 pi for the offer time. And you see that even with big error bars, 10 to the negative 2, 10 to the negative 3, I can do a nice reconstruction. If I go to intervals for the offer time 0 to 100, for example, I have to make the error bars already smaller, and you see that the reconstruction has some issues already. And if I go to something that we hope to have in the next 3 years, intervals for the offer time from 0 to 20, you see that I have to make the relative errors even smaller, 10 to the negative 5, 10 to the negative 6. And even if we had ideal data in this interval with 0 or machine epsilon precision error bars, you see that there are some lingering oscillations in the red dots, which is a manifestation, a resurfacing of the ill-defined inverse problem. So what we did in this paper is we tested pretty much all the methods that exist in the market for the advanced reconstructions. So Bayesian methods, maximum entropy, the Backus-Gilbert algorithm, a hybrid Monte Carlo evaluation of the chi-squared functional, and neural networks in order to be able to reconstruct the Bjork and X PDF out of a handful of lattice data. And we showed in this paper with mock data that this can actually be done. So I would like to flash some results from newer papers with dynamical fermions. So in the next, in a series of papers, we had results, for example, in a coarse lattice with a heavy pion mass of 415 MeV. This is the offer time distribution. This is the PDF. This is the same values of the parameters, bigger volume. The situation is similar. A little bit finer lattice spacing, 0.09 Fermi. These are always about the nucleon PDF. These are results for the moments, for the first moment, the second moment. In the next paper, which is now accepted by PRL, we had the results down to pion mass 172 MeV, which allowed us with 3 different values of the pion mass to extrapolate to the physical pion mass. This is the real part of the offer time distribution, the imaginary part of the offer time distribution. And this is our work. And this is the results of the global fits. This is comparison with the work from the ETMC collaboration. 2018, they had results using quasi-PDFs, 2020 with the pseudo-PDFs. These are the moments. And we have also results for the pion. This is the offer time distribution. This is the PDF. These are results on a coarse lattice with heavy pions. So, of course, these are not very competitive results yet, but we are working on it. This is X times QV for the pion and QV, and compared to JAM and other phenomenological determinations. Different 4 moments for the pion. And then I would like to talk about lattice QCD and how important is a collaboration with phenomenology and global fits. So how lattice could be of use for global fits? Similar to any usual global fit analysis, one needs 3 basic ingredients: a factorization theorem, perturbative input coefficients, and Diglab evolution, and experimental data can be substituted or enhanced by lattice data. So this was the goal of this, one of the goals of these white papers, and it shows the impact in the precision of global fits. Here is a game played only with mock data. On the left-hand side, we have the percentage PDF uncertainty of the S plus quark PDF. This black line shows what happens if lattice and phenomenology don't talk to each other. The uncertainty stays constant. However, if there is a collaboration between the 2 communities, the lattice here, for example, in this left-hand side plot, can provide information about the moments with 3 different scenarios on the error budget, and this can drive significantly the error budget of the global fits down. On the right-hand side, we have a similar game played, but instead of providing information about the moments, we have information about the large X behavior of the PDF from the lattice, and this can also help the global fits. Of course, this is work done with mock data. We are not still in that level of precision to be able to be that much of help for global fits. We hope to be so in the next couple of years. And this is work.
You have 3 minutes.
Yes, I'm wrapping up. This is work done in this slide with some members of the NNPDF collaboration. So we reanalyzed our data with the NNPDF machinery, and this is the result for the PDF. Of course, performing an extraction of the unpolarized nucleon PDF and being competitive is very, very difficult for the lattice, because this is precisely the domain where the global fits can achieve very high precision. But there are other cases, such as the polarized PDFs, GPDs, the gluon PDF, or pion PDFs, where there's not such an abundance of data, and the lattice would be very competitive very quickly. Of course, now we have come to the era also on the lattice for the quest for precision. In order to have precision, we are applying now to our data a new method, which was introduced in spectroscopy back many years ago by Mike Peardon and collaborators. It's called distillation, probably because Mike Peardon is in Ireland, in Dublin. And these are some preliminary results with this new smearing method of distillation. So now our data points for the off-time distribution and of course for the resulting PDF are very precise. These are results for a relatively heavy pion mass of 350 MeV. We hope that by Easter to have results also at the physical point with this very precise and expensive, of course, method of the distillation. This brings me to my conclusions. PDFs are needed as theoretical inputs to all hadron scattering experiments, and in some cases they are the largest theory uncertainty. The lattice community is by now able to provide ab initio determinations of PDFs without theoretical obstructions. The interplay between lattice QCD and global fits is extremely important. I explained why. PDFs are important also in the search of new physics. And what comes next in our agenda: polarized, transversity, gluon PDFs and GPDs eventually. And many, many thanks for your attention.
Thank you so much, Savas, for the good talk and fantastic timing. I can see that Valerio Vertone has risen hand. Please ask your question.
Yeah, I guess that Gunnar was before me, but I can start if
I think Gunnar's hand is from the previous talk.
Okay, fine. Yeah, so actually I had a couple of questions. One is the particular x function that you use in slide 9, if I'm not wrong, you said to guide the eye. So is there any, if I'm not wrong, it's something that starts with the square root of x.
Yeah.
Next.
Yeah, why it's not okay? No, it's here.
This one. Yeah. I was wondering what's if there is any particular reason for using that particular functional form.
No.
Okay.
No, it was like, functional form that seemed like logical, and it could describe this data. Of course, this data is from this very first paper. That I showed that we were working in a physical setup, quenched approximation. That means that the gauge fields were generated with no dynamical fermions, pion mass of 600 MeV. This was just the first, let's say, cheap numerical calculation in order to have some results to test if this idea of radiation made sense at all. Now, and of course, the small x behavior of the resulting PDF was completely garbage. It was not even diverging, and you should take it with a grain of salt. You shouldn't hold your breath on that. Now, with the better methods and with the more precise determinations, we can move having something like in the last preliminary results, like a divergent PDF in the small x regime, if you can see over here by the red curve. But
Right. And okay, yes, got it. And then I have another question, if I may, which concerns the evolution. So at some point, if I'm not wrong, you said that the evolution helps, I'd say, smooth the data.
Exactly. I mean, because the unevolved data correspond to different values of z-squared, and z-squared in this formalism, 1 over z-squared is the scale. So we wanted to bring like the data into a common scale, because in the end we want to give the the PDF at, let's say, ms bar 2 GeV. So
right. Yeah, my question was, is that I mean, because after all, if I understood correctly, the evolution being an integral differential equation essentially spreads out all the fluctuations over the full range. And so I suppose that using the evolution is not getting rid of the fluctuations, but it's just spreading them all over the place.
No, actually, I would say that's doing the opposite of the spreading. It was bringing them on a universal curve. Before the evolution, hold on. Before the evolution, there was some sort of a scatter, but somehow in the after the evolution, they come to fall onto, once you bring them to the same scale, they fall onto a universal curve.
Yeah, that's what I meant, because the evolution essentially is spreading any fluctuation over the full range, and then you don't see them. But that doesn't really mean that you are totally getting rid of them. It's just that you have averaged them out, but they are still there. So I mean that was just, yeah, okay.
But I think that it's also important the fact that we can see some sort of evolution in the data with respect to Z. Right, that's an important like sanity check that we were able to see such a thing at this level of precision.
So, but then the evolution is done on the lattice, so it's not a perturbative evolution.
No, it's perturbative. Unfortunately, still we use perturbative evolution. Of course, ideally it would be great to have like non-perturbative evolution, but we don't have like the formalism to go beyond this just, simple leading order equation. But what you're saying, ideally the best thing is what you say, to do it on the lattice non-perturbatively. But I guess this is for the future.
Okay, thanks.
All right, I don't see any more raised hands. Maybe still somebody wants to comment? If not, thanks, Savas, again. That was difficult, but I think clear as much as possible.
Okay, you're very welcome.
Thank you. And now we shall have Valerio Bertone on collinear fragmentation functions from CDs. We see your slides, but you should go to the full screen, I guess.
Yeah, now you should see me. Right.
Go to the full screen.
Yes, we do. Okay, let me do this.
Perfect.
Yes.
And you have something like 17 minutes, 3 minutes ahead of this. I'll let you know.
Okay, great. So just give me a second because I want to get rid of this thing here. Okay, thank you. So yeah, today I will be talking about the extraction of collinear fragmentation functions from series data. And this is a work that I've started well, around 1 year ago with in collaboration originally with Manuel Nocera, and then Raba also joined us to refine this work, because actually the idea evolved a lot. And I just wanted to give you an extended version of the title, because this something that, I mean, this title is actually a bit not very precise, because what I will be presenting is actually preliminary results on the extraction of collinear unpolarized light hadron fragmentation functions. And in this particular talk, I will be showing only the result concerning the pion fragmentation functions, even though we are also working on kaons and protons. And these fragmentation functions are extracted exploiting CDS data. And in this particular presentation, I will be talking about the CDS data from COMPAS, even though we are considering, even though I won't show any result on that, also Hermes data. Let me start with the most recent determinations of fragmentation functions of light hadrons that are present on the market nowadays. Maybe the most famous and complete is the one by that, well, everybody calls DSS, but actually also includes other authors. So that's why in this particular table I called DEHSS. And this table shows the main features of these feeds. So on top of DSS, there is also an FF 1.0 that came 3 years later, and then the most recent one by the GEM collaboration that came 1 year ago. As far as the parameterization is concerned, the DSS and GEM use a standard parameterization. It's kind of polynomial parameterization, while NNFF uses the neural networks. As far as the error propagation is concerned, DSS uses the standard Hessian approach, while NNFF and GEM use Monte Carlo approach. The data set is what probably makes most of the difference, because DSS is to some extent the most inclusive one, because it includes single inclusive annihilation, semi-inclusive DIS data, and also proton and anti-proton collider data. NNFF 1.0 originally only implemented single inclusive annihilation data, but then we have also worked on including proton data from Tevatron, LAC, and others to determine the charge hadron fragmentation functions. And then the latest one, the GEM, not only includes data that is sensitive to fragmentation functions such as single inclusive annihilation and CDs, but they also fitted on top of fragmentation functions also PDFs. That was a real global fit of fragmentation functions and PDFs. That's why in the table I also indicated DIS and Reliant data, because they also fitted PDFs. As far as the hadronic species, DSS fitted pions, kaons, protons, and also charged hadrons. And that's what also NNFF did, while GEM only considered pions and kaons. The perturbative order is up to next to leading order for DSS and GEM. And for NNFF, it went up to next to leading order, and that was just due to the fact that in the first fit, we only consider single inclusive annihilation data for which next to leading order corrections are known. These are only the most recent light hadron fragmentation functions. There are on the market, of course, also heavier hadronic species available, like this star, lambda, and others. There is also another recent determination from HKKS on the market, but this set so far is not publicly available, so I couldn't really use it for any comparison with our results. And then something that I find extremely important and interesting is that the most recent fragmentation function determinations have been released in the LHA PDF format, which makes it much more easily accessible to people who want to use them either for comparisons or for actual calculations. Before going to the results, let me just give you a very brief introduction concerning the framework in which the analysis that I'm going to present has been carried out. And there is a brand new collaboration that has just born, and this is what we call the MAP collaboration, where MAP stands for multidimensional analysis of partonic distributions. So this collaboration is actually a very, I'd say, loose collaboration, in that it's just a self-aggregated group of people who are interested in the hadronic structure. So we mostly work on collinear and TMD distributions, as well as on GPD distributions. So we just share this interest, and so we have tried to put our energy together and our effort together to get something more efficiently. At the moment, it comprises people from Amsterdam, like Raba, and Edinburgh, like Emanuele. I am in Paris with other collaborators. And the bulk of the group is actually Pavia, where I'm actually where until not so long ago. And what I'm going to present is the first ongoing effort of this collaboration. So this determination of unpolarized collinear fragmentation functions. This just to say that this particular determination, of course, exploits the expertise that some of us have in this particular framework. But this is a completely different context, and it's different in that we are all users and developers of publicly available tools. So everything that I'm going to show can be essentially repeated by any of you just by using the set of public tools that you can really find on the web. And here I've listed the most important one. And so, well, I will be mentioning some of them during the talk just to tell you what we have used them for. So let me start with the result themselves. And first of all, I wanted to discuss the parameterization of the new fragmentation function set that we are working on. And in this particular case, all fitted fragmentation functions are parameterized in terms of a single neural network. So we just really use one single neural network that has as an input, of course, the Bjorken variable x, and as an output, all the fragmentation functions at once. Since this work is still ongoing, we have not decided yet the precise architecture that we want to use. But as an indication, we will be using one single layer neural network with around 200 free parameters. This is pretty much how it looks like. And for the first time, we have exploited the fact that if you use a feed-forward neural network, you can compute analytically the derivatives with respect to the free parameters. And this is what we have done, Raba and I have done in this paper here. And we have then released this result in the form of a public library that is called NNAT. This, of course, as you can imagine, enormously simplifies the task of any minimizer that needs to minimize the chi-square, because now we can really compute the gradient of the chi-square with respect to the free parameters in an analytical fashion, which of course makes it much simpler and much faster to be computed. This, of course, has to be opposed to the numerical and also the well, here not analytical, but the automatic one of the derivation. So here, just to give you a feeling, a flavor of why the analytic derivation is better. In this particular plot, I'm showing the performance of fitting a single hidden layer neural network to a simple oscillating function. On the y-axis, you see the time in seconds per 1K iterations, and on the bottom, the upper axis, you see the number of middle neurons, and on the lower axis, you see the number of parameters corresponding to that number of neurons. And there are three different curves. The green one corresponds to a numerical derivative, why you fit the neural network to this simple oscillating function. And by numeric, I really mean taking the incremental ratio and then just take it you compute the derivative really numerically as a difference between the neural network computed in points that are close to each other. And so the green curve shows you how the time taken for the fit increases with time. The red curve corresponds to automatic derivation. This is something that is implemented in computer algebra, if you like, and it is just an analytic way to compute derivatives. But this essentially exploits the chain rule in that any single operation in a computer is done in terms of atomic functions, and the computer itself knows what are the derivatives of this function, so it can apply the chain rule to compute the derivative of any analytic function. And this is what the red curve shows. And finally, we have applied our analytic expression for the neural network, and this shows this shown by the blue curve. And as you see, I mean, if you go from green to blue, the gain in performance is really large. And so now we are really exploiting this ability to compute analytically the derivatives of neural networks. Now let me go to the prediction engine. We are talking about collinear fragmentation functions. So we are in the framework of collinear factorization. And in this framework, we have considered, well, the cross-sections for single inclusive annihilation process and semi-inclusive DIS. And these formulas here show you how these cross-sections factorize in collinear factorization. So you have in blue the partonic cross-section, and in red I highlighted the fragmentation function. So single inclusive annihilation, of course, only depends on fragmentation functions, but semi-inclusive DIS also depends on PDFs, so F. Then, of course, on top of that, you also need to compute the evolution of fragmentation functions, and this, as usual, happens through the DGLAP evolution. And also in this case, the kernels of the evolution are perturbative objects. And in all this framework, all perturbative contributions, that means partonic cross-sections and splitting functions, are provided by Apfel++. And on top of that, Apfel++ also takes care of numerical convolution, so the convolution that you need to compute cross-sections by say, integrating hard cross-sections and fragmentation functions, but also of solving the DGLAP evolution, and it also takes care of numerically integrating the cross-sections over the final space, the final state phase space. So this is something that I would like to stress. In this particular work, we have implemented the full integration over the final state phase space. So this is particularly relevant for series data that are actually delivered in terms of bins over, for instance, in Compass case over the Y, X, and Q. Now, as far as the computation of the chi-square is concerned, something that I would like to stress, and I think it's very important, is that in this particular work, we have exploited all possible sources of uncertainty. So usually experimental collaborations release experimental uncertainties that are either correlated and uncorrelated. And amongst the correlated ones, usually one can also distinguish between additive and multiplicative uncertainties, and of course they need to be treated differently. So in this particular work, we have tried to do our best to exploit all this information to come up with a chi-square that reflects all possible sources of uncertainties. So this is how the chi-square is computed. So in terms of residuals, where M and T are just the central value of the experimental points, and T are the theoretical predictions, and V is the covariance matrix, which is constructed in terms of uncorrelated uncertainty, sigma unk, and also, well, in this case, relative correlated uncertainty. So, and they are all summed over all possible sources of uncertainty.
Valerio, please, 3 minutes.
Oh yeah, yes, then I have to be super fast. So then the data handling is done by Nanga Parbat. So Nanga Parbat really takes care of computing the chi-square in the most efficient way possible. Then let me very briefly discuss the minimizer. So we are dealing with a large number of parameters because we are minimizing a neural network. So mean width is not really an option. So here you see an except from the mean width manual that tells you that you can use mean width at your own risk if you go beyond 15 free parameters. Of course, we are much beyond that limit, so we have chosen a minimizer that is on the market. It's called Ceres Solver, and it's a very solid minimizer that has been used since 2010 by Google for very complicated tasks, because this is very well suited for complicated optimization problems. And importantly, it also allows to implement not only automatic derivation, but also analytic derivation. So now let me go to the data set. So this is the single inclusive annihilation data set that we have included in our fit. So there are essentially the most famous and important data sets. So more noticeably the B factory data from Bell and Babar, and also the lab data at the Z mass. So this is a scatter plot of this data. But importantly, we have also included the cities data from COMPASS, and this is just a scatter plot of the pi plus data included in our fit. Of course, we have also included data for pi minus, and then after cut on Q, so we required Q to be larger than 2 GeV preliminarily to be in the perturbative region. We have around 300 data points left of cities data. So now let me go briefly to the results. So this is just a comparison between data and theory. And here you see 4 different experiments. So Babar in the top left, Bell in the top right, TPC in bottom left, and SLD in the bottom right. And well, here you see that, of course, the agreement between data and theory is very good. This data has been fitted, and the gray areas indicate the data that are not included in the fit because they have been cut away because of kinematic cuts. Something that I also wanted to show is the agreement between studies data from COMPASS and theory predictions. And also in this case, the agreement is pretty good, as you can see from this plot. So here I just picked 4 different beans. So 4 different beans in X and Y as functions of Z. And so you see here also the agreement is pretty good. And finally, I just wanted to show results on fragmentation functions. I don't have much time to comment on that, but in these 4 plots I show...
Your time is over.
Yes, so 2 more minutes and I'm over. The gluon, the sum of the light quarks, charm and bottom. And here the comparison is between our preliminary determination and DSS and GEM. So you see that there are quite some sizable differences all across the board. So some of them have to be understood. But something that I also want to stress is the size of the uncertainty, which is in many cases also quite different. And we tend to believe that ours is quite solid in that respect. So now just steps left to completion. As I mentioned in the beginning, we are also going to include the Hermes data. We will extend our analysis also to kaons and protons. For now, in this presentation, I've only shown pi and fragmentation functions. We need to optimize the kinematic cuts. So we have kinematic cuts, of course, to make sure that our theory predictions work, but we have to optimize them. We also need to optimize the hyperparameters, so the neural network architecture, training validation functions, and so on and so forth. Importantly, we are also going to consider kaon and proton multiplicity ratios from COMPASS. So there are some analyses that have measured this particular quantity, and these, of course, are ratios, so are very solid in terms of and then we just have to run the final fits and write the paper and release the DLHA PDF grids. So this brings me to the conclusion. I'm not going through them, and so thanks for your attention.
Thank you very much. I have 2 raised hands. Please, I think first was Bernard Mulilo. So please make your question very concise and the same with the answer.
Thank you. Valeria, thank you for your nice contribution. I just wanted to ask a question on the chi-square. I understand how difficult it is to classify them as correlated and uncorrelated. But when the systematic uncertainties are very large, I expect the chi-squares to be very small. So what was the value of the chi-squares that you obtained? How small, large?
Right, I didn't show the chi-squares because this is a preliminary analysis, so I didn't want to, I would say, give you the chi-squares are generally pretty good. So, and they range between much less than 1 in some cases and up to 2, more or less. And yes,
I suggest we pass to the second question because the point was made.
Okay.
Sorry about this. So Alexei, please.
Yeah, thank you. So thank you, Valeria, for a nice talk. So my question is, which PDF do you use for CDs?
Oh, right. This is also something to be decided, but in this particular fit, we have used MMHD 14.
Okay, and how much PDF is correlated to fermentation function?
So this is something that we have studied some time ago. There is some degree of correlation, but it's not very large.
All
Not
right.
very large.
Okay, thank you. So Gunnar, please.
Yes. Quick questions. You use the Bell data, the original data, which is very finely binned. There was some controversy about the interstate radiation corrections there. Have you undone that? And have you looked at the update on the cross sections where a different approach was used?
So right, okay. So first of all, there was a factor to be applied that was we found in a thesis. So we did apply that correction, and then if I'm not wrong, the radiative corrections are mostly important in the large Z region, and so that's why we cut that region away. So that's what the grade.
All right, thank you so
I
much.
hope I answered. So. Thank you. Thank you all.
All right. Thanks, Valerio. And thanks to those who asked questions and comments.
Thank you.
Right. Next speaker today is Ignacio Shimemi from Madrid on jets and TMD extraction in CDs. Please, Ignacio, you have 25 minutes. You will be warned 3 minutes ahead.
Sure. Let me share this.
Very good. We see the slides.
See the slides. Okay. Yeah. So yes, CDs was together with Jets was in the original title. Then speaking with Anna, she was also interested in the plus and minus. So I included also a discussion on the plus and minus in this talk. So the work I will speak about actually were published last year, but this still there is some work which is going on. I will not present much or anything about the new development, but I think it is interesting to go back to this paper. They're not so old, to make some points which probably they have been a bit overlooked. So the idea is to study the hadron extraction of the nuclei, and we want to use jets in series and plus and minus to investigate it. Why to use jets? The prejudice that we have is that we have a better control of hadronization effect in a jet with respect to standard fermentation functions that was the subject of previous talk. And if you combine it with the TMD, we have also an alternative study of TMDs, say, where we have a jet in the final state instead of a HAL. So it is interesting to take this perspective in this kind of study. So the idea is that the following: we have shown here a standard series reaction for TMD studies. So we have series, and usually we have a factorization theorem which expresses this differential cross section in terms of the TMD PDF and the TMD fragmentation function, all with the normalization scale, rapidity scale of the case. Okay. Now, if we would like to see if it is possible to replace the fragmentation function by jet. The point is that the jet introduces also some new variables, like the radius of the jet or a jet algorithm. So it is non-trivial in the sense that there can be jet definitions which are compatible with the factorization theorem like this, and others which are not. So we have to study them. Then there is the case of E plus E minus. The case of E plus E minus is extremely interesting because of the following. Suppose that we can define something like a jet TMDs, and that we can fix this jet TMD mainly perturbatively. Then what is left over here is just the evolution kernel of the TMD. And so we could study in principle, if everything goes right, the evolution kernel with a higher precision than in another experiment. This is probably better shown in this slide. Here I have rewritten the series and the plus and minus cross section, putting into evidence this evolution kernel, which is this function R, which appears in these formulas. And you see that if, in the case of a plus and minus, if the J part, the jet part, is actually very precise, then the only non-perturbative piece which is left over is just the evolution kernel. And because the evolution kernel appears in all processes involving 3MDs, having this piece of information isolated will be, from an experimental side, will be extremely important. So these are the questions that we would like to address. If you can write the factorization theorem with jet, and how much this factorization theorem basically depend on the features of the jet. And of course, then things can be improved. We can consider groomed and groomed jets and so on and so forth, which we have also considered in some works. Now, when I go to jet observables, we have to take care a bit to what is the transverse momentum there. So I've considered here the two cases of the plus and minus, which is shown on the left magenta box, and the series, which is in the right magenta box. So let me start with the case of the plus and minus. Then the Q, the transverse momentum, is actually the transverse momentum of each jet with respect to some axes divided by the energy fraction of each jet. And the energy fraction is defined as the energy of the jet over the square root of S. In the case of series, our transverse momentum instead is a combination of the transverse momentum of the jet, say the same quantity as we had before, this Pj over Z, plus the initial transverse momentum of the quarks or gluons, which are inside the initial part. Then there is a fundamental quantity, which is this tangent theta, which has a very similar definition in the two cases, which is, if you like, the angular analogous of the transverse momentum that we had before. Now, in the picture, we see that these theta and R are actually competing because the jet has this radius dimension, then we can have several cases. There is a case when the radius of the jet is extremely small, so this means that the jet, for instance, is just 1 hadron, and we can reduce it to a standard fragmentation function. Or the cases where instead of this R is of the same order of theta, or perhaps the most interesting cases where this theta is much less than R. This is the most interesting cases because in lower energy experiment, the radius of the jet cannot be extremely small. So they're usually of order 0.5, 1. So, but it's very difficult to have a jet with a value R of 0.1, which is actually more easier in LHC style. So in all cases, we will work when for the factorization theorem where this theta is much less than 1. Now, let me speak about some features of the jet. The jet is just a rule to define an observable, an infrared free observable, and it's a rule to collect hadrons inside a quantity. So there are different rules to collect the hadrons in the jet. These are called jet algorithms, and usually the most usual one is, well, one of the most used is the anti-KT algorithm, which we will consider in this case. And one has to see that the algorithm does not really enter in the factorization theorem. We just say it's a rule with, say, to define our collection of hadrons. What really enters instead is the jet radius, because depending on the jet radius, one can include inside the jet more or less soft radiation. So that it's a soft radiation which will define important properties of the jet, like, for example, the axis of the jet that we want to consider now. So the problem is not easy. Say, usually here is I've written a formula for this jet function. basically the jet function can be defined as a matrix element of a certain operator, which can depend on the algorithm. And if you want to expand or understand this jet function, one has in effective theories, I'm thinking specifically of software linear effective theory, one has to do all these analyses of modes, which separate hard interaction from collinear interactions and soft interaction. And say, I don't want to go through this table, but actually the message of this is that the computation of these modes actually depends on the relation between theta and r, and also the choice, for example, of axes, WTA axis and the standard J axis, which are here written as WTA and SGA. Okay, so there can be different issues related to these modes. And the factorization theorem so will depend on the kind of modes that we have. One thing that you can probably appreciate is that if I look at the first three modes, which are the most important ones in the factorization theorem, you can see that the first three modes are equal for all ratio of r over theta, or relation between r over theta, in the case of the WTA axis, while when we go to the standard jet SGA axis, the standard jet axis, depending on the relation between r and theta, the modes change. And this has important consequences. In fact, let's consider this problem of the axis of the jet. So standard jet axis is, if you like, a standard way to define an axis of the jet. And basically, we sum all the momenta of the particle inside the jet, and the resulting momentum is defines the direction of the jet. This is given by the formula which says that this P12 is P1 plus P2. Okay, what happens to this? That when we change the radius of the jet, actually the direction of the momenta changes, because although we are running soft radiation, the axis actually is affected by the soft radiation which are included in the jet. So, so it means that the axis so defined is less stable, then is much more sensible to hadronization effect in the case of the standard jet axis. And also in the case for large R, basically, we not only we are sensitive to the soft radiation inside the jet, but also we are sensitive to a hard interaction inside the jet, which forbid that this axis be useful for the case of a large radius. In the case of winner-take-all axis, instead, the situation is different. Basically, the way to define an axis in this case is, here I show a formula where I use two hadrons in the finite state. Basically, the energy of the axis is defined as the sum of the energy of the axis, but the direction of the axis, which is this P, is basically the direction of the most energetic particle. So this direction is not changed adding soft interactions. So at the end of the day, this axis is basically is not really affected by changing the radius of our jet. So this is a definition of the axis, which is very easy also from an experimental point of view to implement, and which gives rise to a very stable axis definition. A test of this we did with PITIA. Basically, in this plot of the left and the right, I show the cross section for I think it's series case for different jet radius. So in the left, there is the winner-take-all axis, this WTA axis, and in the right, this standard jet axis. And we see that when theta goes small and r goes high, the standard jet axis basically explodes. It is not stable at all. On the contrary, when theta goes small and r goes high in the WTA axis, basically the curve tend to converge. We basically are insensitive to these radius. The fact that the curves explode in the standard jet axis means is actually a manifestation that the factorization is broken. In this case, when we go to large radius, large radii. So, how do factorization work? As I said, we can distinguish several cases when this theta is of the same order of the radius, or here I show when the radius is very small. So let me start from the top. I consider the case of the plus and minus just for reference, and in this case, basically everything is small. All the parameters are small, and one can easily prove that there is a factorization like this. And actually, in this case, and also in the definition of the jet depends a bit on the axis. If the radius is very small, which is the second case, basically the jet reduces to 1 hadron. So we go to the standard TMD fragmentation case, more or less. And basically, in this case, the result is independent of the axis. Standard jet axis or WTA axis go to the same. And we can actually refactorize our jet in a coefficient function and a residual function. Both have been calculated perturbatively, and it's no surprise that the coefficient is the same that appears for the TMD fragmentation function. Basically, the physical framework is the same. Okay. Now, the other case happens instead when, yes, the QT, the theta is still small, but we have a large radius. What happens in this case? Well, it happens basically that all the radiation is collected inside the jet. So we have this delta of 1 minus z in the definition of the jet, which means that there is basically no more dependence on the energy fraction. And it happens that this residual function is independent of the radius. Basically, we can go to infinite radius stuff. Now, we can perturbatively calculate these things. We did a explicit calculation up to next to leading order, but we can do even more. The point is that at two loops, we have everything predicted by the Recursion relation or the normalization group equation. And we missed just the finite part at two loops. And we made not a direct calculation, but a numerical calculation using this code, which is called event 2. And basically, we have also this piece of this jet function at two loops. Given this, we can use these, we have basically all the ingredients to perform this kind of research at N3LL, which is extremely precise, also from the perturbative point of view. Okay, now this is a resume, so of the factorization formulas for all cases. And I wanted to show in this that we have every time the same evolution kernel that we have in the TMD cases. And using the WTA, we can have this jet function. We pass it smoothly from one type of jet function to the other type of jet function, say from the finite R to the infinite R limit. But the point of all this is that apart from the smooth transition of this jet function is that our factorization theorem is works for all jet radii. Basically, we can have a continuum transition from this jet function, which are in the first formula, to the jet function, which appear in the second formula. But the WTA axis is basically still the same. You do not have to say, even from an experimental point of view, it's much easier, you say, in the sense that you do not have the restriction to choose one particular values of jet radii, but you can work with the jet radii that you have, and basing ourselves on what you can have for this parameter, then we can make our analysis, and we don't worry of the consistency of the data with respect to the theory. And I think this is very nice. Now, I will show now here some plots of the study that we did. See, so this was the dependence of this is the lab case, plus and minus on the jet radii, and of course it depends on z in this case, and we choose two values of z just to show up. So we start with this magenta curve, which is on top with the small radii 0.1, and then we go down 0.3, 0.5. 0.5 is the green one, and we see that already at r equal to 0.5, this is basically equal up to very large qt to the infinite range, infinite values of r. At r is equal to 0.7, they cannot even be distinguished. Changing the values of z, the situation is, well, the curves flip is in some sense, and but the situation is very similar. From 0.5 on, actually the curve 0.7 already coincides with the one of large r. Now, probably the most interesting case for the time that we are is the Belle case. So here the energy is much smaller, and still Belle data can be analyzed. So this is the case where R is, we took it to 0.5 basically. And for some numerical accident, this case is very close to the R equal to infinity. And so, and we checked our theoretical errors, changing this case at the various orders that we have. And because we can reach N3LL, you can see that the precision is pretty high. Okay, so even at Belle, and also is very high also at the lab. So, and we have also a consistency in the sense that all curves basically go inside the previous bands. Another plot showing the dependence on the energy fraction or that we have, and I don't know, we have two curves here. And so what we observe, okay, this average energy fraction, the smaller it is, the better it is in some sense, but okay, this is what we have, say, more or less. So in the case of a LEP and higher QT, we have more spread than in the case of Belle and pretty high R. Finally, I wanted to show the dependence on the TMD parameters, or well, not the TMD parameters, actually on the evolution kernel parameters that we have. So this is a graph, a plot from our paper of 2019. So it does not include the later studies on the evolution kernel that we did last year. And, but we consider two possible extractions of this evolution kernel. And there was one parameters in the, with Artemide, in this evolution kernel, which was this C0, and we took two different type of extraction, this BNP, with a fixed and variable BNP. And there is a difference in the cross section when we vary this extraction, and say we are sensitive to this difference. So there can be deviation from 2 to a few percent in the case of Belle, and the deviation is much less in the case of LEP because we are at a higher energy. But I think that so depends on the quality of the data that we have in these two experiments. Something can be said. We have not. Okay.
Excuse me, Ignazio, 3 minutes.
Yeah, I'm going to finish. I wanted to show just some plots for EIC. We took the case of EIC and HERA. We didn't take the case of compass. The energy of compass is too low for jets, but EIC at 100 GeV can certainly be an option. Or we can revise the data of HERA and see what happens. And here we consider several values of the elasticity, this Y term, and for say R equal to 0.5 and some values of zeta. And you see that because we are at an N3LL, the errors are still pretty small. And again, at EIC, we have checked if we are actually sensitive, and how much we are sensitive to the kernel of PDF. And this is a spread that we have, basically, on the order of 5%, a bit less in the case of HERA. Now, there is something, a study that we didn't do at the epoch, but probably one can think to do is, in the case of CDs, how all this stuff depends on the PDF set that we have chosen, and if there is a better set of PDF or not. Now, to conclude, the JET offer an opportunity to study TMD PDF and factorization. We have basically factorization theorems, which are very similar to the one that we have to the PDF, and we have the same ingredient that enters, like the evolution kernel. There are also the possibility to study the jets also in combination with the fragmentation function and TMD PDF. Basically taking the plus and minus where we have one jet and one hadron, or taking series, for instance. So, and on top of this, we can study also polarizations. So there are a lot of things that should be explored, and the advantage that I think for the evolution kernel and TMD PDF that jets can offer is that they are perturbatively, they are more stable from the perturbative QCD point of view. So probably we can control it better, but we have to check it. This is just probably a prejudice of mine. And there is a way to have jet features under control, like radius algorithms and so on, so that everything could work. So, well, that's all. I think I thank you for the attention and inviting me. And,
thank you, Ignazio. Perfect timing. Thanks a lot. I can see that Alexei has a question.
Yeah, so Ignazio, thank you. So I am actually amazed that you're so sensitive to TMD evolution. As you know, it's my beloved function. So, but if I correctly understood, so the main sensitivity happens actually at Q equal to 2, 1, 2, right? So is there technical possibility to measure such small QT in jets? So maybe it's more question to audience, to the experimental part of audience.
Well, I think yes.
You see, so at least in these plots, so okay, you basically sensitivity starts at QT equal to 2 and simultaneously have very large Q and S.
Well, EIC, let me say something that this I know, that the highest luminosity of EIC happens at 100 GeV. Okay, and this is actually the situation which is shown in these plots. So from the luminosity, I think this is the best that we can have. It's better actually 100 GeV than 140 because the luminosity is less at 140. Then the beaming that they can achieve at EIC, I actually don't know. Probably some experimentalists can help me in this. But well, if you like, I mean, I'm a theorist, so what I can say is that if you want to be sensitive, this is where you should look at. And,
okay, understood. So,
but
just I'm a bit suspicious that we can really measure it at such a small QT.
Probably we have been a bit conservative here. You have taken this Q at from 10 to 25 GeV. This parameter can also be changed. Probably can be put higher, and then the QT becomes a bit. So here we have taken a 3 as a 30% basically of this 25 or 15.
Okay.
But if we can increase this Q here, then we can go to larger. larger values of Q. So this experimental situation should be studied better. Disagree with you.
Understood. Thank you.
All right, Marco has a question also. Please, Marco.
Yes, thank you, Ignazio. Very nice talk. I have a question. If you can comment on the recent suggestion to study effects like Sievers and the Collins effect at EIC, because those this suggestion is based on the anti-KT algorithm. So can you comment on the how reasonable is this suggestion in the EIC energy configuration?
Yes and no, in the sense that I think it is possible, and the algorithm should not be a problem, in my opinion. It's not the algorithm is not the one which can falsify your factorization theorem. What can be a problem is other features of the jet, which are radii, axes, and energies, as Alexei pointed out. So EIC is a framework where the jets are made not of hundreds of particles. They are made of almost 10 particles. So one has to see if these other features of the jet, like radii or definitions, provide some errors. But I think all the field is under development now, so I cannot have a definite opinion about this. But I think it is interesting to look at. One should look at better this stuff. See, one important thing about this is that I should go to the beginning. Say the point here is okay, keeping fixed the jet, the F, the TMD that you want to study can be whatever you like. Now, if your kinematic conditions of the experiment are fine, and if you have a good control of the jet, this means that the Sievers function or whatever function that you want can be really better measured with jets than with hadrons in the final state. Now,
okay,
this is my prejudice.
Yeah, my question was exactly about this. I mean, if the details of the jet and I mean, understanding the details of the factorization, the soft factor, whatever, can be clearly defined and isolated in the energy configuration of EIC using the anti-KT algorithm. So my question was about the factorization, basically, and if the soft factors are the same as in vacuum fragmentation. That's it.
Yeah, I think in this case, yes. Now, I think it's not really a problem of factorization theorem, then, but of the assessing that all hadronization effects of the jet are more under control than with hadrons.
So you mean smearing effects, all these things?
Yeah, so this stuff, this should be checked with definitely more detail. I think one good thing of this approach is that at the perturbative level, we have the same precision that we have for TMD. So we go to N3LL with jet. And so this means that, I mean, we don't lose steps in the perturbative race with the jet.
Thank you.
Welcome.
All right. Thank you. Thanks all the speakers. I don't see more comments here. I want to draw your attention to a vivid discussion that goes on the chat, discussion to Valerio's talk. So please read it, interesting comments. Thank you so much. So we are now on coffee break.
Yes, we will start again 10 past 11 as foreseen. Thank you. Andrea, do we have a photo?
No, I think that we are good.
Nobody missing yesterday.
Some were missing, but if the audience is most of what we had yesterday, I think Ignazio was taken and others which were present today were also taken. So for me, we are more or less, I see Craig, maybe Craig was not switching off on his camera. We can take an overall picture and I will pick up.
This afternoon, maybe. I don't
Yes,
know.
in the afternoon where the most of the persons, also from the US, will be there. I think we can wait for the afternoon and collect.
Yes,
yeah. So I have a good coffee. Ah, Wolfgang, what are you trying to do?
I go to classes. Enjoy for me. 2 hours classes now.
You see what in the projections, what you can pin and have a look at what we have right now in the poster photo.
Okay.
Just on the top Zoom assistant.
Okay.
So at least to have an idea.
I see.
It's a good composition. I like it.
Yeah. It's fine. Good.
Good.
Very good. Have a nice coffee.
Yes, have a nice coffee.
Bye-bye.
Ciao.
Bye.
question. And we start with Alexey Vladimirov on global fee extraction of TMD PDFs from Drell-Yan and CDIS data.
Thank you. So, okay, it will not be only TMD PDFs, it will be fragmentation functions. So, but anyway, so I'll concentrate on unpolarized TMD distributions. And I should say that I have actually a huge presentation and I will try to manage it in 25 minutes. My talk will be mainly about our work with Ignazio, which is called quite often now SV19. So, and the main features which I'm going to present is that actually we provide a joint description of Drell-Yan and CDIS data inside of TMD factorization theorem. We do it with a quite high perturbative order. So in particular, we use an NLO matching for fragmentation and for pattern distributions. And also we use an NLO or an 3LO TMD evolution. So we made two extractions. So in a resummation like notation, it will be NN LL prime or N3LL orders. So an important feature of our extraction is that we use data prescription and we independently define all non-perturbative elements. So extraction is done with Artemida framework, and you can find it here. And actually all codes which we use to feed are also public, so you can, if you want, repeat it or modify something. So yeah, let me come to the body of presentation. So just as Ignazio showed, and this formula actually very similar to what he showed already. So we use data prescription, and data prescription cross-section in TMD factorization is split into three pieces. So we have evolution kernel, and we have two TMD distributions. So for example, in case of CDIS, it is pattern distribution function and fragmentation function. And what is important that all these three functions are non-perturbative. And they do not crosstalk to each other. So they are completely independent non-perturbative function. For each of them, you can write independent operator definition. So these are three independent physical observables. And so our cross-section is dependent on four variables. And each of these functions depends on two variables. Say rapidity anomalous dimension depends on B and gives you behavior in Q. TMD PDF depends on X and B, and the fragmentation function depends on X and B. And that's why we actually were able to decorrelate this function if we look at four-dimensional binning in X, Z, Q square, and QT square, and okay, extract them. So each of these functions are totally independent, but in principle we can, and each of them depend on two variables, but it is kind of too-much parametric freedom, and it's very difficult to extract it. It would be very difficult to extract it unless we use some extra information. In particular, we use information that we know that at small b, which is large QT limit, if we make Fourier transformation. So our pattern distribution, TMD distributions match to pattern distribution functions. So if I make small b expansion, so I can write down operator product expansion, and leading term will be just coefficient function in convolution with PDF. So nowadays, actually, this coefficient function is known up to 3 loops. It was published something like half a year ago. And in fact, we also know all higher corrections. So for example, recently I computed with my collaborator all these b squares, so all powers at these three contributions. So what in our expression, we use just this C1 F1 part at 2 loops, and the rest we just replace it by some non-perturbative ansatz. So here we exactly match to pattern distribution at b equal to 0, and then we have some tail which is parameterized by by these functions, as you can see it. We used 5 parametric functions for transverse momentum dependent distributions, and for fragmentation function we use 4 parameters. And our functions they have quite peculiar shape. They are Gaussian at small b, but then eventually became exponential. Important to mention that we do not have flavor dependence. So all flavor dependence is given by PDF and KC1. So non-perturbative part is completely flavor independent for a moment. So another ingredient is evolution. So it is Collins superkernel, and as it also Collins superkernel is also can be written as some particular matrix element of some particular operator. So this VC is some contour of Wilson lines, which I did not specify for a moment. So and we also can use here perturbative information because at small b it gives us just usual perturbative Collins superkernel, which is now known also at free loop. That was what's used in our feed. But at high B, it should be parameterized by some answers. So, and we use this particular answer. So here it is resummed free loop expression for Collins superkernel, and then it turns slowly to some linear asymptotic. Why linear, I will discuss in the end of my talk. So it's actually our input is the same as was used in the latest Pavia group, Pavia group extraction. So and free low evolution and two-loop matching. So with that input, we made actually chain of extractions, many of them, and just to check the universality of TMD distribution. So our first extraction was made just for unpolarized Drell-Yan process. So we used simultaneously low energy data, high energy data, which comes mainly from LHC. We fit it together, and since it's have a large span in X and Q, we were able to extract pattern distribution function and Collins superkernel. So then on next turn, we actually plug in this information to CDs, and we simultaneously add one more parameter, which is a fragmentation function, and we feed only fragmentation function, do not change in anything in our evolution, and do not change in anything in our pattern distribution. And then we were able to feed nicely CDs, so with high square equal to 1. And this gives us transverse momentum dependent fragmentation function. And this way, actually, we see that indeed our TMD factorization is universal. So because we extract in one process main part of theory prediction, and then we predict actually in our process. So if we do a joint feed, so it's just slightly fine tune our parameters, and we get slightly smaller high square, but generally, so the picture doesn't change. So it also can be plugged, say, to different processes. For example, I also considered pi and Drell-Yan. So I took all information extract from unpolarized Drell-Yan, mean evolution and proton part distribution function, and extracted pi distribution, and also with good high square. You can also continue it, and for example, recently we plug it in Sieverts observable, Sieverts sensitive observable. So you take all this information, so pi distribution function, fragmentation function, pattern distribution function, you plug it in, and then you can actually see that you nicely describe CDs and Drell-Yan observables from various experiments, and you can extract Sieverts function. And you can continue this chain. Okay, we didn't do it yet. So so transverse momentum dependent factorization theorem is really universal. So and we now can see it. So what is the role of COMPAS and all that? So it's actually its role is very huge. So we used the COMPAS data, especially in extraction of unpolarized CDs and in extraction of Sieverts function, which we will not discuss. And this pi distribution, pi induced Drell-Yan was actually motivated by oncoming measurement of COMPAS of pi induced Drell-Yan. So I will later on discuss that. Okay, I hope to get some new CDs data from COMPAS. There are still plenty of questions on our extraction, and unfortunately, I will not be able to cover all these questions. I will just cover some favorite of mine. And the first one is actually where limits of TMD factorization, because all of us know that TMD factorization work in the limit of large Q and small Qt. And so here's example of some bin from COMPAS. So and if you go to say high Qt here, so PT in CDs, so we see it our TMD factorization start to deviate from data, and we do not fit with data. So in particular in this plot, so the field points are the points which were participating in analysis, and the empty points we cut out. So the question is how far we can go in this PT range. And for that, we did the following test. So we actually cut our data such that with some parameter delta, which is just number parameter, so and test. So for each increase in delta, we perform separate feed and check at which moment actually our feeds start to significantly deviate from 1. So high square divided by number of points significantly deviate from 1. And interesting that actually in all studies, the similar study has been made also in recent Pavia extraction, we actually all these predictions show more or less the same number, so that we actually should cut TMD data at Qt something like 0.2, 0.25 Q. So you see, this, we observe some plateau at smaller delta. So here TMD factorization works well, and then it starts to deviate. And somewhere at 0.5, it's completely, I mean, you have high square equal to 5 or something like that. Okay, so even so, we have quite a lot of points. Say we have, you've seen already this plot in Alessandra's presentation. So we have definitely some high energy data, which comes from Tevatron and LHC, and it's only for Drell-Yan. We have also low energy data, and CDIS is the lowest energy data. So here it is with two blobs. So here is a compass and here is Hermes. But still altogether, when after application of all cuts, we have something like 1,000 points. And global high square as a total is pretty good. So of order of 1. And these are how it looks like, so our extractions. And what is interesting, and that's what has actually raised some discussion, is that we do not see any contradiction between Hermes and compass data, which were observed by some other groups. So here is an example of CDs measured at Hermes, and here's an example of CDs measured at compass. We do not use any extra normalization condition. So there is no fixation of points or anything like that. So it's all absolute values of multiplicities which we get. Okay, so what are possible sources of agreement and disagreement between different groups? Why, for example, in extraction made by Pavia group in 17, so they observe slightly different picture. First of all, actually, we use slightly different data for compass. That's also a possible source. But there are also some sources from theory side, and particularly also it was mentioned by Alessandro that actually perturbative correction at such low Q, and Q here is, you see, is of order 4, but it can go up to 1 in some bins, is the perturbative corrections are large. Say if you go from first normal order, which is NLL, so you just switch on evolution to one loop, so you have this dashed green line here, and free low order which we use is somewhere here. So the difference between them is so for the 45%. And this is just one bin. So in different bins, this difference is different, and also it is actually also affect shape because TMD evolution changes the shape of distributions. So this is one possible source, and probably the hugest source of the agreement disagreement between different groups, because just we use different orders of perturbation theory. Another source which I think is important is actually how we treat charged hadrons in final states. Because generally speaking, so charged hadrons should be treated as a sum of all possible hadrons. Say for H plus, it should be P plus, K plus, plus proton, plus whatever. Okay, we use only pion plus kaon, just because proton appears to be not so important. It could change something like 2-3% in the end. But say, again, in the Pavia 17 extraction, so they use only pion. They identify hadron as just a pion. And the difference between these two cases, say if I would switch on kaon and switch on and switch off kaon, so is about 15%. So you see, it's plenty of room for this agreement, disagreement between different extractions. So that's why I would say it's nothing strange that, okay, some group could see disagreement between Hermes and compass, and some do not see it. Actually, maybe it is even good sign. Okay. On contrary, I would say that we see some problem with normalization of low energy Drell-Yan, which is not discussed only by us, but also by some other groups. It happens only at fixed target experiments. So for example, if I look at Phoenix here in the corner, so you see here there is no problem in normalization, while if I look at this Fermilab data, there's quite significant change. Say in this lowest energy bin, we have 30% deficit of normalization. Okay, I bet that it is due to larger X effect. And I should say that this problem becomes even more dramatic if I go to pion Drell-Yan case. So in pion Drell-Yan, so this is example of data from, what is that? It's E615 experiment. So deficit in normalization for some bins, for example, this one, is 60%. Of course, so you should take into account that actually here is a very large correlated uncertainty, which is 16%. But even so, if I make a decomposition of my chi-square, for example, here, so globally for this set, I have 0.7 for shape of distribution. So TMD factorization perfectly describes shape of this distribution, and I have 0.77 for normalization. Take into account 17% normalization error is just a huge number, in fact. Altogether, it is 1.5, so not that bad, but really in Pion, I see this problem. Interesting that this problem presents only in that data, which is most precise data. Say if I go to another experiment, which takes several years earlier, so it's something like 1981. So here, okay, except very first bin, which is probably due to very large X, I do not see any significant problem in normalization, but data is of course much worse. So, and to resolve this problem, so I'm really waiting for Pion-Drell-Yan data by COMPASS. Yeah, so here's another example. So in a free measurement, unfortunately here we do not have good data. It's just a plot. It's just a copy of plot from paper. But anyway, so even so, I do not see significant problem in normalization. Okay, so LHC data I will not discuss. So it's nothing very better than LHC data. So it's nice that we can really see that when we do a global fit, so when we simultaneously feed Drell-Yan and CDIS, and we simultaneously feed part distribution function, evolution parameter, and fragmentation function, actually they're not really correlated. Okay, there's some parameters are correlated, but generally, for example, part distribution function, which is given by that box, and the fragmentation function, which is given by this box, so it is a plot of correlation matrix. So here we have everything almost white, so there's practically no correlation between them. However, we see and observe very strong dependence on our collinear input. So as you remember, I told that to reduce parametric freedom, we use matching to collinear input. And actually, if we start to vary, for example, we start to vary our input PDF, which was NNPDF, by 1 sigma, our chi-square varies from 0.8 per number of points to 6. And for that reason, we actually cannot really accurately estimate PDF uncertainty, because if we take some forest sets, some forest replicas of an NPDF, we just cannot fit the data. So, okay, we tried to do this exercise. For that, we need to reweight this NNPDF set. So, and then we fit with delta FNP, and here I show just example. So it's not absolutely correct picture. So it should be detailed study, which we try to do now. So how the band looks like if we try to include so this uncertainty on collinear input. Okay, let me go to next slide, because here is a ratio of this band. So a red band is a uncertainty in intrinsic KT. So it is uncertainty of non-perturbative part, and blue band is uncertainty due to PDF set. So they're independent here, so we do not add them up. So you see, so the uncertainty due to collinear set is actually much higher than uncertainty due to non-perturbative part. Especially if I go to say to x equal to 0.5, which is many of low energy experiment located. So that's why I think that this is a problem in this normalization. So you see this here we have error up to 50%. So that's easily can describe all these problems with normalization. In fact. Okay, so anyway, so in the end of the day, I can say that we know what are unpolarized TMD distributions, although we of course have some uncertainty. So here is shown by color in this beautiful three-dimensional plots, and there is also some systematic uncertainty which we don't know, just like I show here. So I would say that it's something like 10 to 20% on top of this picture. But still, we can already think about interpretation of this picture. So this picture is given in B space, so that's why it's maybe not very informative. So let's go to KT space and look at it. So, and I would like to just show you some example of picture how, say, in KT space, proton is different from pion, just because it's very spectacular difference. So you really see that proton, so here is distribution of U quark and proton and U quark and pion. So we really have different KT distribution. So protons, you can see much narrower and have really, you see it's valence quarks running here, while protons looks very different. And same in fragmentation function. And here I would like to add some comments on flavor dependence. So in our feed, we do not distinguish flavor, and we also do not distinguish kind of species of particle. So kaon and pion are fit by the same non-perturbative profile. So what is different is only collinear input. However, generally speaking, this non-perturbative profile should be different for them. So if I would try to do so, of course, I have some problems because the data on count, for example, is not that good and comes only, so the separation of particles we have data only from Hermes. But if I try to do so, I actually see that pion and count are really different. So here, for example, we have some parameters of our model. So let's look, for example, what this eta 4. So this upper point is for pion. If I this second point is for count, and actually in reality, I mean, when we fit them all together, we had something in between this lower point. Of course, the count point you see has very large uncertainties. Definitely see that they are different. So pion and count have different shapes in terms of momentum distribution. So and here you can see how it visually looks. So pion is much narrower in comparison to count. So that's why there was discussion 2 days ago, is it sensible or not for COMPASS to measure, to produce identified particle cities? So I would say it's very sensible. So, and I would be very interested to check the data and actually define what are difference between pion and count TMD distribution. So not even in terms of flavor dependence, but in terms of particle dependence. Okay, so and then let me come to large, but the last part of my presentation. So I would like to spend several slides on TMD evolution kernel. So I really like that function, and I think this function is one of most important in all this business. So this is our extraction of Collins-Soper kernel. So we call it D, and it is equal to -1/2 K, which, for example, used in KSS formalism. So as I told, so we use this ansatz. Here we have perturbative contribution, which acts here, and then some linear dependence. What is nice that this extraction is practically independent on collinear input. So what I showed here, that we have this huge dependence on PDFs on collinear input, doesn't really affect extraction of this Collins-Soper kernel. So here you have, you see very different extractions. They more or less produce the same numbers. However, if we compare different feeds which were done by different groups, and here I show 4 of them. So it's our feed SV19, our feed of two years earlier, SV17, and also latest PV extraction and earlier PV extraction. So these distributions looks pretty different. And of course, it mainly happens because we use different models. So for that part. So as you can see here, at b equal to up to from 0 to 1, we more or less coincide because this part is dominated by perturbative input. But then actually all models are different. So and actually all 4 groups use linear asymptotic, quadratic asymptotic, even quartic asymptotic, and error bands are still quite small. So in fact it means that if we go up to b bigger than 1.5, we are not really sensitive to this object. And this is very pity. So another interesting observation that actually when we consider data which contains CDs and Drell-Yan, we get generally higher Collins-Soper kernel in comparison to extraction of only Drell-Yan. So you see here 2 branches. So this branch and kind of that branch. This is really great object to study because this Collins-Soper kernel is something which tells us information about QCD vacuum. So when we study TMD distributions, we study something about Hadron, but to understand really QCD, we should think about vacuum. So if you would like to understand, say, problem of confinement, we should look on the properties of vacuum. And this Collins-Soper kernel is exactly something which measures as vacuum. So as I told, so you can write operator expression for it, and you see this is matrix element by vacuum of gluon-Stank tensor with some Wilson loop. So interesting that you can, for example, compute it. Okay, we know b equal to 0 computation up to 3 loop order, but you can also compute, for example, power correction. So I did it earlier this year. So and actually with power correction, so it's given by some operator, but you can estimate it by some rules, and this estimation tells you that it's more or less gluon condensate, which you can take, for example, some lattice extractions of this gluon condensate and get this number. And what is interesting, this number is actually very small. which you can expect because it's vacuum matrix element. And what is nice, all these extractions, which I show here, they more or less agree with this number which comes from lattice. What is also interesting that, say, if you look at a BLNY extraction, so the number which they produce is order of magnitude higher than you would expect from theory. So this is only one example of what we can study from this fascinating function, because you can also study, for example, string tension. You can just derive expression for it from here. You can even using some model computation derive confinement potential from this repeating numerous dimension, and it actually this derivation tells us that at infinity you have to have linear asymptotic, and that's why we use the linear asymptotic in our extraction, because all other asymptotic will produce you not confinement potential but something else. So as you know, now there are a lot of efforts from lattice side to measure TMD distribution, and I'm happy to present some preliminary result by Regensburg group about extraction of this Collins-Soper kernel. So this is extraction of SV19, and these are preliminary data from Regensburg lattice group. So it's first extraction, which is done on real lattice, QCD lattice, without approximations. And as you can see, so it's I would say, especially for first extraction, it was generally agreement. So this red part have a lot of lattice artifacts. Small b you also should not look here, because there's here factorization theorem on lattice is violated. So in this middle part, I would say there's some agreement between phenomenological extraction and lattice extraction. So this is very, very interesting and very fascinating, and that's what we'll go into have in next years in more details. Okay, so I also had some, I don't have time, but I had some slides about impact studies for LHC and AAC. So probably I will just skip them because I don't have time. Presenting just final results. Say recently was a lot of efforts to study possible impact made by future EIC on extraction of unpolarized distribution. So, and this impact is actually very difficult to underestimate, because definitely EIC will measure, will just pin down all these distribution functions. Here, so this plot is probably main here. So this, how it will affect our knowledge of Collins-Soper kernel. And as you can see, the reduction of errors is just incredible. And this is because EIC have huge coverage, continuous coverage in Q. So no other experiments has such coverage. So that's why, so it will just really pin down this Collins-Soper kernel unprecedentedly. So other functions, say TMD part distribution function, so of course errors is reduced, but less, just because we also have LHC, which also significantly reduces error. So fragmentation functions, of course, seriously impacted. Okay, so I would kind of conclude that nowadays we more or less know what are unpolarized TMD distributions, but this is only first step in these studies, because there are still plenty of problems which we should address in future. And first of all, I would say we should actually understand which uncertainties we have on our extractions. We also should study flavor dependence. And as I told, so there are some issues with normalization, which is quite annoying, especially in this pi under Rho. So that's why I'm personally really waiting for pi under Rho from Compass. There are a lot of stuff which is going to happen soon. First, of course, there's new observables, like as I told, pi under Rho from Compass, but there are also new tools which going to come soon, like TMD Leap. There are huge progress on lattice, and especially in unpolarized distributions. So I think in 2-3 years we actually will have similar extraction to that, but for the distribution itself, which is much more difficult to measure in comparison to Collins-Soper kernel. Yeah, and some progress on non-perturbative modeling, which I just didn't discuss. So thank you for attention.
Thank you, Alexei. Thank you for a nice presentation, comprehensive talk. We have questions. Katarina.
Hello, thank you, Alexei. Very interesting talk. I had a curiosity around page 16, 17, when you try to use the pi-induced Drellian data from past experiments, and I noticed that you have difficulties to to describe the normalization of E615 data, but
Yes.
you did not try to use NA10 data. That is another large set that exists on Pioneer.
Data?
NA10. The reason I ask is because it is known there is a difference in normalization between the cross-sections given by these two experiments, E615 and NA10. They have around 20% discrepancy in the normalization. So I wonder if you would try to use the NA10 data, what you would obtain.
So actually, it's interesting to know that there is discrepancy in normalization for them. I didn't know it. So so this data which you mentioned, I think it doesn't have QT distribution, because for extraction of TMDs we need QT spectrum. And most part of these Pion data, they have just Q distribution, so only for total cross-section.
I am a bit surprised, but
if I will check it, but at least I didn't know that we have QT distribution, and I don't know it now.
Okay, thank you, Katarina. Marco.
Alexei, thank you so much for this nice talk. So on slide 9, you were discussing, let's say, a parameter to select the data.
Yes.
And I would like to understand a bit better the rationale there, because ideally what you want is that the chi-square is around 1. So to be smaller than 1 is not good, because means that you are overestimating the errors, or maybe your function or your covered range is too narrow, or your function, and you don't really test all the parameters of your function, let's say.
You're right. So ideally, in absolute kind of the ideal case, of course, we will have just plateau here at chi-square equal to 1, and then it will start to grow. But just you know, when you go to smaller delta, you have really small amount of data points. So if I correctly remember, at this point, it's something like 20 data points. If you go to 0.1, and okay, you have 10 parameters, so it's normal to have it very small. So, but you see here, for example, it's really something close to 1, and then start to grow. Here, something close to 1 start to grow. Same here, so it's no.
But did you conclude that cutting at 1 in Q is better, as an example?
So we conclude that cutting not at 1, but you see, so you should check where this plateau turns to growing. So and this plateau turns to growing almost somewhere in between 0.2, 0.25.
I mean, just to be provocative, if you take a Q greater than 2, just to stay in the safe side, and you apply your, let's say, prescription to have delta around the 0.2, your chi-square is lower than 1, so you're not in a good region, in principle.
No, yeah, but okay, theory tells us that we should take as small as QT as possible. So that's why.
I know that, but if you wanted to find a value for QT based on chi-square, I mean, you should account for the chi-square theory also.
Yeah, but okay, for example, here we have 0.95 per 1,000 points. So is it bad or good?
No, that is good because it's close to 1, sure.
So here we have it's a bit smaller.
Okay, one last question by Andrea Bresson. Andrea? Don't forget to unmute your microphone.
Yeah, I was unmuting now. It is on the same slide. I'm curious about the matching. Since this moment, okay, this select the region where you have TMD factorization, which is holding, but in principle, you would like to describe also the higher QT region with the PDFs and match the two regions. How is going on this?
So in our fit, we do not match with regions. So we just use, so we do not use Y term. So we use only W term. And actually, that's why here, say it with high delta, we practically not sensitive to any TMD physics. So we just continue until we can, so including the data.
But the white term is not bad.
White term is not bad, but we see why. See, even so, inclusion of white term will not help us to fit TMD distributions.
No, I know, but let's say for presenting a theory which is has TMDs and has the part of PDFs which are all together a complete theory, let's say, it will be nice to have this matching developed and carry on.
We are working on it, so eventually it will come. But for a moment, yeah, so just with the plot, say for LHC, so how we are sensitive in which region for non-perturbative parameters, just for demonstration. So you see, if I go to very high QT, so here's Q, so you see this is green. So it's whatever we change our TMDs, so we dominated completely by collinear physics. So nothing happens here. So that's why I just would like to defend our extraction. So our
no, but I'm perfectly fine with your extraction. Simply, I would like to have a more complete picture, which include also the collinear part.
I promise, let's say in 1 year we will give you a complete picture. But for a moment we have just TMD.
Okay, thanks.
Okay, just another question, Alexei. For COMPASS data, you underlined that you would be interested in PID data, pions and kaons for CIDIS, yes. And then also nucleon, pion nucleon Drell-Yan data. I guess also QT distributions in both cases,
right?
QT and QT. A question is like, with all these normalization problems, would it be enough just for a first step to have not the distributions, to have only the shapes, let's say, the distributions with arbitrary normalization?
No, in principle, so supposing that everything in our fit and in your extraction, in your measurement is good with normalization, yes, it would be enough, I think.
So only without normalization, basically with arbitrary normalization. But
yeah, understood. Yeah, actually, I do not have plot here, but in some proceedings several years earlier, there was preliminary COMPASS plot for pion Drell-Yan, just for shape. And I should say that my extraction perfectly agree in shape. So generally it would be interesting, especially for this exercise, pion versus count, to have already just unnormalized data. It's okay. But for pion, I personally would of course prefer normalized just to solve this issue with pion normalization.
Okay, good. We can continue this offline. Thank you very much, Alexei. And we switch to the next speaker. We are behind the schedule, 8 minutes is the delay. Sorry about that. We have next speaker is Jan Matuszek. He's going to talk about COMPASS CIDIS measurements, TMD-related measurements, asymmetries and multiplicities. Jan, please go on.
So good morning, everybody. I would like to thank the organizers for inviting me. It's a pleasure for me to speak at this workshop. Although it would have been a bigger pleasure to speak in Trieste in person, but okay. I'm going to talk about unpolarized CIDIS studies at COMPASS. So I guess we all know COMPASS. It's international collaboration running a fixed target at CERN. We're using secondary beam from the SPS. And over the years, we have run a broad research program. We've done CIDIS on longitudinally and transversely polarized proton and deuteron targets, Hadron spectroscopy, the first ever polarized Drell-Yan experiment. And in 2016 and 17, we have taken data for DVCS and also for CIDIS measurements with 160 GeV mu plus and mu minus beam and liquid hydrogen target. At the bottom of the slide, you can see the COMPASS setup. So most of it is a spectrometer with 2 stages built around 2 magnets. But for this 2016-17 setup, the typical thing is the camera recoil proton detector, which is surrounding the liquid hydrogen target here, and the ECAL zero calorimeter right downstream to catch the photons which come at the large polar angle. So the cross-section for producing a Hadron H in deep inelastic scattering on unpolarized target is parameterized in terms of structure functions. There are 5 of them, and they can be distinguished by different azimuthal modulations in the angle phi h, the angle between the lepton scattering plane and the hadron production plane. And it can be also rewritten in terms of asymmetries, which are ratios of structure functions. And they are amplitudes of the modulations in phi h. The structure functions can be interpreted in terms of convolutions of TMD PDFs and TMD fragmentation functions. Of course, there is the FUUT, which is a convolution of the unpolarized transfer-momentum dependent functions. Then the cosine phi h structure function, there is the contribution from the Kahn effect, which arises from the non-zero intrinsic transverse momentum of the quarks, KT. There is also a term coming from Bell-Mulder's convoluted with Collins function. And the cosine 2 phi h should come from convolution of Bell-Mulder's and Collins functions. And the sine phi h only from twist 3 terms. The convolution runs over the transverse momenta because, of course, what we can measure is the PT of the final state hadron, but this is composed of the intrinsic KT of the quark and the P pair obtained in the fragmentation. And the observables which are sensitive to this KT and P perp are the azimuthal asymmetries, which allow to access the mean KT via the Kahn effect. They also can give access to the Bell-Mulder's function, and the PT-dependent distributions, which give access to the KT and P perp dependence of the PDF and FF. COMPAS has published results on both these things. So there are azimuthal asymmetries on deuteron target and PT-dependent multiplicities on deuteron target. Additionally, we have published also a background to the asymmetries coming from the case of exclusive vector mesons, which was proven to be important later after the publication of the first paper. And we have this new data from 2016-17 taken with liquid hydrogen target. The primary goal was DBCS, but they are also useful data for CDs. The advantage over the older measurements is the pure proton target. Also, it's good to have alternating mu plus and minus beam because we can do some stability tests. Also, acceptance correction is crucial for these measurements, and here the Monte Carlo is developed in synergy with the DBCS group inside COMPAS. This is another advantage. In August, we have released first preliminary results using about 11% of the statistics, and we are working on this data to provide another results. But there is not just the past and present, there is also future. So next year we are going to take data again with the deuteron target, transversely polarized. And we're certainly going to look also in the unpolarized observables in this data. So now I'm going to speak about the published measurements. So first, the azimuthal asymmetries. We've studied unidentified charged hadrons in the bins of XZ and PT separately, so one-dimensional binning. You can see there is clear difference, for example, between H plus H minus. That's quite interesting. There are a strong dependence on the kinematics, especially at large Z. We see large asymmetry, cosine phi h. We have done also analysis in 3D, so in XZ PT together. And here you see also strong kinematic dependence. At the time when this was published, some features were not really understood, like how can you have positive amplitude of the cosine phi h modulation? You can see in some bins. Later, we have shown that this can be explained by the contamination from decays of exclusive vector mesons. About the PT-dependent multiplicities, this we have published in 4-dimensional binning in XQ square Z and PT. You can see it sketched here. We have taken into account both QED radiative effects and the contribution of the decay of exclusive vector mesons. So how this contribution works? Well, you can have the major contribution comes from rho 0, which can be diffractively produced. and it decays into pi plus pi minus, and these pions enter your charge hadron sample. So, and this contribution is important in certain bins, especially at small q square, large z, and small pt. So there is the contamination fraction plotted here. What was realized a bit later, that these hadrons coming from decay of exclusive vector mesons have large azimuthal modulations, especially in cosine phi h. We have shown this in the data when we have selected only the events with scattered muon h plus h minus. And if we ask the sum of the z of the two hadrons to be large, close to 1, we select this peak basically. And then we look at the correlation of phi h and z. You see that there is a very big modulation in cosine. At small z, the modulation is positive, and at large z is negative. So we have done a correction to the asymmetries, taking the contamination fraction from Hebgen and the asymmetries from this data analysis. And subtraction was done at the asymmetry level then. So the contamination is quite large in certain bins. You can see it can go up to 0.5. This is in the bins of XZ and PT. In other bins, it's quite small, but still, because the amplitude is very large, it has impact. Here you can see the impact in the lowest PT bin and in bins of Z. So we go from the empty points to the full points. And nice feature is that these positive values go to negative, almost all of them. And then if you compare the resulting cosine phi h asymmetry with the Monte Carlo based on Kahn effect and string fragmentation, you obtain a quite decent agreement. So I think this is encouraging. So now I move to the new measurements. So this is the XNQ square range that our data cover. And we apply the standard DIS selection. We cut a bit into this XNQ square distribution. We cut on Y and on theta of the virtual photon in order to have moderate acceptance corrections. Difference with respect to the older analysis that we also remove right away the exclusive vector meson decay hadrons. So if we observe only mu prime h plus h minus, we ask the sum of the z to be smaller than 0.95 to exclude this peak, this exclusive peak. We cut on z and pt to select the good hadrons. The binning so far is taken from the published results, based on the published results. So for asymmetries, it's 1D and 3D in XZPT. For the PT-dependent distributions, it's 4 dimensions, XQ square, ZPT square, but using larger bins with respect to the publication. In the future, we would like to do the two observables in the same binning, but this is not released yet. So I have said that we remove the visible hadrons which come from the decay of the exclusive vector mesons, which we can identify, where we see both of them. And about 80% of the decays are visible in this sense. But there are also the 20% of invisible decays where we observe only one hadron. So we cannot know if it is comes from decay or not. So to remove them, we use Hebgen Monte Carlo generator with the azimuthal modulations already implemented in. And we just normalize this Monte Carlo to the data using the missing energy distribution of the visible decays. And then we subtract in every bin, including the phi h bins. So we don't do the subtraction on the level of asymmetries, but already at the level of histograms or distributions, events, basically, which is more robust technique. Here on the left, you can see the contamination fraction. It can go quite high, up to 50%, again, like we have seen before, at high Z here, for example. But most of it is the visible component. This is shown by the empty point here. And the invisible component is only this. So only this is taken from Monte Carlo. And this is just cut by the event selection. Even if in most of the bins the contamination is not so large, the azimuth modulations are large. You can see them here. This is measured from the data. This is comes from the visible vector meson decays, and especially the dependence on Z is very spectacular of the cosine phi h modulation. It goes from +1 to minus, also almost 1. But also cosine 2 phi h contribution is very important. So even if the fraction is small, they have impact on the result. This is the impact of the subtraction for the PT distributions. Again, in some bins, especially small q square, small PT, and large Z, like this case here, the contribution is important, is almost 40%. In other bins, it's smaller. And okay, after removing this exclusive vector meson decay products, we do acceptance correction using a lepton generator and full Jean simulation of compass setup. What we do not do yet is a QED radiative effect correction. This is not yet taken into account. We plan to use Django Monte Carlo generator, which would enable us to evaluate also the impact on the hadronic variables like PT and phi h of the QED radiative effects. Here I'm showing the results for the asymmetries in one dimension in XZ and PT. You see qualitative agreement with the published results. So there is a difference between positive, negative hadrons. There are the kinematic dependencies very similar, except for Z, where because here we have subtracted the hadrons from decay of exclusive vector mesons, and this very large Z, very large modulation at very large Z has gone up. So the modulation is smaller in absolute value. Here are the 3D results for cosine phi modulation on the left and cosine 2 phi h on the right. So also this quite agree with the published Neutron results. And we see the same features. And here are the PT distributions shown only in 2 bins of Z. I'm going to show the other 2 later. So if we think about the simple Gaussian model for F1 and D1, we should get exponential distribution here. And we see some deviation from simple exponential. Basically at PT square around 1, we start seeing another slope. Here you can see all the Z bins. So for small Z to high Z here. And as up to 1 GeV in PT square, the distributions look quite nicely exponential. We can fit them with the exponential function and look at the dependence of the fit parameter, the mean PT square here, on Z square and Q square and X. And from the simple Gaussian model with fixed width, we expect a linear dependence on Z square. But if you look here, it's not always the case. So this suggests the dependence of the mean P per square on Z, or maybe also mean KT square on X. And okay, we can move to the conclusion. So the azimuth asymmetries and PT dependent distributions, they are interesting observables accessible in an unpolarized CDs. The azimuth asymmetries are sensitive to the mean KT via the Kahn effect, and they also give access to the Baer-Madras function. So the polarization, transverse polarization of quarks with respect to their transverse momentum. This is quite interesting phenomenon. The PT distributions, of course, give access to the KT and P per dependence of F1 and D1, PDF and FF. The contamination from decays of exclusive vector mesons plays an important role in both measurements. We have published results on deuteron target, or 6-lithium deuterium. We have new preliminary results from liquid hydrogen using about 11% of statistics and more robust method for exclusive VM subtraction. And certainly more results will come from this data. And we have a new measurement scheduled for next year, again with deuteron target. So these measurements provide important input to general understanding of the transverse momentum dependent structure of the nucleon. This we have heard in other presentations today and before, and of the fragmentation process, of course. So we hope to provide these inputs in the future as well. And this is all from my side, so thank you for your attention.
Thank you very much, Jan, for a very clear presentation and for perfect timing as well. Do we have questions to Jan? I don't see any hands raised. So, I mean, for 2021, this can be done also with PID, right? We can obtain the results for the asymmetries and for the PD multiplicities. With
yes, I hope also for the hydrogen data.
Hydrogen, no. I mean, not now. Okay, yes, in the future. This just going back to Alexei's comment. Okay, if there are no other questions, then thank you again, Jan. And we switch to the next topic. We change the topic. In fact, switch to emergence of hadron clusters. Craig Roberts. Jan, I guess you have to stop your share.
Yes. Where is it? Okay, here.
Craig, can you hear us? I see your mic.
I can hear you, yes.
Please share your slides.
I'll try that now. Is it visible?
Yes, perfect.
Very good, then I shall begin. Hello everyone, greetings from Nanjing in China. We had a lovely 30-degree day today. To begin, just a bit of background. Our universe existence depends on a few empirical facts. One of them is that the proton is massive. The strong interaction mass scale is very, very different to that of electromagnetism. The proton is also absolutely stable.
Sorry for interrupting, Craig. We have an echo. Jan, could you please switch off your microphone? Okay, perfect. Thank you.
Yeah, that's great. Thanks a lot. I was worrying where that was coming from. So the proton is absolutely stable despite being a composite object. That's unusual. Composite things usually fall apart. And the pion is unnaturally light. It's not massless, but it has a lepton-like mass. So we have a hadron, which is unusually light. And this is despite being a strong interacting state, just like the proton in many ways, yet it decays quite quickly. These are examples of emergence. We have low-level rules producing high-level phenomena with very complex appearance. And this is where it's supposed to come from. Quantum chromodynamics is one line and one definition, and that is supposed to describe all the properties of the bulk of visible matter. That's you and me and everything else that we can put our hands on. And the big question for us across the world is how it does this. So where can we begin to start to understand how this all appears? Well, I'm going to start with the gluon. And the observation made by Google, for example, it says that theory does not make predictions of gluon masses. Well, that observation, although written in 2016, is actually about 40 years out of date. We have known for quite some time that if you study the gluon gap equation, you study how the gluon interacts with itself in the gauge sector, you will see that those interactions very much change the characteristics of the propagation of a gluon. They produce stressed gluons, which are mathematically connected to the gluon partons, but have very, very different properties in the far infrared. In fact, if one combines the best information we have available from the continuum and the lattice, you can compute the gluon two-point function, and you will find that the gluon two-point function saturates in the infrared to a finite value. If this were a photon, this curve would continue to rise with 1 k² behavior to infinity. In QCD, it doesn't. There's a mass scale that causes this gluon two-point function to saturate, and that mass scale is about 0.43 GeV, about half the proton mass. Some might worry that this is violating gauge invariance. In fact, of course, it doesn't. We've known since the work of Schwinger in the middle 60s that gauge bosons can acquire a mass if they interact in a special way with their dressing fields. So long as it preserves this transversality condition, the appearance of a gluon mass does not violate gauge invariance. This translates into statements about the running coupling. We know what's happening in the ultraviolet. The big question is what's happening out here in the infrared. We've asked that question since QCD was invented. And we know that people have thought the running coupling is small in the asymptotic region and rises, maybe unbounded. And so people imagine we had infrared slavery, where the coupling runs to infinity as k² runs to 0. And many have interpreted that as being synonymous with confinement. But you can ask the question, is that correct? Is that necessarily true? And is that connection rigorous? Well, things are different in QCD. QCD is really rather different than what quantum mechanics might lead people to expect. This is the most recent computation of the process-independent effective charge in QCD. We have mathematical techniques developed over the last 15 to 20 years. It involves pinch technique, background field method, lattice QCD, continuum analyses of gauge field equations. And we can now define a unique process-independent effective charge that's completely defined by the gauge boson two-point function. In the ultraviolet, it looks just like perturbation theory, but in the infrared, it saturates. The coupling stops running. This is a parameter-free prediction based on continuum and lattice studies of the gauge sector of QCD. And you see the coupling changes at the gluon mass. As the momentum involved in the interaction becomes less than the gluon mass, those gluons are frozen out of interactions so that one enters an effectively conformal domain where the coupling no longer runs. The coupling, it freezes in the infrared. This new type of effective charge is very important because it's process independent and unifies a vast array of observables. It possesses this infrared saturation point, and so we have now a non-perturbative analysis that demonstrates the absence of a Landau pole in QCD. There are no divergences in the infrared. This is because the gluons acquire this mass scale. We know also that asymptotic freedom means that QCD is well defined at ultraviolet momenta in the ultraviolet out here. So now we have a very special quantum field theory. It might be unique. It certainly is unique amongst known four-dimensional quantum field theories in being defined and internally consistent at all momenta, in the ultraviolet, in the infrared. And that means that QCD is not interesting just for us alone, but it might also be the correct paradigm or a very useful paradigm for extending the standard model, for looking at compositeness of what we now think to be elementary particles. The same sort of thing happens in the matter sector. Quarks are parton-like in the ultraviolet, but as the momentum of the quark drops, they acquire a large effective mass. And you can see in this figure, the parton-like quark evolving into the constituent-like quark in the infrared. And this mass scale of 1/3 the proton mass is obviously the sort of scale you need for a constituent quark mass. This work was first discussed by Lane and Politzer in the mid-70s, and since that time, the techniques have been refined. We have refined continuum and lattice analyses so that we can now compute this mass function with quite a good degree of confidence. So this brings us to a question of confinement. And in this picture, it's a dynamical statement. It's not tied up or connected with potentials of any sort because we have light quarks. And light quarks, the retardation effects that you would introduce from light quark degrees of freedom would destroy any concept of a potential. So the picture you have now is that a quark begins to propagate, and that after a length of order sigma, which is typical of this infrared mass scale, the quark starts to fragment, and that goes on ad infinitum until finally a cloud of partons coalesces. And so one has the fragmentation phenomenon as being perhaps the cleanest expression of confinement, this dynamical picture all tied up with these dynamically generated masses that run owing to QCD dynamics. This is the emergence of hadronic mass. Those masses could not exist unless there were a trace anomaly in QCD, unless one quantized the theory, and that led to an anomaly in the divergence of the dilation current. This picture with the masses emerging for the previously massless gluons from the previously massless quark partons is why we have a mass scale for strong interactions that is so different to that of electromagnetism, why the proton mass expresses that scale, and why the pion is nevertheless unnaturally light. It says that no significant mass scale is possible unless one of a similar size is expressed in the dressed propagators of the gluons and quarks. And it follows that the mechanisms that explain the emergence of mass can be exposed by measurements that are sensitive to such dressing. There are many observables that make this possible. I'm just going to sketch a few examples. So let's look a little closer at this enigma of the appearance of mass. I'm illustrating here what a theorist would call the pion's wave function, or in fact the pion's beta salpeter amplitude, this gamma pi. This is analogous to a Schrödinger wave function if a non-relativistic limit were valid. Of course, it's not valid, so we can't get to a Schrödinger wave function in a covariant formalism. But this is the quantum field theory analog. And then there's the dressed quark propagator. This is the one-body problem. This is the two-body problem. And the mass function I drew before is the ratio of B and A here. In chiral limit QCD, so in QCD without the Higgs boson couplings, one can derive a collection of four what you might call Goldberger-Treman relations at the quark level. They are exact, no approximations, and what you see is something of a miracle in QCD, that the one-body problem, the solution for the quark two-point function, almost completely determines the bound state solution in the quark-antiquark scattering channel in the pseudoscalar sector. So the two-body problem is solved almost completely once you know the solution of the one-body problem. That's impossible in quantum mechanics. Those systems are completely distinct in quantum mechanics. It's only because of the character of dynamical chirosymmetry breaking, the emergence of hadronic mass that makes this possible. And so one arrives from this at the most fundamental expression of Goldstone's theorem and dynamical chirosymmetry breaking and the emergence of hadronic mass in the standard model. The one-body problem and the two-body problem are effectively identical. Now, if you go back to Nambu's Nobel Prize winning work, you can find a simple expression of this in his paper. This expression is model independent, it's gauge independent, it's scheme independent, and in fact, it underlies the success of chiral perturbation theory, another effective field theories at low energy. And it says the pion exists if, and only if, mass emerges dynamically. So let's look at this and summarize it. We have a Higgs boson, we turn the coupling of the quarks to that boson off. The pion exists and it's massless. Oops, all right. Beta salpeter satisfies this identity, and that means that the properties of the pion's wave function, is the cleanest expression of an emergent hadronic mass in the standard model. The cleanest way to understand the emergence of mass in the standard model is to study the almost massless pion. In many respects, the light front wave function is the key. You can't talk about probability distributions unless you move to the light front in quantum field theory. And this light front wave function can correlate all the observables. And the emergence of hadronic mass is expressed in every hadron light front wave function. An example here I'm showing is the pion compared to the kaon. They're both broadened by emergent hadronic mass, but you see a shift, a skewing of the kaon relative to the pion. And this is the Higgs modulation of emergent hadronic mass in the standard model. So experiments that are sensitive to differences between these two wave functions are sensitive to EHM, emergent hadronic mass, and also to Higgs modulation of these effects. Excellent examples are the pion and kaon distribution amplitudes and distribution functions. And they're both important because they're two sides of the same coin, and they're accessible via different processes. Therefore, they're independent measurements of much the same thing. And so we have theoretically and empirically a great check on the consistency between our understandings from these sectors. One thing that has occupied people for 40 years or more is the pions valence quark distribution function. This is measured in pi-p Drell-Yan experiments. If I consider a theory in which quarks scatter via vector boson exchange, and that vector boson behaves as 1 over k squared to a power beta at large momenta k squared, then at the hadronic scale, the distribution function for the valence quarks must be 1 minus x to the power 2 beta. So that means that the large x behavior of the quark distribution function is a direct measure of the momentum dependence of the underlying interaction. QCD beta equals 1, so the pion distribution function must be 1 minus x to the power 2 at the hadronic scale. In QCD, we have scaling violations, so the power 2 becomes 2 plus gamma, and gamma is greater than 0. This is the Parton model prediction for the scalar, for the valence quark distribution function of a spin 0 meson at zeta h, the Hadron scale. That scale, of course, is not accessible in experiments. What we have in QCD is improvement of that because of anomalous dimensions. So we have this prediction. At any scale accessible to experiment, the distribution function for the valence quarks in a pion must be 1 minus x to the power beta greater than 2. This is a simple restatement of the following facts in QCD. The Parton model gives scaling and scaling laws. QCD's gluon corrections give you scaling violations. Scaling violations do not alter the integer number, but they increase the value of the power. They certainly can't reduce 2 to 1 or 3 to 2 for the nucleon. In analyses of the nucleon distribution functions, there is good evidence to suggest that the power is 3 plus something. So we ought to expect the power for the pion to be 2 plus something. What's the consequence? That any analysis of Drell-Yan or deep inelastic scattering or a similar experiment which returns a value of beta less than 2 is in conflict with QCD. Another observation is all existing internally consistent calculations preserve this connection between the large k-squared behavior of the exchange and the large x behavior of the distribution function. If the interaction is 1 over k squared to the n, the distribution function is 1 minus x to the power 2n. No existing calculation which has 1 over k squared behavior for the gluon gives you anything other than 1 minus x to the power 2. All internally consistent calculations that preserve the renormalization group properties of QCD give you a value of 2 plus gamma, where gamma is greater than 0. So the controversy is here. If one ignores threshold resummation, that is soft gluon resummation, and this is done in almost all modern phenomenological analyses, despite some work out of Regensburg 10 years ago, then the data analysis will yield a power of 1, a factor of 200% different to what QCD predicts. If we include threshold resummation, as Eicher, Schaefer, and Vogelsang did 10 years ago, then you get a value of 2. And that's what we're trying to solve. Today, we have continuum and lattice predictions for the pointwise behavior of this distribution function. This behavior has been the same in the continuum for 20 years, but the refinements of the techniques have made us more confident. And moreover, new lattice methods are making the pointwise behavior of the distribution function available. And you see with the comparison between the blue curve and the gray curve that both continuum and lattice agree on a power that is about 2.5 at a resolving scale of 5 GeV. The purple data on this curve is that from E615, but I've rescaled it according to the analysis of Eicher, Schaefer, and Vogelsang. So that analysis and lattice and continuum providing the pointwise behavior agree that the power is greater than 2. So now we have its last chance, or finally the chance, where we have JLab at 12 GeV using the Sullivan process, the M2 beamline at CERN, an electron-ion collider, perhaps an electron-ion collider in China, that are able to probe this domain. You don't need to get to 1 here. Between 0.6 and 0.8 would be enough. I'm emphasizing this because Here is the continuum prediction, and here is a commonly spoken about phenomenology of the pion distribution function. That produces a value of 1 minus x to the power 1 because it doesn't include next leading logarithm resummation. So you see a difference between phenomenology and theory now. Let's move on to the glue and the C. There are fits from this collaboration, for example, but there are no predictions, or there weren't until recently. Now you see the continuum predictions for the glue and the C, and you can see that for the glue, on x greater than 0.5, or 0.05, I should say, they're roughly the same. But at small x, they're very different. In terms of the C, the profiles from the continuum prediction and the jam fits are completely different for all x. We need, therefore, to understand not just the valence in the pion, but the glue and the C. Prompt photon J-psi production might be possible to give us this glue connection. The C, we might need to use Drelian data on isoscalar targets. Let's look at the kaon. I said at the beginning that no picture of QCD is complete unless you understand the pion, the kaon, and the proton. So to see this picture in full color, as Paul Reimer might tell us later on, you need to study kaon distribution functions as well. There are no recent phenomenological inferences. In the valence quark sector, we have results from models and a single recent lattice study. But for the kaons, glue, and C distributions, there are no results. The one piece of available empirical information we have is the ratio of UK over U pi measured by Badier et al. In 1980 at CERN. You can see the continuum prediction. The errors are effectively zero here because the corrections to both the kaon and the pion distribution function cancel. And I'm comparing them with a lattice result, which is the most recent one out of the Michigan State University and Hui-Wen Lin. What you see here is something I haven't illustrated. The lattice QCD distribution function for the valence U quark in the kaon is very different to the continuum prediction. But the prediction for the ratio from both studies is very similar. So this ratio is very forgiving of differences in the distribution functions. It is useful, but if one is going to use it to try and constrain or give us information about this ratio or the distributions in the kaon and the pion, one has to get these errors down. It would be better to have results for the pion and kaon separately, not just the ratio. Well, there were no results for the kaon distributions for the glue and C until now. Now we have these predictions for the glue and the C and the kaon. What one sees is that the distribution functions in the kaon for the glue and C are quite similar to those in the pion. And a detailed comparison requires the use of mass-dependent splitting functions. We have to take account of the fact that strange quarks are heavier than U quarks or D quarks. So they're going to emit less glue, and gluons are going to produce less SS bar pairs. This will lead to changes in the glue and C quark distributions in the kaon at large x. And that's what I've illustrated here. These are the absolute values, and what I've shown here are the ratios of the distribution in the kaon over distribution in the pion for the valence, the glue, and the C. And you see that on x greater than 0.2, so in the valence quark domain, you have measurable differences between these distribution functions. J-psi production might give us information on that. The Hadron accelerator landscape is evolving. We expect to have an electron ion collider in the USA operating by 2030. Here in China, we're discussing construction of a similar machine. A white paper will be released in a few weeks. New capabilities are expected at CERN, and JLab is currently operating at 12 GeV. Each of these facilities is giving a very high priority to measuring these three-dimensional images of the hadrons, in effect trying to map the wave functions, the light front wave functions of the hadrons. I'm going to illustrate something. I'm going to use a simple model to do it because it's algebraic, and so I can show you very simple formulae. The qualitative features are real in QCD, but the illustration makes it simple to see what's going on. This is a generalized parton correlation function, at least to GTMDs, GPDs, and TMDs. If I insert n dot gamma, where n's a light vector, into this diagram, I'm going to get the leading twist vector GTMD of the pion. And that's what this formula is in the simple representation. I could do a similar insertion with a different operator and I'd get the tensor GPD for the pion. It's obvious from this formula that the pion's beta saltpeter amplitude appears twice in this GTMD. And that means the strength is determined by the square of the pion beta saltpeter amplitude. Because of this relationship, it says that the strength and the dependence, the momentum dependence, X dependence of this GTMD are fixed, are determined by emergent hadronic mass because of this relationship. So both the shape and the size of every one of the pion's GTMDs are largely determined by the character of emergent hadronic mass. This highlights once again the properties of the nearly massless pion are a really good way of getting into the physics of emergent hadronic mass. Let's look at the form factors that one gets out of these GTMDs. We can get the electromagnetic form factor as the 0th moment of h pi, which is the k-perp integral of F1. Or I can look at the first moment and I can get the mass distribution and the pressure and stress distributions. In this approach, I have used the best available contact interaction work, simple model, but in this picture, I've compared it with available lattice results. One of the things you notice is that the θ2 form factor for the pion, which is the mass distribution, is harder than the electromagnetic distribution, which is harder again than the pressure distribution. Comparing these with the lattice results, which are now more than 10 years old, we need some more results there for objective comparisons. You'll see that qualitatively, the contact interaction or the simple interaction and lattice provide the same types of results. So there is a measure of confidence in these predictions. What's very interesting now is to compute the pressure. And I'm going to compute the pressure in the pion using a bright frame definition. I could, of course, choose to take a light front definition. That wouldn't change very much. The orders of magnitude are still the same. So the numbers are still meaningful one way or the other. And what you see here is something quite striking. Let's focus on the blue curves because they're the most realistic. There are two domains. The small r domain, the quark and the antiquark are trying to push away from each other. The core repulsion, they're trying to break away. And then at about 0.5 Fermi, one enters the confinement domain where the quarks are feeling their attachment to one another. The strong interaction is pulling them back in. So the pressure shows that. Of course, r squared times p must integrate to 0 because this is the bound state. There's something else of interest here. If I compare these numbers, this pressure inside the pion, I see that it's 5 times larger than at the core of the proton. And I can compare this with the core of a neutron star, which is 0.1 GeV per Fermi, with errors because there are many models for the neutron star equation of state. So what you see now is that the pressure at the core of a pion matches that within a neutron star. So this QCD matter at the pion core is roughly the densest material in the universe. And we have it within our grasp here on Earth in pion properties. So that's been a bit of a tour, a rather rapid tour because of the time allotted. So I'm going to wrap up and give you a few little pointers. The first one, LHC has not found the God particle. The Higgs boson is not the origin of mass. It's crucial, of course. It does so much to make the universe we see today possible. But in terms of mass, it produces just a little bit. The Higgs-generated light quark masses explain neither the proton's large mass nor the pion's near masslessness. What we have is the strong interaction sector of the standard model, QCD. That's the key to understanding the origin, existence, and properties of the vast bulk of all known matter. Our task is to explain the origin and distribution of the bulk of visible mass. Our current paradigm is QCD. As I highlighted, because of this emergent hadronic mass, QCD is generating its own infrared cutoffs. It's therefore, very plausibly, a mathematically well-defined quantum field theory, the only one we've ever produced. Consequently, it could be the paradigm we need for going beyond the standard model in terms of compactness for the so-called elementary particles. The challenges are to reveal the content of strong QCD, and finally, to unify it with nuclear physics. So that takes us back to the first talk today. Can we understand, from the perspective I've outlined here, the structure of the deuteron? That's a challenge. We have 10 years, 10, 20 years to do it, perhaps. Progress and insights are being delivered by an amalgam of theory, experiment, and phenomenology. No one approach is capable of solving the problem that the simple Lagrangian of QCD poses. We need every branch of the tools or of the body available to us to make progress. And that's why we're developing a whole array of new facilities. JLab at 12 GeV, the electron ion collider, the new facility at the beamline at CERN with the Compass Amber collaboration, and potentially an electron ion collider in China. This work is the result of a wide-ranging collaboration across the world. I'd just like to show you the collaboration members. There are many more than here, but they have contributed enormously to this work. And I'd like to thank you for your attention, and finally to invite you to join us in the week beginning 30th November, continuing to the 4th of December. We have a teleconference hosted by CERN to discuss more of these issues about the emergence of hadron mass in the strong interaction. So I'll stop there. Thank you for your attention.
Thank you very much, Craig, for a nice presentation and actually good timing. Do we have questions? I see a question from Stefan. Please, Stefan.
Hello, Craig. Thanks a lot for the nice, illuminating talk. I learn each time I hear your talks, I learn something new. This time I learned something about this pressure in the pion, which is look extremely attractive. But I wonder how, what kind of experimental information could be used to compare what you have shown us? What kind of experiment you would like us to provide in order to check your calculations?
Okay, so this is a pion physics problem. If we can measure, develop experiments that are sensitive to the light front wave function of the pion, then I can make constraints on this. So, for example, simply put, the valence quark distribution function in the pion is a constraint that I can use because that GPD H pi has a boundary value being the pion's valence quark distribution function. So that will help us constrain that. I'm not sure that will be accessible in the near future, experiments that are so sensitive to the pointwise behavior of the pion. But we will have other information that we can use to place constraints. This was also an illustration. I wanted to show you just the sort of pressures one is reaching at the core of a hadron. I use the pion calculation because I can do it quickly. I can do the same thing, I meaning the international collaboration, can do the same thing for the proton. And there is the GPMDs or the GPDs are something that people will have access to directly because, as we've seen in the presentations this week, GPDs are being studied in a whole array of experiments. And in the future, with the new facilities, we should get a good handle on the pointwise behavior of these functions. So to answer your question quickly, what you tell us about the pion and K distribution functions, you will see provide constraints and help to test that idea about the pion's pressure. Moreover, direct measurements of the proton's GPD will give us access to similar content inside the proton.
Lost the sound, Craig.
Oh, bloody hell, what?
Okay, now it's, at least I can hear you now.
Okay, did you hear my answer or did I just talk for nothing?
I think, no, we heard. Yes, okay. Only the last sentence was missing. Stefan, do you need any further clarification?
No, thank you very much indeed. Yes, it is very difficult to measure the GPDs of the pion. It's not impossible. Probably in the future, I don't know, but I'm happy with your answer.
Great. Do we have any other questions to Craig? Funso, please. Don't forget to unmute your
pion GPD. As you know, the time-like pion GPD was already measured by the Bell collaboration. So, yeah, GPD for the pion is possible in the time-like region. Space-like region, maybe not so easy. So that's
the idea here, of course, is that if we have the theory that is capable of unifying both time-like and space-like behavior, then we're in much better shape.
Yeah. So at Bell collaboration, they are doing also other So since they are upgraded last year, so they should be in a much better shape in a few years.
Yes, this is very promising perspective.
Yeah.
Okay, thank you again, Craig. We'll come back to this question in the afternoon, addressing it from the perspective of the measurements, let's say from experimental point of view. And I guess here we can thank all the speakers of this second morning session, and we will come back after lunch break at 2 p.m. Am I right, Anna?
Yes, at 2, 20 minutes before for speakers if they want to try to check their connection.
Perfect, thank you.
Thank you. See you later.
See you later.
See you.
Okay, so I think we start because I have 1400 at my laptop. So yeah, welcome to the first afternoon session, and this is a sort of mixed session. We will have two presentations on the hardware and then two talks on physics. So I will let to so all speakers, please, you have 25 minutes and 5 minutes for discussion. And I will let you know when you have 5 minutes left to the end of your presentation. So please let us go ahead and let us start with the first talk by Peter Guysen. It is about the recent advances in detectors. Please, Peter, go ahead.
Okay, thank you very much. I hope you can hear me. So I will after a brief introduction, I will go into new sensors for tracking and vertexing. I will then discuss particle identification and low-level light sensors. Now, the title of my talk, of course, is very broad. So, clearly, for a single talk, it's very hard to cover all interesting developments. So, what you will get is some subsample, also partly reflecting my interests, and hopefully interesting enough for everybody. So first, let us remind ourselves where we are regarding the instrumentation. So on the intensity frontier, Bell 2 has started taking data, and the next upgrade is probably at least 6 years away. LHCb is being upgraded. On the energy frontier side, Atlas and CMS are getting ready for a major upgrade in the next long shutdown, and ALICE is being upgraded now. And on the electron-ion collider side, the preparation is taking place with a very tight schedule. Now, let's go first to the first topic, which is tracking and vertexing. Now, of course, what you need depends very much on what you are doing, where you are. So at lower energies, so like Bell 2, you need precision tracking and minimal multiple scattering, very low multiple scattering. You have few particles in the final state and no event overlap. So it's only background, your event plus background hits that you are detecting. So this is what you can see on the left side. On the right, you see an LHC event with a high density of particles. You require vertex precision with a high density of particles, multiple overlaid interactions within the same event, and high radiation load. So let's go first to Bell 2. Now, here vertexing, as I said before, in vertexing, we are concerned with particles with rather low momenta, so below 4 GeV, so from few hundred MeV up to 4 GeV or so. Therefore, what you do is it has to be a low mass. So you have a low mass thin beryllium beam pipe, and then 6 layers of vertex detector, where the first 2 layers are pixels, depth-based pixels, and then 4 layers of double-sided silicon strip detectors. Now, first, the depth part. Depth is a novel type of silicon pixel detector. As you can see, this certainly fulfills the request of a thin detector. It's only the sensor is only 75 micrometers thick, and all the services are put to the side the sensor. There were many interesting R&D aspects for this sensor type. Low mass modules with self-supporting 75 micrometer thick silicon, which is 0.2% of radiation length. Low power active pixel sensor. There was a development of dedicated readout ASICs of 3 types, and on-module data with on-module data reduction features. And the assembly procedure was, of course, a special issue. And in addition, cooling is required with CO2. The next 4 layers are double-sided silicon strip detectors, and there the chip-on sensor concept was the origami chip-on sensor concept was developed for a good signal or noise with fast readout and moderate material budget. And excellent time resolution was achieved thanks to multiple recorded samples and waveform fitting. And again, CO2 dual phase cooling. So this is a close-up of one of the early events with cosmic rays. This is the full detector. This is now the full vertex detector, 2 layers of pixels and 4 layers of double-sided strip detectors, and finally a close-up into the innermost part. Now, moving to the next detector where vertexing is being upgraded, and that is LHCb. The requirement there is that all front-end out electronics has to be read out at 40 megahertz with an average input of 30 megahertz into a full software trigger. And indicated here are parts that have been upgraded, and as you see, most of the spectrometer is being upgraded right now. Now that we are with vertexing, the vertex detector, the upgraded vertex detector, so-called Velo vertex locator, is composed of 2 parts that then come together around the beam. And what you see on the left is the upgraded, the expected performance of the upgraded Velo in red compared to the current resolution of the detector that they have been using up to a year ago. They're using, for the upgraded detector, they are using innovative cooling scheme with micro channels made of silicon that are I mean, this is of course the same material as the sensors, so has the same thermal expansion, is low material, and it has high thermal efficiency and good cooling power. Now, for the high Lumi LHC, the radiation levels will be, the fluences will be of 2 times 10 to the 16 neutrons, 1 MeV neutrons equivalent per square centimeter. Total ionizing dose 1 gigarad, and pile up to 240 events. So this is really going to look very widely. And what you see here on the right are expected fluences as a function of position in the spectrometer. Now, for this hostile environment, 3 types of interesting detector development has been taking place. 3D detectors for extreme radiation hardness, large area coverage for with depleted CMOS sensors, fully monolithic or hybrid ASICs, and timing detectors, low gain avalanche diode with the possible application of 3D technology. So let's go first to 3D detectors. The advantages are that they have excellent charge collection efficiency or a large fluence range. They have a fast charge collection, which is very promising for timing applications. You need only reduce the full depletion voltage and by that power, and you have freedom to choose electrode configuration ad lib. Now, of course, there are also limitations. Columns are a dead area, but most of the tracks are anyway inclined. There is considerable inter-electron capacitance and therefore noise, particularly if small spacing is desired. The availability on a large scale is not clear, and of course also time scale and cost. Low gain avalanche detectors, LGATs, they are APD-like devices which allow segmentation and high voltage operation close to breakdown. They have been pioneered by RD50 and are getting now more and more attention. And what you see here on the left is a schematic view of such a device. The key properties are that gain is very sensitive to the P+ layer doping and process parameters. Gains up to 100 are achieved, giving an excellent time resolution of 26 picoseconds for thin LGATs. And this is currently the best technology for achieving excellent timing measurements for MIPS. It's expected to be employed at Atlas and CMS for the next upgrade. Limitations, of course, are radiation hardness and regions around the electrodes do not have a gain. So one has to look into improving the fill factor. And finally, depleted CMOS sensors, so a high voltage CMOS process, which allows monolithic detectors. And the first devices produced are showing huge potential in all respects: scalability, cost, and integration. And now key properties are that they have excellent position resolution, but the different substrates are often limited by the vendor. The limitations are radiation hardness, speed is not yet optimal, and you will, let me just remind you that you will hear more about this in the talk, the next talk by Ivan. So let me move to the next topic, which is particle ID. Just to remind you, particle ID is essential because it reduces combinatorial background, as you see here illustrated on both left and right. In one case, it's the combinatorial background is reduced by a factor of 5, and the other, you wouldn't see the signal at all if you wouldn't use the particle ID device. So we start with LHCb. LHCb has two ridge detectors that are covering a huge momentum range between a few GeV up to 100 GeV, and they are employing hybrid photosensors covering a large area of photo detector planes in both ridges. Originally, in order to cover such a large area in momentum, from a few GeV up to 100, you do need more than one radiator, and therefore there were originally 3 radiators set up in 2 ridges. 2 of them were gas, 2 sorts of freons, and aerogel. And what you see on the bottom right is Cherenkov angle as a function of momentum, and you see well how different gases can be used in different radiators can be used in different momentum ranges to separate, for example, pions from kaons. These are the two ridge detectors, one right after the vertex detector and the other one behind the magnet, the dipole magnet of the spectrometer. So both ridges were performing extremely well with excellent agreement with Monte Carlo, and the performance of the two, which is also illustrated by control channels on the right, has been essential for the big success of the LHCb experiment. Now, as already discussed, LHCb is being upgraded, and this also include ridge detectors. The photosensors, these hybrid photon detectors had to be replaced because they had a maximum readout rate of 1 megahertz, and which was integrated into the sensors. So they have been replaced with multi-anode PMTs of two sizes, as you see here, of two granularities, this one and this one here, with Claro chips for the readout. Yeah. And in one of the next long shutdowns, another PID will be added called Torch, which again is based on Cherenkov light. It's a combination between a time of flight and ridge detector. So let's move to PID systems in Bell 2. There are two Cherenkov-based detectors, one in the barrel, this quartz 2.5 meter long quartz bars, and one in the end cap. Now, the part in the end cap uses aerogel as radiator and hybrid avalanche photodetectors as sensors. And what you see here is this radiator plane and the photon detector plane, which is then located in the forward region of the spectrometer. Here we employ an interesting trick to increase the number of photons, which is small as usual in a ridge detector. You have to use a thicker radiator, but if you use a thicker radiator, you get a wider ring, and therefore you get more photons, but the error in measuring Cherenkov angle increases. However, if you choose the two layers with different refractive indices, you get more photons, but the rings, you can make the rings overlap. And this is a kind of focusing radiator. And you see the proof of principle in these two pictures. This focusing configuration is a narrower Cherenkov peak. This, of course, is only possible with aerogel, where you can choose your refractive index ad lib. And this is how the detector looks like: the photosensor plane with 420 HAPDs, and the backside with the electronics. And this is then combined with the aerogel radiator plane into a single unit. The performance is shown here at comparison of data in Monte Carlo Cherenkov angle distribution, and here patterns on the Cherenkov detector plane, or in fact in the Cherenkov space. Comparison of data and Monte Carlo, we see a very good agreement, and also in the performance there is good agreement, but the refinements are underway and further improvements are expected. The other PID device is a time of propagation counter, which is one of these new generation devices inspired by the Dirac counter of the Babar experiment. You use a quartz plate to produce Cherenkov photons, and then you use total reflection to propagate them up to the end of this bar, where you put
5 minutes.
Thank you. Which have to be very fast and have to operate in 1.5 Tesla magnetic field. And of course, you don't get a Cherenkov ring; you get a pattern in space and time, and you of course use likelihood functions, these 2D likelihood functions to calculate the likelihood for pions and kaons. And of course, the important part of one of the important parts of R&D here was the development of photosensors that are fast enough and that do not age. And these are atomic layer deposition microchannel plates. And the same sensor is used in the Dirac-like detectors in Panda experiment, where more than 8,000 channels of MCP PMTs have to operate in 1 Tesla magnetic field with a timing of the order of 100 picoseconds. And here they have used an innovative focusing scheme where you add to the quartz bar, you add lenses for focusing, and you use an expansion bar and photosensors. Photosensors are then attached to this final plate. Finally, PID devices for the electron-ion collider. There are 3 types for each of the regions. One of them is a Dirac-like device that we have seen that is being constructed for Panda. And the other 2 are ridge detectors, one with 2 radiators and one with of a modular type. Let me just very briefly show the modular type. So it uses aerogel, and then instead of a long expansion gap, it uses a Fresnel lens to focus the Cherenkov photons on a sensor plane. And what you see here is the beam test result, where as sensors, silicon PMs were used. The dual radiator ridge uses aerogel and gas, and in beam test, this concept was tested, and what you see here are both the gas and aerogel rings. A very interesting development is actually being carried out in Trieste. The combination of thick gem and micromegas was developed for the COMPASS experiment, where cesium iodide was used as a photosensitive substance. For electron-ion collider, the idea is to increase the number of photons in the far UV, and therefore you have to remove this window here. And cesium iodide might not be robust enough because of humidity and ion bombardment. So they are looking for alternatives, and currently under study is nanodiamond photocathodes. They are interesting, but of course, there's still some way to go. Finally, silicon PMs are a very interesting choice for Cherenkov detectors, but of course, this is not trivial because of dark counts, and this gets worse with irradiation with neutrons. For beam tests, of course, this has been proven to work, and in particular because you can add light collectors to increase the light yield and to increase the signal over noise ratio. But of course, these devices because they are semiconductor devices, they get worse in being irradiated. And this was, for example, a showstopper for using them at Bell 2. Now, for the next generation of reaches, one has to consider cooling of sensors with waveform sampling, readout electronics, and preferably with also some annealing method, which are being studied by several groups.
25 minutes.
Yes, I'm there. So one final slide is, I just want to mention a very interesting development for trigger. The LHCb experiment here to the right will have after the upgrade, a triggerless readout. They will just record everything and analyze everything. And this, I think, is a very interesting concept. Is being picked up also by other experiments. It's probably something that we will see more in the future. So let me summarize. Detectors for particle physics experiments are our discovery tools. The well-designed and well-functioning devices have been essential for our present understanding of elementary particles. And this is a very, very vibrant research area. Large variety of new methods has been developed recently or is under commissioning or early data taking. And new challenges are waiting for us when planning the next generation of experiment. And I'm looking forward to meeting them. Thank you.
Thanks a lot, Peter. Thanks a lot for as well being sharp in time. So we have time for 1 or 2 questions. I don't see raised hands, but I have a question. Do you, in terms of PID, do you know about these techniques which is under development now in US, for example, in Chicago University? This is.
You mean the time of flight?
Yes. Yes.
Yeah. You're probably referring to this large area
exactly.
MCP PMTs, these
yes.
LAPPDs. Yeah. Unfortunately, I didn't have time to mention. Actually, this is one of the sensors that is being considered for the reaches of the electron-ion collider, and so this is also a part of the development there. For example, one could use the LAPPD here at the end of this device, or one could use, of course, the same device here at the end of the as a photo sensor for a Dirk-like focusing Dirk-like device. Mm-hmm. So these are very interesting devices, and actually, this has been the knowledge has been transferred to industry. There is a company called Incom that is actually selling this. We have to see how successful that goes. If the concept is excellent to make MCP PMTs of large area that would be affordable, much cheaper than the present MCP PMTs. But we have to see.
Okay, thanks a lot. Sylvia, I saw your hand raised, but then you lower it. So do you see?
Yes. Peter has already said everything about LAPPDs.
Okay, so I don't see other questions, so we thank Peter again. And we go to the second presentation of the session. This is HV CMOS sensors. Talk will be given by Ivan Peric. Please, Ivan, go ahead.
Hello. I hope you can see my slides.
Yes.
will also start the presentation.
But it is not full screen.
Okay, now. Yeah.
Now it is, yeah.
No, so first of all, thank you for inviting me to present this talk. My talk will be more like academic. So I will first give an overview of CMOS sensors and then present our developments. I think this is fine. This is unfortunately without any overview slides. So the standard technology for pixel sensors so far were hybrid pixel sensors, as we all know, so these hybrid sensors are very successful sector. They are used, for example, in LHC, so experiments like Atlas, CMS. But they have drawbacks, so they are quite expensive. They require bump bonding. The pixel size is limited to the bump bonding pitch, and also the amount of material is high. So therefore, this motivated several groups in past decade or even 20 years to develop CMOS sensors based on standard CMOS processes. So on this slide, you see this standard CMOS structure, so which is also used in, for example, sensors for digital cameras. But this structure has been adopted or modified a little bit to be full sensitive, so with the full area to particles. So the idea is to use epitaxial layer, so of silicon p-type, which is very high resistivity or lowly doped, and then in this way we have a kind of potential minimum. And when a particle penetrates this sensor, electron holes are generated, but they are repelled by this deep P substrate because it is higher doped and the potential energy for electrons is higher. And also it is repelled by the P-well. So it means the electrons, for example, they move by diffusion. And then finally they can get collected by this anvil. So this is the working principle of this CMOS sensors for particles. And they are called MAPs, which means monolithic active pixel sensors. And they were for the first time published in this paper, so in 2001. So this first structure is very good if we require a high spatial resolution and low noise, but it has also some drawbacks, especially it is not very radiation hard, and also the time resolution is not very good. So this is all the result of this charge collection by diffusion, which takes time. Also, another drawback of this original structure was that the electronics, readout electronics in pixel was limited to one type of transistors, which is N-channel transistor, and this limited the complexity of this electronics. So the structure has been developed continuously in the past 20 years. And first improvement was to add this implant here, deep P-well. And in this way, the shield or this PMOS transistor substrate from the sensor. So this allowed more complex readout electronics, which is important if we want, for example, to improve the time resolution of the structure. So, and here I always write the first publication of this structure. Approximately this time, the HV-CMOS structure was also proposed. And here you can see how it looks like. So they are based on the following ideas. First, we use the standard high voltage CMOS bulk process or technology process. So this is a standard technology which is originally developed for automotive or industry applications, or for example, for drivers of flat screens. So not, of course, for sensors, but more for like a generation of high voltage signals. But it means it is commercial approaches. It is available, long-term available. It is relatively cheap. And as you see, this structure uses several implants in this silicon. So, for example, we have the P-well, N-well. This is the standard. And then we have this deep N-well, more or less standard in the semiconductor processes. So high voltage processes, also low voltage processes. So now what is here really new? The new is that this structure, deep N-well, has two roles. So it is a charge collection electrode, so it collects the signal charge, but also at the same time it is the substrate for the electronics. So this twofold role is a bit complication. So it requires several design tricks or innovations that it works well. But it has also advantages. And the first advantage is that we can deplete the substrate using high voltage. Why is this so? Because the region with a high electric field is outside of this electrode, and electronics is inside. So it means electronics will not get damaged by high field. So it is isolated or protected by this deep N-well. And we can use relatively high voltages here. So for example, minus 50, minus 60 volt, but they are also used even up to minus 200 volts. So it means it is possible to deplete quite a deep region of the substrate. And in the sensors that were designed in my group, it is typically 30 micrometers, but it was published also up to 170 micrometers. So depletion was achieved. And so this is really good. So because a large depletion region means a large amplitudes of the signals, the particle penetrates this sensor, then the electrons and holes are very fast, separated by electric field. The electrons are moving to the N-well, and this induces very fast signals. So it means that the structure is capable to provide high time resolution, and also the radiation hardness is good, because if we have, for example, non-ionizing damage of this substrate, this will induce traps. But since the charge collection is very fast, the probability of trapping is not that high. So it means that we manage to collect here the most of the signal. Good. So then several slides illustrate this. It means average MIP signals are at least 500 electrons. Then we have this very fast collection and strong and fast signals. And here there are several good also properties of these sensors. So we use a standard process. So it means these sensors are really not expensive. And second advantage is the sensors can be thin, because typically we have here the noise, which is noise levels which are less than 100 electrons. So it means the sensors work well with depleted regions of 30 microns. And the backside of the substrate is not really relevant for signal generation. So it means the sensors can be thinned to, for example, 50 microns, and they work very fine. Also, the electric field lines are relatively parallel, so it means that we can achieve here very high time resolution. The structure has been so far developed in many processes, not only in one or two. So there are 8 processes we have used, even low voltage processes like 65, for example, nanometer process. Then several foundries like AMS, TSI, what we use now. So and global foundries was used, L Foundry and IHB. Also, the choice of substrate is relatively so easy. So let's say, so even a 10 ohm centimeter substrate is working. Substrates with higher resistivity are also fine, but it is important here to note that when we have higher resistivity, the substrates are also more expensive and difficult to get. So the industry usually uses like 10 ohm substrate or less. So it means if a sensor can work with this substrate, it can be also implemented in several processes. Also, the structure has some drawbacks, which is maybe a bit too technical now. So I will just say that original structure is so that the PMOS transistors are not separated from the sensor electrode, which can cause crosstalk. So it means digital noise. But we so developed here design techniques to cope with this. So one technique is to limit the pixel electronics to amplifier and comparator and place the digital circuits on the periphery of the chip. Now, of course, it is possible to add improvements, like, for example, this deep bevel layer. So, and to isolate the PMOS transistors better from the N-well. So this we use. But all these improvements have the drawback that it works only with a certain foundries, certain producers of chips. So if you have something that is not standard, you first need to negotiate with the factory and so. And if the factory is not offering production anymore, then it's difficult to find a new producer. That's why, so from our experience, it is better to stick to the standard process, which is here. Just 2 more slides about another alternative to the high voltage CMOS, again, the standard map structure. So this structure was also developed in the past decade towards a better time resolution and a better radiation hardness. And also here, the idea was to introduce a high voltage and depletion and to use the charge collection by drift as in HV-CMOS. So, one of the first publications about this was here in 2010. So this is again the standard map structure with a high voltage applied for depletion. But as you see here, is a bit more difficult to achieve full depletion because the distance between the regions that are on different voltages is much shorter. And that's why the breakdown voltage is also much less. So, and then the next step in the development was this process modification in Tau-Jazz process. And so, which you can see here, the idea is to add this end implant, so to make the collection electrode a bit bigger and to, in this way, to make the field more parallel and so to make the structure more like HV-CMOS sensors, but of course this would have drawback of increased detector capacitance And here the trick is now to fully deplete this N region, because if you fully deplete a region, then the electronics does not see the full capacitance of this. So these are the latest sensors of MAPS type. Now I hope I have some still time. I will give an overview of our developments, HV-CMOS. And this slide shows that we have done a lot of test sensors. Basically, we have two lines of development. So we first started with R&D phase. So this was somewhere here in AMS 350 nanometer technology. And then in 2011, we started a long time development for Atlas and also for mu3E experiment. Now for Atlas, we first developed a so-called capacitively coupled hybrid sensor. So it means the HV-CMOS sensor did not contain the electronics, the readout electronics. The readout electronics was actually in the external chip. So it is a kind of a hybrid sensor, but still it didn't use the bumps because we could transmit the signals capacitively. Now from mu3E, from the beginning, the monolithic solution was taken. So it means that the readout parts are on the same chip as the sensor. So for Atlas, we concentrated on radiation hardness, and for mu3 on this monolithic structure, but at some moment in like 2018, we merged both developments here and also adopted a monolithic solution for Atlas. And then also in 2018-17, we changed the foundry from AMS to TSI. And this TSI foundry, which is in United States, is to buy experience very, very good. So they are really fast. They are also not expensive, and the quality of their work is very high. And this change to the new foundry really gave momentum to development. So now we can develop or submit a lot of big sensors very fast. And the latest sensors that we have are really reticle size sensors, 2 by 2 centimeter, Atlas Pix3 and mu Pix10. And this was all done within. Now concerning Atlas, I will show maybe 2 more slides, 3 more. So for Atlas, the structure, as I mentioned, is so that we have a pixel, we have digital parts on the same chip. Pixel electronics is limited to amplifier and comparator, so it doesn't contain digital circuits, which are placed on the periphery. And so this I will not comment much, these 2 slides, so you have impression that it is a digital circuit and it is working the way you have some timestamp signals, so some time base, and when there is a hit of particle, then the time of this hit is stored, time information, and this time information has a certain frequency, for example, 40 megahertz in the case of LHC, so Atlas applications. So some highlights. So for Atlas development, as I told, we first started with these capacitively coupled sensors and concentrated to demonstrate radiation tolerance. And we managed to have radiation, for example, tolerance, or let's say efficiency of 98% at 5 to 10 to 15 neutral equivalent. So fluence, so nil. So non-ionizing damage was investigated here, and also this we achieved on the standard substrate. So it means a standard substrate is really good because it has the property after irradiation with protons, it gets better because we have an effect called acceptor removal, and the resistivity gets higher, and then we get stronger and stronger signals. So another highlight was the first really monolithic sensor with this readout on the same chip, Atlas Pix1, where we also measured very good radiation tolerance. And the last, what I showed for Atlas is this Atlas PIX3 sensor, which is really the full system with the electronics, which in principle could be used in the experiment. So this electronics includes a triggered readout, but also as a debug feature, untriggered readout. Then it has all the extra features like a command decoder, like so special interface and how to say the formatting of the data. The interface is
5 minutes.
5 minutes, good. So in principle, I uploaded the slides, and you can see also the comments that I have, like notes. They are more detailed about this, and some results. So we tested already this sensor. It has really good efficiency, and we will continue the tests in next time. HV-CMOS are also used in Mu3 experiment, and here you see the specification of this detector from Mu3. So it is very low mass structure, so 0.1% of radiation length per layer. HV-CMOS sensors will be thin, so 50 microns. They will be glued on very thin Kapton foils without any other carrier, and the cooling will be by helium flow. Commissioning is planned for 23-24, so in 2 years. So this is the final design for Mu3 experiment, MuPix10. It is a similar chip like Atlas PIX3. Some results also is working nice. We started to test it this year. Now, what I want also to show, HV-CMOS sensors can have also higher time resolution, and as development that shows this is the development in BiCMOS technology of IHP, so where the very fast transistors, HBT, so heterojunction transistors, are used as an amplifier. And this development is mainly done by University of Geneva. And as you see, they managed the time resolution of 50 picoseconds with this chip. Here we have sensor diodes, high voltage CMOS diodes with separated electronics without any avalanche multiplication. So this is very interesting. And as a last slide, I will show that HV-CMOS are also, as Peter also mentioned, they are proposed for the upgrade of LHCb. So this development started last year. And here what is planned is to use the CMOS sensors in the inner part of LHCb tracker upgrade. We also here submitted and now test the first test structures. This is now the last slide. So you see the HV-CMOS are proposed or will be used in many experiments. Good. So with this, I would like to thank you. So, and please, if you have questions, ask.
Thanks a lot, Ivan. Very nice presentation. We have time for questions. For the moment, I don't see raised hands. But if you are talking about, so how reliable this number is, 50 picosecond time resolution?
Well, I think they are really, so I can tell you what is in this structure, let's say, ideal. So the diodes, so as you see, we have here only, I think, 12 diodes. And the electronics is separated from them. So this is, of course, not always so a good solution. So if you have very high area, then the connections between the electronics and the diodes will be too long. So now in a phasor detector, it is so that the detection efficiency will be not really 100%. So some regions near the sensor diodes will be reserved for electronics, and then it will work. But in the, of course, applications where this is not allowed, so we need to cope with this. Also, what is here ideal is this separation. So it is in principle possible also technologically to put amplifier in the sensor diode, like I showed. But this would add a bit more capacitances. Nevertheless, so we continue this development also at KIT, in Heidelberg, in Geneva, and we already have prepared test structures, and so which are, let's say, which have also a larger area or 100% fill factor, and we will soon test it. But so this what was measured here is really according to simulations. So this is to my so what is also maybe to mention that the time walk was compensated. So of course. So how it works here, that the amplitude is measured by the scope, and then the time walk can be corrected. Of course, if you have now a system with 10,000 pixels, it is not possible to connect the scope and so to every pixel. But we are also working on the circuits that can do this on the chip. So this is everything feasible, to my opinion.
Okay, thanks a lot. And I see that Stefan wanted to ask a question. Please, Stefan, go ahead.
Hi, Ivan. Thanks very much. Now, what limit is there a size limit for the production? How big could you make wafers? And what are the developments concerning let's say a readout module, which you can more or less easily connect to the outside world?
Well, the size of the chip is usually limited to 2.1 by 2.2 centimeters. So the good example is this UPix 10. So this is really sorry, I wanted to show this number. Yeah. So the wafer itself is in the diameter 20 centimeters. So this is wafer is also not very expensive. It is 1,200 euro. So now concerning connection to the world is so, for example, the UPix 10 will be connected by so-called tape bonding. So it means it doesn't have really wire bonds. So it is so that the pads for the chip are really large, typically 150 microns. And then the foil can be pressed or connected by, let's say, by pressure without any wire bond. And this makes the structure really so compact and easy to connect. Now concerning signaling, so far we managed with these sensors to have a link speed of about 1.6 gigabit per second, which means that we can transmit information of one particle hit within 25 nanoseconds. So this is the rate, but this is only one link. So we can have many links per chip. For example, on this UPix, we have 4 links. Now, I hope this answers your question, because maybe you wanted also to hear something about this reticle stitching or so.
Yes.
Yeah, this is another question. So far, we don't have much experience with this. We know that, for example, TSI can do this. Also, some other foundries like Foundry, for example, can also do IHB. What was presented for these fast sensors cannot do reticle stitching, but they can have larger reticles. For example, they can have, I think, about 3.5 by 3 centimeter large chips. So this is, yeah.
Okay, so it is possible to make sort of reasonably sized sensors for Atlas or for other experiments.
Yes, this is really, so 2 by 2 centimeter is really easy. So this we measured with Atlas Fix 3, the yield was really good. So it means 85% of the chips worked that we tested. So this is not a problem, but
letters to make sort of letters using stitching, that is, you say it's still
stitching is still, we don't have experience.
Yeah.
So what we test within Atlas is now quad module. So a quad module consists of 4 chips, which can be separately tested. And then they are abutted. So it means they are touching each other. So there is some very small red region, less than 100 micrometers, but they are still 4 different entities.
Okay. So thanks a lot, Ivan. I think we have to stop here, unfortunately. So thanks again for nice presentation, and we change sort of topic. We go from detector techniques back to physics. And the next talk will be given by Paul Reimer on key measurements for the understanding of the emergence of hadron mass. Please, Paul, go ahead.
Okay. Let's see, view full screen. Okay, so I presume you can see my screen. As I said, as Oleg said, I'm going to be talking about experimentally probing the emergence of hadron mass. So basically, I'm going to be talking about how we see the color in this lovely picture. So we're all familiar with the proton. As we know, if you add up the proton's mass from the quarks that is produced by the Higgs mechanism, the U quark is only 2 MeV, the D quark's 4 MeV. Put those together and you get roughly 9 MeV. Down here, that's roughly 1/10 of the mass of the proton. And so it naturally begs one to ask, where does the remainder emerge from? And so there are a number of decompositions of the mass of the proton. There is, for example, I put up here a pie chart of the rest frame decomposition, where you can see that part of it comes from the trace anomaly, some from the gluon energy, some from the quark energy, some from the quark condensate. And there are various different decompositions in different sort of frameworks that you can find for the mass of the proton. But the point is that the Higgs mechanism provides for a very small mass, or a very small fraction of the mass of the proton. But there is one thing with all of these that one needs to consider when you start talking about the decomposition of the mass of a composite object. And that is, in my relativity class, I learned that when you start talking about mass, you end up talking about an invariant mass defined as a 4-vector squared. And when you square a 4-vector, a 4-vector squared is not simply the sum, a 4-vector of a component part of a component object squared is not simply the sum of the 4 vectors of the component squared. Take, for example, a pi 0 that decays. The sum of the squares of the two photons is 0, but you add them together and then square them, and you get the pi0 mass. So one has to be careful when one talks about exactly how you're decomposing this mass in whatever frame you choose to do it in, or however you choose to talk about it. That's just a caveat that I'm making. I have heard an entire talk about various types of decompositions on this, which I am not going to go into. But when we're talking about how to understand the mass of the proton, we have to be aware that there are certain understood norms or understood standards that we're talking about, and we have essentially then given up on this frame invariant definition of mass that we all like. One interesting thing to note in terms of the mass of the proton is in the chiral limit, where the mass of the quarks goes to 0, the trace anomaly shown here, as Craig Roberts frequently points out, gives the mass of the proton entirely to the gluons. That becomes interesting later when we consider it in the context of the pion. So I like to think of the strong force in terms of this picture. It's a lovely picture. It's one of my favorite works of art. But if you consider it in terms of just the Higgs mass, you get something like this. You've wiped out all the color in the picture, and you've sort of killed the resolution. And that's not the beauty of nature. You really want this to see the beauty of nature. Okay, and not only that, but if you look at this picture in detail and enlarge any individual area, there is an incredible amount of beauty and detail in the pixels and the color. So in this little circle, there's this nice couple here, and even in the background of this nice couple here, there's another couple back here, and we want to see all of those pixels together to make up the work of art and see what's going on. So how are we going to do that? So the first thing we need to look at is the proton is a wonderful system. It's nominally 3 valence quarks and a whole lot of QCD, and it somehow comes up with the proton that we know. There's a simpler system out there that we know of called the pion. In a naive estimation, the pion's mass should be roughly 2/3 that of the proton mass if you take constituent quarks. A different naive estimate would say the pion's mass is 0 in the chiral limit as a Goldstone boson. We know it's neither of those. If you look in the chiral limit and look at the trace anomaly, here you get the mass of the pion equal to 0. And so there are no gluons in the chiral limit. So we should explore that. And what we really want to know is how the Higgs mechanism, which does have mass for the quarks, it has about 7, oh my, I put GeV down here for mass. I'm sorry about that. That's 7 MeV of mass of quarks in the pion compared to the 140 GeV of mass. MeV of mass. I'm getting my units confused. Where does that mass come in? And then we really want to compare that with the mass of the kaon. And the reason we want to do that is really the question of this Higgs mechanism versus dynamical chiral symmetry breaking in the pion with the light quarks. What happens to it when you add a heavy quark, where the Higgs mechanism does in fact account for a substantial part of that quark's mass, and hence a substantial part of the at least a more significant part of the mass of the composite object, and how dynamical chiral symmetry breaking and the Higgs mechanism are then rebalanced. And so I'm going to say a lot about measuring the pion's structure to start with in this talk. And then I'm going to go back and say, and we need to do this all over again for the kaon. And I'm very serious about that because if we want to understand the mechanisms of how the Higgs is balanced with dynamical chiral symmetry breaking, we need to understand how the strange quark, the addition of the strange quark, changes the entire picture we get when we look at the comparison of the kaon with the pion. Okay, so the key questions I would love to see answered are, do we understand the trace anomaly? And part of that, is there any glue in the pion? Is there any glue in the kaon? Then do we understand the energy mass distribution of the pion and of the kaon, with the caveats that we have to have some frame-dependent definition for those two objects that I said before. Excuse me. And then the question is, do we understand how these two are different and why they're different? Well, why? Because we've added a strange quark that has a Higgs mass, but do we understand the interplay between those? And then finally, how do we relate this to the mass of the proton? We need a consistent picture of QCD. And so basically, experimentally, we need to know the structure of the pion to kaon ratios in the kaon. And then it would be nice to know, not nice, it's imperative to know all of this from lattice QCD as well. This is not a lattice talk, so yeah, I just lay down a challenge now to those lattice QCD experts listening. Everything I talk about, please try to calculate it as well. And I know you've made good progress on everything so far. Okay, so before I go on, what we generally try to measure as experimentalists are parton distributions. Now, no single experiment, as much as we'd like to say so, measures a particular parton distribution. And as an experimentalist, I'm very guilty on this. For those of you who know me, I have been advertising for about a decade an experiment that I say measures the ratio of anti-D to anti-U quarks in the proton. It doesn't really. It measures a cross-section ratio that is sensitive to that quark ratio. But to actually understand that quark or anti-quark ratio, you need to consider all of the physics of the proton, or in the case we're going to be talking about, all of the physics of the pion and all of the data surrounding the pion, and put it all together in a physics-based model that constrains all of the partons, so that you have the whole picture, and any one individual component, like the experiment I've been talking about for the proton, doesn't give you the whole picture. Having said that, some experiments have more sensitivity, though, than other experiments. So, for example, there's actually a program called PDF Sense, written by some members of the CTEC collaboration, that will allow you to evaluate, before you do an experiment, what the sensitivity of that experiment or those measurements will be to the overall knowledge of the parton, of the general parton, no, general is now an incorrect term, of parton distributions in general to the measurement you have. So you could put in the cross-section ratio measurements and see what their sensitivity is to vary, or what parton distributions would be affected by a change in a certain cross-section or cross-section ratios. So you can then just figure out, where in fact you need to make your measurements. So that helps in telling us where we need more knowledge. The other thing you need to know about parton distributions is we make some assumptions. Some of them are very good assumptions. So for example, the pion, we assume that the number of U quarks, that would be U minus U bar quarks, is equal to 1, and we express it like this. And the total momentum of the pion, that would be the number X times the number of quarks plus the number of anti-quarks plus the number of gluons, sums up to 1. Okay, very simple assumptions, but they are assumptions that we put into the parton distributions, and I'll get back to this one a little bit later. And then in general, although not always, we make some assumption about how we can algebraically express our knowledge of the parton distributions, and sometimes that influences what we see in the end. We try to get rid of that influence by changing our assumptions. There's a notable exception to this, and this is the neural network people who have tried to eliminate all bias from this. And that is a good thing to eliminate. Okay, so what would we like to see measured? Well, there's a question about what can be measured. There are some measurements that have, as I said, nothing determines one thing in particular, but there are some measurements that have better sensitivity to quark distributions, and there are some measurements that have better sensitivity to gluon distributions. So first, sensitivity to quark distributions. There's pionic Drell-Yan. So in pionic Drell-Yan, there's always been, or at least recently being the last 10 to 15 years to show how old I am, there's been this question on what is the shape of the valence distribution of the pion at large X. And in particular, if you express the valence distribution as having a 1 minus x to the beta shape at large X, can we validate what Craig said earlier today, that beta is greater than 2 at large X? That's an experimental question. Craig put it very strongly this morning that theoretically it has to be. So this is a question of, can we validate the theory? This graph on the right here is from an experiment E615 done at Fermilab, where they purported to measure the parton distributions of the pion, the valence parton distributions. And if you look at this, it doesn't really look like a 1 minus x squared distribution there. It looks more linear. This is the data they extracted. But there's a caveat there. That's not what they directly measured. What they directly measured are these points over here, which is the cross-section of pion on nucleon. And then they took that cross-section and they subjected it to a global fit. And their global fit then also had as inputs to it. In their case, it was a leading order fit because computing time was insufficient for next to leading order in the 80s when they were doing this. It had some form that they adopted with a higher order. I think they had a 1 minus something square root of x, etc. terms out here. Was that form actually a form that could fit the data? Was there a motivation for that form? Could you do a better fit with a neural network? So was there sufficient freedom in their form to calculate what was actually measured? Was their model sufficient to actually do this? So they calculated in leading order. One can calculate this in next to leading order. And then one can calculate this with soft gluon resummation, which is a much more time-consuming calculation. And then one has to ask, with this data, how do the C and gluon contributions...
Excuse me, Valery, please switch off your microphone. Valery. Somebody can who is managing the meeting. Can you please switch off the microphone by Valery?
Yes,
Okay, so then the next question is, how do the C and gluon assumptions that they put into this affect the pion? And then how does the proton they collided with it affect the pion? So later fits were done to this that did come up with an actual beta greater than 2. But I want to point out one other thing. If you look at their mass distribution of the J psi, and fit this distribution. I believe this is out of the graduate student's thesis, John Conway's thesis. You get a mass of the J-psi width of about 165 MeV. You look at mass squared is pi x, or x pi times x of the nucleon s. You just do, a rough error estimate on that, and you get the uncertainty in x percentage-wise is 0.1. And just extrapolating that here and plotting maybe some error bands in x on here, I'm not sure you could actually tell from the data whether or not beta is greater than 0.2, less than 0.2, or what it is, regardless of how you have extracted it. Now, they didn't quote an X-pi resolution in the paper or in the thesis, so I don't know. But this is just a question one might want to raise on this data. So what I am saying is, and I'll get to this in a minute, this is data that I want. The second thing that I'm saying is, remember, that's not the only data out there. As I said earlier, you need to do a global fit. So there is additional Brillouin data from both Na10 and Na3. Na3 had both pi plus and pi minus data, which gains you sensitivity to the pion C quarks, and brings a question of how the C of the pion comes about. Does it come solely from glue? Fortunately, a recent fit to this data has been done, including the Na3 and Na10 data in a global fit sense by the JAM collaboration. And here, unfortunately, on a log scale, I couldn't show you all of the data if it weren't on a log scale, are the results of their fit for the E615 and the Na10 and Na3 data compared with the data. On a log scale, they look pretty good. So that's a good point. They do not, however, find that beta is greater than or equal to 2. So that brings up some more questions. Okay, so data that I want. I said I would talk about key measurements. A key measurement that I would like to see is pion-induced Brillouin with pi minus, so that we can measure these valence distributions. On the right-hand side, oh, that's a pi plus graph. Okay, so I thought I had a pi minus graph there. Is what Compass plus or Amber should be able to do in their experiment. On the lower left-hand side is what they should be able to do for a C to valence ratio using both pi plus and pi minus data. The other thing I would like to see is data with sufficient resolution out at high X to answer this question that Craig has posed as to whether, excuse me, as to whether or not it is really 1 minus X to the 2 plus something. It would be nice to put that question to rest with data that we know everything about. Okay, so moving on. Another way we can address the quark sensitivities is pion data with leading hadrons. So the idea there is we don't have a pion target, except we do, because there is, if you take the Sullivan process, where you expand the proton into a proton plus a pion cloud around it and some other nucleon, you have all these pions just floating around your proton, and so you can use them as a target. And you tag the fact that you hit the proton by looking for, in a collider mode, a neutron coming off in basically the direction of the proton, or a proton that has been barely touched by the electron. And so then you have done essentially an electron pion DIS experiment, and you can tell how real that pion was by looking at the neutron or proton and seeing how on shell or off shell it was. So this has been done before. It's been done by Hera. And so here is a plot of some of the Hera data with fits to two of the existing parton distributions at the time compared to their data for the pion. One fits better than the other. But again, the JAM collaboration has come through and redone this data, redone a global fit, including this, as well as the Drell-Yan data in their fit. So this graph was on the previous page. This is simply the leading neutron H1 and Zeus data compared to their fit. Excuse me, my voice is going. So we can redo this at the EIC. When it is built. And now I can say when and not if. I'm very happy to say that. And this shows essentially the kinematics that can be covered and gives you some feel of the uncertainty in log of x pi and minus t at various q-squared values for the EIC. And this will give us a good measurement of x pi down to relatively low q-squared of the structure function of the pion. So that is going to, just like deep inelastic scattering has given us much of the knowledge we have of the parton distributions of the proton, this is going to fill in a lot of the gap on the structure function of the pion. So that then leads to, I see my graphs got stretched out. Okay, that then leads to the structure functions of the pion in terms of the gluon. So there are a number of ways to get to the gluon. Traditionally, the gluon is the hardest, and the way that it is usually reached is not through these methods, but if you look at this sum rule, the gluon is basically attributed to whatever is left over and not taken by the quarks or the antiquarks. That's not a satisfactory way to do it. There is some sensitivity to it from Drell-Yan in next to leading order, from these two diagrams that are stretched off the screen. Sorry about that. But there are two other ways to get to it. Direct photon production and J-psi. Oh my, so somehow in full screen mode, some of my graphs got messed up. So these are supposed to be Feynman diagrams showing
5 minutes.
5 minutes, okay. Showing two competing processes for direct photons. Basically, you're sensitive to gluons. If we look at WA70, which measured this, and SMRS derivation of their fit to their data, they came up with gluons holding 1/3 to 40% of the momentum of the pion. And that's pretty much in direct contradiction to this chiral trace limit where the gluons hold no momentum of the pion. So this is then a really interesting measurement to make. If you look at the JAM analysis of the pion gluon content, they find that it holds sort of roughly 1/3. Again, much, much more than you would expect from this chiral trace anomaly. So in this plot here, the C holds sort of like 15, 18%. The gluons hold around 30%, and then the valence hold 55, 60, 55% of the C. So we can do this again at Compass. And so this is a measurement I'd like to see at Compass. Shown here, I actually clipped out the plots for the kaon and not the pion, which is fine. But they cover a nice kinematic range. The only drawback is they have to fight large backgrounds coming from minimum bias photons to get the direct photon background, to get the direct photon signal out of it. Another way to get the gluon signal is looking at J-psi production, which generally involves a gluon in either the pion beam or the target. The problem there is you need to understand the way to get rid of or understand the excess color in the production model, because all of these generally come from a fusion into a gluon that produces the charm pair, and the charm pair is colored. But this is, again, something that can be done at Compass. So we're now able to see some of the color in the lovely plot, but we can't see it all. And the reason we can't see everything is because we don't really know how to balance out the effect of the Higgs mechanism with what we have just measured in basically the Goldstone boson, the pion. And so I outlined some measurements I would like to see at COMPAS, direct photons in Drell-Yan, at the EIC through the Sullivan process, and form factor measurements of the pion. Now I'd like to see all of those measurements repeated for the kaon. So the Sullivan process for the kaon, and all of those COMPAS measurements repeated for the kaon, so that I can fill in the rest of the color in this experiment. So in particular, it would be nice to see the ratio of U quarks in the kaon to U quarks in the pion. Shown in the left is an Na3 plot from a long time ago of the yield on kaons, or yield on pions to the yield on kaons. A plea for anybody now who might have been around during this plot, during this paper. I can find the plot of this data published in Physlet B, and I can find a thesis. I think I found a thesis with this plot, but I cannot actually find the numbers short of digitizing the numbers off of this plot. So if anybody has those, I would appreciate it. Anyway, aside from that, you can look at these data and make predictions based on beta-saltpeter equations for what these ratios should be if our understanding of QCD is correct. So that would be a nice test. And then you can come to COMPAS and make these measurements. And this is a prediction for the sensitivity which COMPAS might have from their letter of intent. So again, I basically want to see these measurements done over again that I said earlier, except with kaons. Also, here are possible ratio measurements from COMPAS of the ratio of sensitivities of the C to the valence distributions at various beam energies. So I'd like to see that.
Speed up.
Yep. Okay, so my conclusion is basically I'm asking not how does mass emerge, but how does a big picture emerge from these tiny dots of color? And what experiments would I like to see done? Here's a list of them. The key thing is I want the list for pions repeated for kaons. The pion measurements are not enough. And then you need to do a global analysis for a consistency check. And so thank you, Oleg, for inviting me. I hope to see you next time in Trieste or wherever this is held next, rather than from my living room. But thank you.
Thanks a lot, Paul. So we have two hands raised. So please, Igor, go ahead with your question.
Okay, and thank you very much, Paul, for the nice overview. I have one naive question addressed to probably your page 2.
Page 2, okay. Yes.
Okay, and there is an interesting distribution in the center of this page, which said that gluon distribution has gluon contribution has 35%. As far as I know, and Harzeev proposed that gluon contamination has 80% for in the proton mass.
So,
do you have any comments?
So there are a number of different ways to break this down. And so as I was making this slide up, I thought about putting more than one way down. So there's this decomposition, there's another rest frame decomposition, there's the G decomposition. And once I started looking into all of those decompositions, I decided that it wasn't the goal of my talk to get into that. And so I just decided to point out that it's not quite clear what any of these decompositions mean if you're talking about mass, because the only invariant that I know of would be the sum, would be the entire thing. So yeah, there are different decompositions. So I just took one and I footnoted it here as to where I got it.
Okay, thanks.
Mm-hmm.
And we have another question by Christian.
Yeah. Yes, my question or comment goes in the same direction as Igor's. So you talked about the gluon PDF in the pion and the nucleon, but the PDF, the parton density, captures only part of the gluonic fields in the hadron in the rest frame, namely that part which projects on transverse gluons, physical gluons with transverse polarization when you boost it to infinitum. There can be other gluon fields that project on longitudinal polarization states, or even like Coulomb type fields, and they can happily contribute to the mass and the in the rest frame, but you don't see them in the partonic content. And in the language of QCD operators, those are in higher twist operators, like the trace anomaly is one example of that. And in the language of like light front quantization, those are in the so-called zero modes, the modes of the fields that don't move along with the fast-moving hadron, but that kind of remain behind and like vacuum fluctuations. And so I agree with everything you said about the gluon density in the pion, that it's interesting, but it's missing. It's not the totality of relevant glue for the hadron mass. And in particular, you made one statement that the jam result for the gluon density in the pion is inconsistent with the trace anomaly. I think there you're just equating a twist 2 with a twist 4.
I accept the correction. Yes.
Not adequate, really.
Yes, you are right.
So thanks a lot, Paul, again for nice presentation. So we have to move on. So next speaker is Jan Friedrich, and he will tell us about the overview of the proton radius measurements. Please, Jan, share your slides, and I will let you know when you have 5 minutes to the end of your presentation.
Okay, hello, I'm sharing my screen and go to full screen. Not yet. So here we are. So I give a talk about the proton radius and an overview of measurements of it. And being the first of the few talks which follow on it, let me start with introducing the physics case and some remarks on the historic and theory background to hopefully highlight why there is still today such a vast interest in clarifying this case. So when has the extension of the proton been brought up as a serious scientific case? It was linked, in fact, to the discovery of the pions in the late 1940s. And they were established soon after as the strong interacting particles, and giving rise possibly to higher order diagrams as shown here. And those involve a pion loop. And now the speculation about a corresponding extension of the charge distribution of the proton was done by Marshall Rosenbluth. And you see here in this paper from 1950, so this is now 70 years ago, he proposed that doing electron scattering at low relativistic energies below 50 MeV, the experiment could provide a valuable check of QED, and at higher energies, it should yield data on the nature of the meson cloud of the proton. So having this picture in mind, he was working out, in fact, we all know this, the formalism to describe the respective form factors. They have been measured then soon after. The first experiments were set up, and the canonical first value was 0.8 femtometers, published or produced and published by Robert Hofstetter, and this monumental review from 1956 is recommended to everybody who gets into the subject. Just two remarks from it. First of all, the introduction of this quantity of the radius linked to the Taylor expansion of the respective form factor, and at small values of momentum transfer Q, the first non-trivial element in the Taylor expansion in Q square is related to the extension, and in fact, by definition, called the mean square radius of the object that you're scattering of. Or in turn, the radius is given by the slope of the form factor at small values of Q square. And second remark of this review from the experimental side, so you have to measure a cross-section which is steeply falling with the increasing momentum transfer or with higher scattering angles. And so you have to keep track of all your backgrounds that you possibly have. And here Hofstetter describes the low background was achieved by this setup, which is common to later apparatuses which have been used later that we will also see. And you see here a 180-degree spectrometer placed on top then of this target cell. Here's the incoming beam axis, and you can rotate this spectrometer to different scattering angles. And by this you could measure then also extremely small count rates with low background conditions. Okay, so how did the story go on? In still the 50s, dispersion relations have been worked out for strong interactions also, so including possible resonance contributions and how the analytic shape or analytic form of these form factors may be constrained. And based on this, in 1960, there was a vector pion-pion system postulated with quantum numbers spin parity 1-, to explain this proton radius that have been seen and been not quite interpretable in terms of such a pion cloud, but rather with vector mesons, which couple more directly, obviously, to or fluctuate into the virtual photon. They got the mass of the vector meson a little bit off because the proton radius was not correct, and also because other vector mesons, which we know nowadays to exist, were not taken into account. And but a year later, the rho resonance was then in fact found. Hofstetter, about 10 years later, measured at higher q-square and found the rough so-called dipole form factor shape that dominates, in fact, to highest values of q-square. And then the measurements of the electron scatterings were refined. Again, about 10 years later, the experimental data were giving a rather large radius of 0.88 femtometers. And at the same time, the dispersion relations FITS delivered values which were in discrepancy. So this is the origin, in fact, where the first discrepancy around the proton radius also was discussed. 1980, the first larger set at low q-square at Mainz was produced, and the radius was a little bit larger, a little bit slower to 0.862, measured on a hydrogen gas target at higher pressure. And still, the updated dispersion relations FITS was favoring a smaller value, or is still favoring. So there's further refinements to this, but basically what has to be said about the proton radius remains the same message from this theory background. And then in 2010, two very relevant impacts from the experiment came. The second larger set of low q-square data were taken at MAMI, and the proton radius, the extracted proton radius, got back to the 0.88 in this analysis by Bernauer and colleagues. And at the same time, the atomic spectroscopy was refined and delivered a very high precision value using bound muons in hydrogen, so for exotic atoms. And this analysis delivered the value 0.841, with the uncertainty even only in the last digit, so a very precise measurement. And in fact, in line, so if you would have let you guide by what theory expects, then you would have directly looked around this value. But obviously, now there's also a discrepancy at the experimental value. And this triggered then from 2010 on many papers on the fitting procedures, on systematic effects, and trying to resolve what is behind this discrepancy. So let's have a look again at the experimental method of these two different values. So the Mainz measurement of 2010 was done here at this 3 spectrometer setup, a somewhat enlarged version of the original Hofstetter setup with spectrometers that you can rotate around the target. And you see here that many data, many cross-section points, about 1400 have been produced at different energies and different scattering angles. And by this, the Rosenblum separation could be done on a high precision level. And then the slope at 0 was extracted and delivered this value 0.88. On the other hand, here you see this transition that is measured in the muonic hydrogen atom by the Kramer collaboration, and we have a dedicated talk by Randolph later, so I will keep short on this here now and focus on the scattering experiments, where there's also a lot to say about. So, apart from the MAMI data that we have just seen, there started a big experiment at Jefferson Lab called PRAD.
with electrons at somewhat higher energy, 1 and 2 GeV about. And the recent publication of the results is in line with a smaller value of the proton radius. It tends even to a value smaller than 0.84. And there's also a detector upgrade planned, and we have a dedicated talk by Ashad later on this. At MAMI, there are 2 more experiments in preparation on this, so I think I cannot explain all of them in detail. Here, just give an overview. The same is true for the MAGIC MESA at a new energy recovering superconducting accelerator being set up at Mainz for low energy or lower energy electrons, and be able to redo the Rosenbluth separation in this regime. And then there is an experiment prepared at PSI called MUSE, and this uses muons, electrons, and also their charge partners in the same energy regime, so low energy regime, to compare electron and muon scattering, and data taking has started. We have a dedicated talk also on this in the following. I have included in this list also the Olympus experiment, which has delivered data already and is planning to go on. It is not directly related to the proton radius measurement, but they measure with a high precision the ratio of electron and positron cross-sections at low momentum transfer. And with this, they systematically can investigate the contribution of 2-photon exchange, which may play a relevant role in solving the riddle. Last not least, I will obviously tell a little bit more about this. There is the proposal and the preparations of the Compass plus Amber experiment with muons at high energies, 100 GeV. And these should deliver high precision data on high energy elastic muon proton scattering. And as we will see in the following, has quite different systematics compared to the other approaches. So let's have a look at the kinematic ranges of these different experiments. This plot here is inspired by what the MUSE proposal has used to display their different kinematic ranges. It's just extended here to lower scattering angles, respectively, for higher beam energies, and made in a logarithmic manner in order to get all experiments included. So this is the plot of the lepton scattering angle versus the momentum transfer that you achieve on a proton target. And you see here for different beam energies, this is the line for 100 GeV that you have in logarithmic scale, linear relation between Q square and the scattering angle. This is the line for 50 GeV. Here are the lines for the PRAD experiment at 2 and or 2.2 and 1.1 GeV, and then 300 MeV down to below 100 MeV, the different kinematic settings for the MUSE experiment. And what you see here in these horizontal lines are those of a constant relative contribution CE of the electric form factor GE. And since it is practically constant over the kinematic range at a larger energy, you cannot do in these ranges a Rosenbluth separation, because this depends on a different ratio of GE and GM. And if you have no lever arm, then you only can assume a certain magnetic contribution and correct for it. However, you see that at small q square, this contribution is very small, 99% here at the lower values, contribution from GE. And so with a very modest precision on GM, you can make a good extraction of the electric charge radius. And well, you see here at μ's, there is differences due to the lepton mass. So this is electrons, this is muons, only at larger scattering angles or smaller energy. And this plays only a role for μ's. So μ's has to use a different theoretical model for interpreting the muon and electron scattering. Okay, now let's compare the results which exists for PRAD already and the previous MINDS data. You see here the low Q square data from MINDS in red with various models that I don't go now too much into detail. They are trying to accommodate the slope at 0, so namely the radius, but you see directly from the plot that these two lower curves corresponding to the MINDS canonical value of 0.88 is clearly favored by the MINDS data. And you see here that on the mere cross-section level, the PRAD data contradict the MINDS measurement. So at a higher Q square, you see is like a 5 sigma deviation between these data sets. Obviously, they run into this common point where they are normalized to at 0 momentum transfer at Q square equals 0. But due to this evolution, you get the vastly two different slopes or different values for the proton radius. And below here in green, you see the uncertainties for the Compass plus amber measurement for a program of 200 days of beam, where we can then reach a precision on the proton radius below 1 femtometer if you translate just the slope that you get by such error bars to a radius value. For μ's, just to also display their error estimates, you see here that for the red data points, which are for the muons, they cover a larger range in Q square. However, with smaller precision than the compass measurement can deliver, especially at smaller values of Q square. In gray, you have the electron data, which have also quite small uncertainties. And two other measurements here, the MINDS measurements and an ultra-low Q square measurement proposal, where only the Q square ranges are shown.
Jan, you have 5 minutes.
Okay. So here you see the different results that have been produced by spectroscopy, by atomic spectroscopy and scattering. And you see, in fact, two groups evolving, one at the lower value scenario and one at the higher, here the uncertainty of the amber measurement. Here the evolution of the form factors, the electric form factor and the magnetic form factor. And here the error band by which you would constrain the form factor evolution at lower Q square by this Compass plus amber measurement. Let's have a short look on this experiment. It is a extension kind of the compass spectrometer with a special target setup with a high pressure active time projection chamber as the core part. And we put silicon and sci-fi high precision detectors up and downstream of this TPC. And then we use the inner tracking and the calorimetry of the compass spectrometer. And this physics program had been proposed here and the given references, and recently has been recommended by the CERN SPSC in for being done at CERN, and we are setting up the respective collaboration now. This is how the inner life of this TPC looks like. So there is the drift fields with 50 kilovolts in a 20 bar hydrogen gas, and the diameter 600 millimeter, and this allows for reconstructing then recoils from 500 keV up to 20 MeV and covering the shown Q-square range. For this, we have to use two momentum transfer, two pressure settings. So the low Q-square data we take at 4 bars, and the high Q-square data then at 20 bars with some overlap between the two kinematic regions in order to be able to connect the one data set to the other. And then depending on whether we leave the Taylor expansion or the free parameters in the fit free to the R to the 4 or R to the 6 term, we get a statistical precision of 1.6 or even 0.7%. These fitting procedures and further theory input that you may do to the data is subject by itself, and we have the next talk by Christian will cover this. For technological developments, I just want to highlight one aspect of it. So we also go for a triggerless data acquisition system. We have heard today about for LHCb about very similar plans. So the idea is to let the front ends of the detectors deliver their data continuously to high capacity front-end electronics, which can concentrate these data and then establish a trigger logic on a higher level. And the data rate capability first will be 2 gigabytes per second and increase to 10 gigabytes per second. And the key part is the IFTDC card. And technically this works with the so-called images or time slices, which are adapted to the speed of the detector. So for slow and fast detectors, you make different length of these images that you, where you group your data in. One aspect in order to compare to other experiments is the appearance of higher order effects, namely, for instance, Bremsstrahlung for lepton scattering, which is real photon emission, which goes in the direction, is peaked in the lepton direction. And here, just to give the numbers for our case, for 100 GeV muon beam, the emission probability for photons between 50 MeV and 5 GeV is about 5 times 10 to the minus 4. So for our data set, we will have about 38,000 radiative events. And we can observe them under very forward angles in the electromagnetic calorimetry. So the picture we should get should look like this. This is kind of a front view of where the photons should end up in the calorimeter. At 0, 0 is the direction of the incoming beam. And here's shown only for muons which have scattered by 14 milliradians. So here, and you see the peaking approximation at work, so high intensity around the muon direction, but also here already interference between the two, which gives, in fact, a large impact on how this looks like. If you compare the radiative effects for electron and muon scattering, the main message is that for electrons, you have like 15 to 20% typically radiative corrections if you constrain yourself to elastic kinematics, which you should do, in fact. And this compares to about 1.5% for muons. And the important thing here is that here you see for electrons on this logarithmic scale that this correction changes over the relevant regime from 10 to the minus 3 to 10 to the minus 2 GeV squared by several percent. And so it is of utmost importance to make this correction correctly, while for muons in this same regime, this effect is below 1%.
Yeah, I'm sorry to interrupt you.
Okay, so I come to my summary. Is my time really over? Not really, huh?
Yes, because
I'm talking 24 minutes.
No.
Okay.
You have started at 37. Okay, please go ahead.
Okay. Anyway, I'm done anyway. So I come to my summary. So there's a large variety of experiments on both sides, atomic spectroscopy and lepton scattering, ongoing and foreseen. So we will hear in the following about much of it. And there is an increasing evidence for the small scale, small radius scenario. Here you see a compilation of the recent developments by Jan Bernauer, which would be in line with the established theory expectation. But certainly then remains a question, what about the earlier electron scattering data? Has anything gone wrong there in the data taken or in the analysis? And if yes, what? And this is quite important to resolve, for instance, with this muon scattering, because these scattering experiments do not focus only on the slowest Q square and clarify what is possibly wrong with the proton radius or what the real value is, but about the full functional dependence of the electric and magnetic form factors of the proton, which we need in the end to understand the full physics behind. And the riddle may not be solved. What if the proton looks completely different from what we imagine? Expect the unexpected, as I think is the lesson from this weird year 2020 in general. Okay, and by this I close. Thank you.
Thanks a lot, Jan, for a very nice talk. We still have, we are a bit late, but I guess we still have a room for questions. So please, Randolph.
Yes, thank you very much, Jan, for this wonderful talk. And I'm certainly looking forward to all these exciting new measurements. The muon scattering is really high up on my expectation list. I have a somewhat dumb question on slide 8, where you showed the different form factors. And I don't understand, and maybe I should ask Ashot, but you could probably explain it better, this one. Why is the P-rad fit at 0.84 femtometer not the same as the Mainz fit forced 0.84 femtometer? So the blue line is not the same as the green dashed line. Shouldn't that be the same?
They are the same in terms of how they end up at 1. Yeah, you see that this green curve and also this dash dotted they make quite some change in the slope in the very last on the very last meter or femtometer here. And in fact, it is here where they have a very similar slope, while the distinction comes from that these more smooth curves go in like this here. And clearly, one could ask the question whether there is some weird behavior of the form factor in the very beginning, but theoreticians tell you that it's simply not possible to have such a huge curvature in the form factor over the very first 10 to the minus 3 GeV squared. This would correspond to a charge distribution which has some very high moments or some far out, in a weird way, far outlying charge. Not impossible for sure, but very exotic.
Thanks.
Thank you, Jan. I don't see other questions, so we thank all four speakers.
Yes.
Sorry? Okay, please, go ahead, Ashot here.
Because there was a address to me. Most likely, the value of radius are same here, but for factor is different. Ours is a rational 1, 1. I have to check if in this plot, what's the minus one. Second point, actually it is a little, we have to be a little careful to say that PIRAD normalized for factor to Q square 0 to 1. We didn't. And that's a big difference between our experiment and other. But there are some arguments that during iteration process, we use that slightly, but it's not at least in first order like other electron scattering experiment in which they force to be for factor to be Q square 1. That's a big difference. And yes, that could be one discussion point between these differences because you're basically forcing your data at a level arm level.
Yeah, the normalization of the absolute cross-section measurement is indeed one of the very important points to address with Mainz measurement, and it's a strong point that for PIRAD, you measure directly without a further correction or without allowing correction factors there. You say you have your iterative process, which may implicitly then introduce it, but it's not made in this bold way of giving the normalization free.
In other words, it is not in fitting procedure that we are forcing Q squared to be at 0 for factor 1. It's not in fitting procedure. And that's big difference.
Okay.
So thanks a lot for this. Again, for this presentation, all four speakers, we thank you all for the nice talks. With this, we are finishing our third session for today, and I would like to ask organizers to tell at which time we...
Yeah, before running away to grab the coffee is screenshot time. So please stop sharing, Jan, and I ask everybody to...
I didn't have my camera on.
Yeah, I know, but when you start talking, we can ask, oh, Patricia, you solve your problems. Good. So...
Did I stop? No?
Okay. 4:25.
Say it again, please, Anna.
We will start again at 4:25.
Okay.
So 5 minutes later.
Silvia, free your camera.
Are we supposed to stay in front of the screen in the coffee break? I find that a bit strange.
No, we are just... Gerard, you're always funny, I know. We just want to take a screenshot, which is an instant of your life, and then you can run and grab your coffee. No, Jan, don't stop sharing.
I don't get rid of this window which tells me to share it.
No, go up, stop the sharing, and leave everybody take the coffee after we. Okay, so wait a moment. Sorry. Okay. Now 1 moment, please, that I drop the screenshot. Okay, now let me see if there is a second window. Screenshot also the second window. Gerard, you switch off your camera and run away, so you are now in the second window too. Good.
But why you prepare, may I comment? Now I understand why Jan didn't have the camera on, because there is something new. He has a bird.
I have a bird?
This was not expected.
A beard.
Yes.
A beard. Okay. I don't have a beard. No. I just didn't shave. That's a difference.
No, sorry, it was a joke.
Patients we all have.
Everybody's free to go and grab. Sergey, you're late. Stay there. I will take the. No, leave it. I will take the screenshot of you once.
Not switch on the camera. I have to think.
Okay, good. Third screenshot, and now we have also Sergey appearing. Thanks to everybody.
We can stop the camera again. Right?
Yes, you can.
Of this workshop. The first talk is on the precise determination of a proton magnetic radius from electron scattering data by Christian. Christian, whenever you're ready, please start. I will give you a reminder 5 minutes before the end.
Yes. So, do you see my slides in full screen?
I see your slide in full screen and I can hear you very well.
Okay. Very good. So good morning, good afternoon. This presentation will be about a precise determination of the proton's magnetic radius from electron scattering data. This is recent work done in collaboration with José Manuel Alarcón from the University of Alcalá and Doug Higginbotham at Jefferson Lab. So we performed a radius extraction using a theory-based method that we call dispersively improved chiral effective field theory. So very briefly, this method combines dispersion theory, meaning analyticity, sum rules, and chiral effective field theory, meaning dynamics, controlled accuracy. It correlates the value of the radii with the form factor behavior at finite q square up to about 1 GeV square. And in this way, it enables a reliable determination of the magnetic radius. So the theoretical method is developed in these articles here, and the recent radius extraction is the subject of this one article highlighted here. So let's start with a brief motivation regarding the role of analyticity in proton radius extraction. And Jan really gave a very nice introduction to the overall problem. So the challenges in proton radius extraction, where we aim to extract the derivative of the form factor at q square equal to 0 from the electron scattering data at some finite q square. And the traditional way to go about this is by some kind of extrapolation to q square going to 0 of a fit to the data. And this raises the question of, in the case of, say, flexible or higher order fits like polynomial stability of the fit, or in the case of some more simple functional forms, the problem functional bias. And this question was discussed really very extensively in the literature, and I'm not going to comment on that anymore. These problems are especially severe in the case of the magnetic radius, because we know that the contribution of the magnetic form factor to the elastic EP cross-section goes like tau over epsilon, where tau is q square over 4m square, and as such, it vanishes for q square going to 0. So, now, the analyticity of the form factor actually plays a crucial role in this. So as we know, the form factors are analytic functions of the invariant momentum transfer T, which is defined as minus q square. They have singularities at positive T along the real axis, which come from processes in which the electromagnetic current communicates with the nucleon through a hadronic exchange in the T channel. And the position of these singularities are known, the strength is roughly known, and this fact really correlates the functional behavior of the form factor at finite q square with the derivative at q square equal to 0. It's a very powerful correlation. Among other things, it's able to predict the size of the higher derivatives. Analyticity also gives us global properties such as sum rules. We can, for example, relate the form factor, the radius to a certain integral over these singularities. And we want to use these properties in radius extraction. And of course, we were not the first to do so. These, as Jan has explained, these methods have been around for at least 60 years. But we implemented them in a new way, which I wanted to describe now. So this method is called dispersively improved chiral effective field theory. We're using the standard dispersive representation of the form factor, where the form factor is written as an integral over the discontinuity or imaginary part on the cut in the time-like region. This is called the spectral function. This representation expresses the full analytic structure of the form factor. And the spectral function, it lives in as was said earlier, it results from hadronic exchanges between the electromagnetic current and the nucleon, but these exchanges occur in a region below the NN bar annihilation threshold, so where the time-like form factor cannot be measured directly, and so as such, this discontinuity in the spectral function has to be constructed theoretically. Now, the most important part of the spectral function for our purposes is the lowest mass part, which is the 2-pion cut in the isovector form factor, so where the current communicates with the hadron through exchange of a 2-pion system. And the spectral function in this region can be constructed using a very nice and an old method called elastic unitarity, where the discontinuity of the form factor can be expressed as the product of two amplitudes, the amplitude for the current to convert to the pi-pi system. This is the pion time-like form factor. And for the pi-pi system to couple to the nucleon. This is the partial wave amplitude of pi-pi NN scattering. And now both these amplitudes, the pion form factor and the partial wave amplitude gamma, have the full information about pi-pi rescattering and the rho meson resonance in the T channel. And in fact, they are exactly entangled by this unitarity relation through Watson's theorem. Now, in order to evaluate this relation, we factorize it in a form such that the pi-pi rescattering effects occur only in one factor and the other is free of them. And this is a very nice method. It's called the N over D method. And so we write this unitarity relation in the following form, that we write it as the ratio of gamma over f pi times f pi modulus square. Now this ratio gamma over f pi, this function is free of pi-pi rescattering by virtue of Watson's theorem. And as such, it plays the role really of the coupling of the pi-pi system to the nucleon. And that function can be computed in chiral effective field theory very reliably with good convergence, because it is free of pi-pi rescattering effects. And the other factor then is the modulus of f pi square. That can be taken directly from the E plus E minus annihilation data, where it's measured very accurately. So in this way, we have organized the elastic unitarity relation in a way that we have one factor that we compute, the pion coupling to the nucleon, and one factor we take from data, the pion time-like form factor. Presently, this is implemented at leading order, next to leading order, and partial next to leading order. So in this way, we can construct the spectral function of the nucleon form factors in the pi-pi region, as indicated here. Now, in order to complete the calculation, we also need the spectral function in the high mass region. And fortunately, as long as we're interested in the radius or in low Q-square form factor, we can get by with a kind of summary description of this high mass region by an effective pole. This is fully sufficient, and we have quantified the uncertainty and actually included that in the uncertainty of the radius extraction. Now, to fix the parameters of the chiral EFT calculation and of the high mass pole, we use the sum rules of dispersion theory, which are listed here, which express the form factor and the derivative, meaning the charges and the radii, in terms of certain integrals over the spectral function. And in this way, we can, in particular, express the low energy constants of the chiral EFT calculation in the pi-pi continuum in terms of the nucleon radii. And as you see in this way, the nucleon radii appear directly as parameters in the spectral function, and as such control the behavior of the spectral function and of the form factor. And this is different from traditional dispersion analysis, where the pi-pi spectral function is taken as a fixed input following the classic extraction by Höhler in the 70s. So here is our results for the spectral function. So the red bands are our spectral functions in the pi-pi region as extracted using the method I described, and they're compared to the orange line here, which is the result of Roy-Steiner equations of Hofer-Richter, and you see that we have very good agreement between the two calculations. And the band here in the spectral function corresponds to the PDG variation of the radii. And in this way, you see how an uncertainty in the radius translates into an uncertainty in the spectral function, and as such in the full form factor. Now, with these spectral functions, we then evaluate the form factors using the dispersion integral. Here it's written for the electric and magnetic form factors. And as we said, these spectral functions depend on the radii as parameters. And so what we obtain in this way is really a family of form factors depending on the radii, where each member of the family respects analyticity and the sum rules. Each member even has an intrinsic theoretical uncertainty coming from the high mass pole in the spectral function. And in this way, we have achieved what we described earlier. We have correlated the radius with the finite Q-square behavior of the form factor. And as you can see, this correlation is really provided by analyticity, and we can use it for radius extraction. So each presumed value of the radius selects one member of this family which has a definite high Q-square behavior. So now we have performed an extraction of both the magnetic and the electric radius using this technique. We use the DI chiral EFT parameterization for GE and GM with the electric and magnetic proton radius as parameters. We fit the Mainz cross-section data, which extend over the energy and Q-square region indicated here, as described in Jan's talk. We've done a full fit to the original cross-sections with floating normalizations. We have also fitted the reanalyzed cross-section data of Lee, Arrington, and Hill that have who have recalculated the uncertainties using the actual distribution of the data as opposed to, say, assumptions. The two fits give the same radii, but the fit to the reanalyzed data has a lower chi-square because of the recalculated uncertainties. Now, a few comments about the impact of the data on the magnetic radius. This impact is really determined by an interplay of several factors. One is the sensitivity of the cross-section to the magnetic form factor, which appears only at finite Q-square. Another is the variation of our theoretical prediction for GM on the magnetic radius. We also have a theoretical uncertainty from the high mass pole, which becomes significant at at higher Q square. And altogether, say, kind of optimizing all these factors, we concluded that it's best to use data up to about Q square of 0.5 GeV square in this approach for this analysis. And the figure here in the upper left really summarizes the sensitivities. So these are the theoretical form factor predictions. Now that's for a fixed value of the electric radius, and for various values of the magnetic radii, 0.84, 0.85, 0.86, the blue, the red, and the green. So these are the Chiral EFT predictions as announced, that where the finite Q square behavior of the form factor is correlated with the radius. And the bands associated with the curves are the intrinsic theoretical uncertainties of these predictions. And you really see this interplay of kind of sensitivity to the radius on the one hand and uncertainty on the other hand if you go to larger Q square. And we can, as I said, we've optimized all that, and we use the data up to about Q square of 0.5 Jeff square for the final radius extraction.
5 minutes.
Yes. Now here is on the left is a plot of our like final fit to the MINDS data. The band here describes the variation of the result with the of the theoretical prediction with the radius. There's also an intrinsic theoretical uncertainty, which is not shown here and which is added separately. The figure at the lower right here shows the combined chi-square as a function of the electric radius and the magnetic radius after minimizing with respect to the normalization parameters, the floating normalization parameters. Now, here are the extracted radii. So we get an electric radius of 0.84 and a magnetic radius of 0.85, very similar. And let me not comment on the values so much as on the uncertainties, which are of main interest here. So you can see that the uncertainty, so for the uncertainties, we've quantified separately the fit uncertainty and the theory uncertainty in both cases. And you can see that the fit uncertainty actually, let me read it out first. So for the electric form factor, we obtain a fit uncertainty of 0.002 and a theory uncertainty in the range indicated here. For the magnetic form factor, we obtained a fit uncertainty of 0.001 Fermi and a theory uncertainty as indicated here. And interestingly, you can see that in the magnetic radius, the fit uncertainty is lower than in the electric one because it is determined by the higher Q square data where there's more sensitivity and more constraining power. However, the theory uncertainty is larger in the magnetic radius because we have to obviously go to higher Q square to constrain the magnetic radius where it's less constrained by the values of the radius and where the uncertainties from the high mass pole are more severe. And altogether, you can see that the magnetic radius really needs a theory-based extraction method. And I would like to mention that our results are consistent with the results of empirical dispersive fits, in particular this last one here from the Bonn group. So to summarize, the method of dispersively improved chiral EFT describes nucleon form factors combining dispersion theory and chiral EFT. It includes pi-pi rescattering and the row resonance in the spectral function through unitarity. It enables predictive calculations with controlled theoretical uncertainty. And it gives excellent agreement with the empirical form factors up to Q square 1 GeV square and beyond. And I have some summary plots about that, which I'm not showing here, but if you're interested, I can pull them up. The di-chiral EFT method enables a theory-based radius extraction. It correlates the q² equals 0 derivatives with the finite q² behavior through analyticity and sum rules. It employs the radii directly as parameters and kind of trades the low energy constants of chiral EFT for the radii. And as such, it enables a reliable determination of the magnetic radius from finite q² data. And as a last point, let me mention that this method of dispersively improved chiral EFT has many other interesting applications. We can compute the nucleon transverse charge and magnetization densities, which are actually projections of the generalized parton distributions that we discussed yesterday. They are integrals over X of the quark minus anti-quark GPDs. We've also applied the method to the scalar form factor of the nucleon, which is the form factor of the sigma term or the quark mass contribution in the nucleon mass decomposition. And you can see it's a very nice method, and we're actually looking forward to further applications. Thank you.
Thank you, Christian. We have time for one question. Randolph.
Sorry that I jumped in so much. Christian, thanks a lot for this great talk. That's very nice, of course. I was wondering about your results on the previous slide that you showed, where you state the uncertainties. I mean, the statistical uncertainties are really wonderful and small, and then you have a theory uncertainty. Now, as I will show in my talk later on, we are now going for something called the Semach radius, which is a convolution of electric and magnetic properties of the, basically the integral over product of electric and magnetic form factors. Now, my question, I assume that your theory uncertainty bands there are correlated because you fit electron scattering data, which is a combination of electric and magnetic processes. Now, if you were to calculate the Semach radius, would these somehow cancel or compensate because it's all constrained by the form factors which are measured? And can you get a better prediction for the Semach radius, which would enable us to find this resonance in muonic hydrogen much faster, maybe?
That's a very good comment and suggestion. We are actually in the process of computing the Semach radii. I did not have time to comment on that. And it is, as you say, the theory uncertainties are implemented in a fully correlated way. So we basically have, if you allow me to go back here, the main uncertainty comes from the unknown position of the high mass pole in the spectral function. So we take that as an open theory parameter, which we vary in a certain range. And so that's another parameter on which the another hidden variable on which the form factors depend, and we just do the full procedure of the radius extraction for extreme values of that parameter. So in this way, we hope to capture the full correlated theory uncertainty. And let me just point out that the uncertainties quoted here are not apples to apples. So the fit, that's the 1 sigma uncertainty, and the theory uncertainty is really the full range, as I described, by really pushing this position of the high mass pole to extreme values. So we cannot assign a kind of probability to that, but it would certainly be larger than 1 sigma. It would be more like 5 sigma or so, if you like. But yes, absolutely. So this method exactly allows you to compute quantities where these correlated uncertainties play a role, like the Semach radius. Densities are another example. So in the density, you do like a Fourier transform of the form factor, or you can also use a dispersion integral, and the result for the density at a certain radius is highly correlated across Q square. So in this way, we can really, by putting these correlations into the form factor model, we can get them implemented in the densities.
Can I have another question?
Super short, Jan.
Super short. Well, first this comment just to stress, because these extracted radii are displayed there again. This is kind of this self-fulfilling prophecy, maybe, that within the dispersion relations or these refined models, the form factor kind of has to look this way and predicts the radius there. And so if you have a few data only which fix a part of the model, then the radius or the radii will end up there. My question now is, for the experimental data, have you made use of the normalization constants to reconcile the data with the model? Or in other words, the figure that we always show, showing the discrepancy between also the JLab data and the MINES data, do you vastly, by a few percent, change the normalization of the different data sets to achieve this? Or is this solved in another way?
Let me answer from backwards. So we do, as I said, we did a full analysis with floating normalizations, exactly as the MINES analysis, where we use our our theory to guide the kind of use the knowledge of the shape of the form factor from the theory to determine the normalizations. So the normalizations we get in this way are within a percent or even a sub-percent level, agree with the original Bernauer et al. Analysis. The way we treat the normalization factors is as nuisance parameters. So they are they reflect a feature of the data that we have no control over, and we allow the chi-square to be kind of minimized with respect to that parameter, and we take into account the uncertainty that comes from fluctuations in these parameters through a bootstrap method, but we don't assign any meaning to the value of these parameters. And as I said, we also did an analysis of the rebin data by Hill, Arrington, and Lee, and we get the same radii within uncertainties, just with a lower chi-square, because the uncertainty estimate of the data is different. But let me come to the self-fulfilling prophecy, because you seem to imply that all dispersive fits kind of have to get a radius of 0.84. And just two comments. So first of all, the qualitative constraints from analyticity that we have, they are really on very solid grounds. So the fact that like where the singularities are and the rough distribution of the strength, that there's a rho type resonance sitting here, that's really God-given, and that alone gives you very strong constraints compared to other like purely empirical fits. And now one important point where we actually deviate from other dispersion fits and where we have more flexibility is that in our method, the height of the rho peak of the spectral function is allowed to vary with the radius, and it varies in a correlated way with this high mass pole. So, and this happens, it's really beautiful. It happens through these dispersive sum rules where the total where a certain integral of the spectral function is constrained to be equal to the radius. So now, as we vary the radius, the height of the rho peak and the height of this high mass pole, they are allowed to vary in a way that the total charge, of course, is conserved, and in a way that that together they produce this radius. And this is much more flexibility than the traditional dispersion fits have. They took Euler's calculation based on pioneering scattering as input, and no doubt this is an absolute excellent calculation. It was done 50 years ago and it still stands. But for the purpose of radius extraction, so the traditional dispersion fits do not allow. I say they take the rho as the height of the rho peak as axiomatic, and we allow it to fluctuate. And so I dare say we have more, actually more flexibility. And it's in that sense, it's a confirmation of the earlier results that comes out of our more flexible calculation.
Yeah, thanks a lot. I mean, there would be more to clarify here. That's really exciting, but
not now. Yeah, no, definitely not. Sorry, Jan. Sorry, Christian. Thank you again for the very nice talk. And we move to the next speaker, Randolph, that is going to talk about the nucleon, the nuclear structure from measurement in muonic and normal atoms. Randolph, if you can share your slides.
Where is it? Here it is. Wait a second.
So you have 25 minutes plus 5 minutes question, and I remind you 5 minutes earlier.
Okay, very good. So yeah, thanks a lot for inviting me and giving me the opportunity to talk about our measurements and our more recent results. I take some time to. I have some echo here. Somebody has his. Not muted. Okay. I take some time to explain to you how atoms can contribute to the question of nuclear and nucleon structure, both normal atoms and muonic atoms. And so these nuclear radii that we're talking about is this not only the proton but also other light nuclei. They are essential input for nucleon and nuclear structure and modeling of nucleus. But they're also interesting in precision tests of quantum electrodynamics and the standard model. And if we want to, maybe crack the standard model at some point in the future, using atoms, precision measurements in atomic physics, you will need to have reliable values for the charge radii. And another thing that these enter is the fundamental constants in this codata, least square adjustment of all fundamental constants. And so they are, at the moment, there's only the proton and the deuteron in this codata fundamental constants, but we will expect that this is soon going to change, and including helium and maybe even lithium and beryllium. So here's my map of the world. It's concerned with charge radii, and they have all been measured in electron scattering, and these are the numbers in femtometers in these blue numbers, and we're trying to improve on this by a factor of 10 or so. Then 10 years ago, this proton radius puzzle came about when our measurement of the muonic hydrogen atom, as you all know, got a large discrepancy with respect to the previous determinations in both electron scattering and hydrogen spectroscopy. This made quite some noise, and 10 years later, it's still worth a discussion in the session in this conference. So it's looking at the problem of a deep understanding problem in our understanding of the nucleon. I'm an atomic physicist, but I always show this slide in terms that the electron scattering is a story on its own. And depending on whom you ask, you get different answers on the charge radii of the proton, charge radius of the proton, as was touched upon by Jan and Christian. If you take these classical Rosenbluth separated numbers, or if you use these dispersion relations. But I'm focusing on atomic physics, and I would like to briefly show you how hydrogen, how atomic physics can contribute to the knowledge of the charge radii. You all know this Bohr model of the atom, where you have an electron orbiting in a planet-like orbit around the proton, and Bohr actually got it almost right with this somewhat awkward starting point of a planetary system. The energy levels are proportional to something which is now today called this Ripper constant over n squared, where n is the principal quantum number. And then there is a host of other information that you have to digest and calculate the QED contributions to these energy levels, which we assume now for a moment can be calculated with great precision because it's a simple hydrogen-like atom. So two-body system where you can calculate this with 12 digits of accuracy. And then you still have this additional term, which is this finite size effect. And this comes from the fact that the wave function, the radial wave function of an electron orbiting a proton has a maximum at the origin for S states, which is this 1s state and the 2s state. So here the radial wave function is maximally here at the origin. And for P states and others, you have a zero here. That literally means that the electron penetrates the nucleus in such a hydrogen-like system. And when the electron is inside of the proton, because the proton is somewhere here at r equals 0, when the electron is inside the proton, it sees a reduced Coulomb attraction because it sees Coulomb attraction from all sides. And so on average, these energy levels are displaced. And this is the finite size effect, which is 1.2 megahertz for the ground state in hydrogen, and scales it with 1 over n cubed. So by measuring two of these transitions, you can extract a charge radius of the proton and a Ripper constant in a correlated pair. Now we're dealing with muonic hydrogen, and that is a proton orbited by a negative muon. And as you all know, the muon is 200 times heavier than the electron. Therefore, the Bohr radius is 200 times smaller. So this picture is completely not to scale. And the wave function overlap, so the probability to find the muon at r equals 0 that is inside the proton, scales with a third power because it's smaller in x, y, and z, this Bohr radius, and that is a few million times higher sensitivity to the proton size. The classical lamp shift is what we measured in muonic atoms, is this 2s to 2p transition. And here is the plot there where you should see that this finite size is really macroscopic for such a muonic hydrogen atom. The red dashed line is the line that you expect for a point-like proton, and the 0.84 femtometer shifts this up by about 2%. There's a 2% effect if you look at this, and therefore that shows that this 2% effect is really large, and we don't have to measure very accurately. Only 10 to minus 5 in laser spectroscopy, which is not very precise. And then 10 years ago, we got this outcome that our resonance, which is this measurement of this lamp shift transition, is here, peaking at that point, whereas the prediction from electron scattering and hydrogen mainly was 5 sigmas away. And that gave the start of the proton radius puzzle. The first big debates were made about the theory in muonic hydrogen, and you see that this is this equation which I showed you, where you have to see this 2% effect from the proton form factor. The leading term, but 99%, is this simple electron vacuum polarization term, and then there is many other higher order diagrams. And the battleground was this two-photon exchange, the polarizability contribution from this term here, from the virtual excitation of the proton with 2 photons. So this formula is very difficult to calculate in all details, but the good news is that if you look at on a log scale, this one loop electron vacuum polarization is 99% of this initial term, and this dominates everything. The second most important effect is this finite size effect. That's the reason why we do this experiment. Then the 2-photon exchange, the central term here, is on the very small scale already, and the discrepancy is much larger. So this discrepancy between the large electron scattering value of the proton charge radius and our result would be the 5th largest term if it had to be accounted to a missing QED term or missing theory term. In the end, it boiled down to the question: can the polarizability explain this discrepancy? And it basically boils down to this Feynman diagram, where you have the inelastic 2-photon exchange or polarizability contribution, and the essence of this can be basically traced back to some subtraction term in the dispersive treatment or dispersive calculation of this term, using virtual Compton scattering data. And this subtraction term is known only at q square equals 0, which is the magnetic polarizability of the, or is given by the magnetic polarizability, and then the large q square behavior, which is also known. But the question is in the intermediate part, what can you do? Or how does it look there? There's no data. And but in general, this term seems to be small and cannot explain the discrepancy. Voila. Yeah, so we have measured other nuclei with muons in the meantime, and I've also been part of experiments measuring the proton radius with normal hydrogen, and I would like to give you an update on that, and trying to convince you that muonic atoms actually give reliable values for the charge radii. So muonic deuterium, there's been the same 5 sigma discrepancy between the CODATA 2014, which is the last published value for the CODATA least square adjustments, and our measurement in muonic deuterium. You see, our value has moved a little bit from the first publication. It has moved a little bit to the right, to larger radii. This is an update in theory, and the main essence of this is that there is a 3-photon nuclear polarizability contribution, which is astonishingly large, and which has been evaluated in the group of Krzysztof Pachucki, and that has shifted this deuteron radius to slightly larger values, a bit more than a sigma than our previous published value. And it's now in excellent agreement with this value, which is, I would claim, the best value of the deuteron charge radius. And this comes from using our muonic proton radius and the electronic isotope shift that we've measured in Garching on the normal hydrogen deuterium 1s2s transition. That's the best measured transition in hydrogen with a few parts in 10 to the 15 accuracy. And from the isotope shift, you can get the difference of charge radii. Here is the value. You get this with a very small uncertainty. And if you plug into this equation, you plug in the proton radius from muonic hydrogen, you get muonic deuterium, a deuteron charge radius, which is this small uncertainty. And the agreement of muonic deuterium and the expected deuteron charge radius shows somehow the internal consistency of these muon-based determinations. Voila. So the theory in muonic deuterium, and here you see these 2 shaded bands. The inner band, the thicker red band, is our experimental uncertainty. You see here the value, and the outer shaded band is the theoretical uncertainty, and that of course comes from these polarizability contributions, both the nuclear and the nucleon. And the best most recent determination of this 2-photon exchange effect gives this uncertainty, which is despite being the best theoretical calculation, it's still not it's still shy of our experimental uncertainty by a factor of 6 or so. So you can use now this equation up here in 2 ways. Either you plug in the calculated 2-photon exchange contribution, and then you use our measurement of this energy difference in muonic deuterium to extract the charge radius, and that is the number that you saw on the previous slide with these 2 uncertainties. But you can also do something different. I told you that sorry, home office. Then you can also use this deuteron radius, which I showed you before, which is this best estimate of the deuteron charge radius from the muonic proton radius and the isotope shift. You can plug it in. You can take our measurement on the left-hand side, and then you can calculate the 2-photon exchange, 2 and 3-photon exchange nuclear polarizability contribution. And that gives this value, which is in of course, good agreement with the theoretical value, but a factor of 3 or so more accurate. So that's a general statement. If you have a calculation of the polarizability, muonic atoms usually give you a very good value for the charge radius, usually limited by the polarizability. And if you have a good radius from somewhere else, for example, electronic atoms or scattering, you can use the muonic atom spectroscopy to determine polarizabilities. So in that sense, we learn much more about the nucleus and the nucleons. Okay, so hydrogen. I showed you this before, and I told you that by measuring energy level spacings in hydrogen, you get, if you have two measurements, you can get a correlated number for the Ripper constant and the proton charge radius. And if you look at the charge radius, this is the world until 2014 or so, where you have this ensemble of many measurements in hydrogen, which individually are not very discrepant with our muonic value. But if you average these 25 measurements in hydrogen and deuterium, you get this very small uncertainty, which is then 4 sigma or so away from the muonic hydrogen value. Of course, people have set out on improving these measurements with the advent of this proton radius puzzle. We did a measurement in Garching doing laser spectroscopy on the 2s4p transition, and due to some time constraints, I will not go into the details. Please ask me if you want to learn something about this. The essence is that on this proton radius puzzle plot, this is a significant contribution because it's one measurement which has the same, similar statistical or similar uncertainty as the world data on hydrogen that was taken before, but it agrees with the small muonic proton radius. Then shortly afterwards, a new measurement from Paris came about with which is the 1s3s transition in hydrogen, again combined with our measurement in 1s2s. That gives you this charge radius, which is large, and that was somehow came as a surprise. But then in the meantime, there was a measurement of the classical lamp shift 2s2p in normal hydrogen, which also gives the small radius, and then of course the PRAD measurement that Ashad will talk about in his next talk, which also gets a small radius. So it seems that people are getting more and more used to accepting the fact that the proton radius is actually small. And now there's the question about this measurement. We've already, I don't know, 15 years ago, so in Garching started out in also doing this measurement. And with an heroic effort of the generations of PhD students who really had to fight a lot with this apparatus, we have now actually gotten a paper into Science, which will be published next week, about a completely different way of measuring 1s3s in normal hydrogen compared to the previous Paris measurement. This is the data we typically take. We do some frequency comb spectroscopy where we have lots of laser frequencies at the same time, and then that gives rise to a very funny spectrum that we observe, but we have this clearly separated peak of the 1s3s transition with some side peaks due to other possible transitions. And we do this in a very cold hydrogen atomic beam to get lots of systematics to very small and acceptable levels, and we're not correcting our final result by a lot. And the result, which is preliminary until next Friday when this will appear, is that the hydrogen 1s3s measurement in Garching gets you to a smaller radius compared to the previous determination, previous best determination in Paris. It's still 2 sigmas or so away from the muonic value. It's also 2 sigmas away from the Paris value because the sigma is a different size if you take the combined error bar. But I would argue that this is on the small side of this table, and there's still a 10% chance that you have such a statistical fluctuation, or there's maybe some systematic which is underestimated a little bit also. But in the end, this also confirms the smaller proton radius from muonic hydrogen. I'm in Mainz, so I have to, I must, and I would like to advertise our new MESA accelerator, which has been touched upon already in Jan's talk today. This is now under construction. The building is being built, and there the MAGIX experiment will go to the next level in spectrometer-based form factor measurements for hydrogen, maybe deuterium, and maybe helium in the future, and then can be compared with our determinations. Another paper which has just been accepted from the Kramer collaboration is measurement of the helium-4 charge radius based on muonic helium ions. So it's a helium-4 nucleus, which is only orbited by a single muon. There's no electron around. And that has been analyzed and accepted. That's analyzed, but we have to write the paper. We have to finish the paper on muonic helium-3. So I will show you first muonic helium-3. The very preliminary still result is that there is no discrepancy compared to the world data on electron scattering on the helium-3 nucleus. That's perfect agreement. Again, you see this smaller shaded band and this wider shaded band. The smaller shaded band is the experimental uncertainty that we have, and the theoretical uncertainty from the nuclear polarizability is a factor of 10 or so larger. And that does not yet include the effects from the 3-photon nuclear polarizability contribution, which I expect to be large. So this will maybe even go a little bit larger. For muonic helium-4, this is the money plot from our paper. You see, this is our data, and this is where we expected this line to see this line, and this is where we found it. So there's again a perfect agreement between the world data on elastic electron scattering on the helium-4 nucleus. This is our muonic value. Again, these two shaded bands. You see, this is the theory uncertainty. Here we implemented an estimate for the uncalculated inelastic 3-photon contribution, which is somewhat an educated guess, which was approved by Krzysztof Pachucki, who did the 3-photon exchange on the deuteron and the elastic 3-photon exchange on helium-4 and helium-3 as well. So the bottom line is there are no discrepancies left anymore. In helium-3 and helium-4, we have perfect agreement with elastic scattering, but there's not yet a result from spectroscopy of electrons. However, there's works on the way, both in Max Planck in Garching and in Amsterdam in the IKEMA lab, where these groups will study hydrogen-like helium plus ions, and that will boost the QED test and determine the Ripper constant. And then we can also determine these 2- and 3-photon exchange polarizabilities with quite a bit improved uncertainty. The agreement suggests that there is no beyond standard model solution required for the proton-deuteron radius discrepancies. And on top of this, this new value for the alpha particle charge radius is, I would claim, a precise benchmark for few nucleon theories. And we can also improve a little bit the helium-6 and helium-8 radii, which are these interesting, very interesting halo nuclei, these borromean nuclei. But there now one needs to have a better determination of these isotope shifts in normal helium-6 and helium-8 to be able to improve on the charge radii. But with our measurement of this helium-4 anchor nucleus, we are opening the way towards an improved determination of these nuclear charge radii.
4 minutes. Oh, perfect.
Okay, so no, this is intermediate conclusions. I'm still halfway through my talk only. No,
I hope not halfway.
No, I'm joking. So what I told you is that if we combine our measurements in muonic ions and atoms with calculated polarizability, we can improve typically the charge radii by a factor of 10 or so, and that gives these small 1 digit in the fourth digit charge radii, with the exception of this deuteron proton radii where we have this shift. This is in good agreement. But we can also turn this around and say we take, for example, the charge radius from normal atoms, and we can get nuclear polarizability contribution. So with that, charge radii are put on a hold now, and we are turning towards the magnetization distribution of the proton in the Kramer collaboration. You know that the hydrogen 1s ground state hyperfine splitting is one of the best measured, or has for a long time been one of the best measured transitions of all of them. 50 years ago, people measured this with a hydrogen maser to an astonishing 12 digits. But these last digits, the 6 last digits, cannot be used as a test of quantum electrodynamics because of these proton size and polarizability contributions. And we hope to improve this by a factor of more than 10. Compared to what Christian just said before, this is another interesting quantity. This Semach radius. So This hyperfine splitting is governed by the so-called Seemach radius, which is this in position space, this funny convolution of electric and magnetization distribution, or more correctly in the momentum space, you go to a product of electric and magnetic form factors integrated. And so this is again something where you can compare muonic hydrogen with normal hydrogen and with elastic electron scattering, both magnetic and electric form factors. So there's again an opportunity to learn from each other. And this is the map of these so-called Seemach radii up to now. Here you see the value from hydrogen, and depending on whose polarizability calculation you believe, you see this is the wiggle room that you have on the Seemach radius. But there's also a problem with the older elastic electron-proton scattering as evaluated by Jim Fryer. At the new MINDS evaluation, you see that there is some difference. And from our lamp shift measurements, we can also infer with a very bad uncertainty a proton Seemach radius, but the new project is aiming at such an error bar. So then we can again compare and see if there's something interesting. The
Sorry,
problem is,
Stefan, could you mute your, yeah, thanks.
So with that, we will measure this hyperfine splitting with a ppm accuracy. Then we can get these 2 photon exchange contributions with 10 to minus 4 relative accuracy. And that can then be used either to determine the polarizability if you plug in the Seemach radii from scattering, or you can determine the Seemach radii if theory gives us the polarizability. With the Seemach radius, one can use a model to determine magnetic radii. So it's somehow not a direct access to the magnetization distribution, but to this convolution. The problem is that even worse than in the lamp shift in muonic hydrogen, where we had to search for 5 sigmas, and this took us years because we were not prepared, and we should have listened to the dispersive analysis as we learned from Jan this morning, or 2 talks ago. So we have an uncertainty because of this the prediction of the resonance, and this boils down to hundreds of measurement points which we have to cover, because the resonance is very narrow, and the field of predictions of our transition gives rise to a few hundred measurement points, which is nearly prohibitively large. So we would really like to have an improved determination of the Seemach radius, if possible, and of the polarizabilities for the hyperfine splitting. Okay, and with a brief outlook, we think we can do muonic lithium and maybe even muonic beryllium. This is hard, and this is very hard, but that's something we can do. We are also thinking of improving on the proton charge radius, because this was our measurement was a first ever, and this can certainly be improved by a factor of maybe 5 or so. But then we are again in problems with the polarizability contribution. And then we are now looking, or we are aiming at a measurement of the triton radius, because you see this is a really bad uncertainty compared to the other ones. And we hope to get this down by a factor of 300 or so by measuring 1s, 2s in tritium. And with that, I would like to mention all the people who did all this work, and a picture of my group before COVID. And if you have people who want to join my group, here's my email. And with that, I would like to thank you.
Thanks a lot, Randolph, for the very nice talk. Now we are open to questions. Please use the raise hand button. Christian.
Yes. Is there a reason why the 3 photon exchange contributions in deuterium are so large? I mean, is it because the system is loosely bound, or is it some quantum number thing, and is the same size expected for other nuclei, or is it particular to the deuteron?
So as far as I understand it, it's related to the fact that the deuteron is such a loosely bound thing, and it's been estimated for the proton, and it's much smaller, and at the moment still almost negligible at our level of accuracy. And so for helium-3 and helium-4, only the elastic contributions have been calculated, but not the nuclear inelastic, which is difficult. And but people are looking into this, and it's probably on the way. We expect something to be, you know, for our guesstimate is we said it's between 0 and 100% of the elastic contribution. That's what you see for the proton, where you have this, you know, very 300 MeV far away delta resonance, and for the deuteron, where you have only these 2 MeV binding energy. So we said somehow for helium-4 it must be somehow in between, and we gave it a 100% error. That's all we could do, and that increases our uncertainty a little bit from 17 hour units to 85 or so. So the 2 photon and 3 photon, so the 3 photon is in fact astonishingly large, and maybe a worthwhile investigation.
Okay, thank you. It's very interesting.
Thank you. We have time for one short question, if necessary. Seems not to be the case. Thanks again, Randolph.
Thank you.
And we move to the next speaker, Ashot, talking about the PRAD experiment. Ashot?
Hello, can you hear me?
Yeah. I can hear you now.
Let me try to share. So I wasn't prepared because I was expecting news talk. So let me see. It's supposed to be somewhere here, right? Oh.
So while you are getting prepared, just want to say that you have 30 minutes. After 20 minutes, I will tell you that there are 5 minutes left, and just in order to leave 5 minutes for questions.
For now, I cannot find my talk. Can you see now? No.
Not yet.
Okay. What happened with this? Give me a second. Supposed to be okay, huh?
If you need more time, we can try to see whether Ronald will be ready, and it's fine for the organizer to just swap the two talks.
Yeah, looks like I need that because I cannot find my screen, which is very, very strange.
Okay.
Can you close all other windows except for the one? I also have this problem sometimes.
Yeah, looks like so. Let me go through those whole things. Yeah, you take your time and just use that. Looks like it will go longer.
Okay, so Ronald, are you connected? Would you mind to start before Ashot?
Have I shared my screen?
Yes.
Okay, then let's see. I will.
Yeah, you're in full screen, 30 minutes. I'll tell you after 20 minutes.
Okay, good. We'll talk about the Muse experiment at PSI, some motivation, most of the time on the experiment and status, and a brief summary at the end. Of course, the motivation comes about because of Randolph's measurement, which we've just heard about. So I don't think I need to talk about it in any detail. It's the muonic hydrogen measurement that found the proton radius was smaller than we generally believed
before. And I think since we're running late, I'll just be very, very fast here and go on to the next slide. So as of 2013, we had two muonic hydrogen measurements that showed a small radius. Generally from the electronic measurements, the hydrogen spectroscopy and scattering, we believe the radius was larger. And we were thinking about what to do about this situation among the group of us who were electron scatterers. Of course, there are two classes of explanations: that there's something interesting happening and new physics to learn, whether it's beyond standard model or conventional physics, or there's some experimental issues that we didn't appreciate in advance. When we looked at the situation, in particular, when Michael Cole and I were at a conference in Marrakesh talking about the situation, we noticed the following. We made the following observation, that we didn't have any muon scattering radius for the proton. We had the hydrogen spectroscopy, we had the electron scattering, and we now had the muonic hydrogen. So it was obvious to us to try to measure muon scattering and to compare. I will note at this time, just to be precise, that there actually is a measurement of the proton radius from muon scattering. There's an unpublished PhD thesis from Columbia and Nevis labs that found a radius of 1.1 plus or minus 0.2 Fermis, which clearly isn't precise enough to distinguish between the 0.84 and 0.88 Fermi sizes that were brought up in the proton radius puzzle. So as time has progressed, as Randolph showed us, we've had a series of new results and measurements. We've had atomic hydrogen measurements that are both large and small radius. We've had analyses that are both large and small radius, and we've had scattering experiments, initial state radiation from MINDS and the PRAD experiment at JLab that are both large and small radius. And I also show on this slide an anticipated result from MUSE. So it looks increasingly with time like the real result is the small radius and its experimental issues, but I do want to show another plot that there's a problem in the scattering experiments. This is a plot of the extracted electric form factor as a function of Q squared from PRAD versus from MINDS. And you'll notice the two data sets are slightly off by about 1% in GE. And this leads to questions of whether we understand well enough our radiative corrections in analyzing the electron scattering data, or whether we still have issues in the experiments, not just the fitting that's been talked about, but in the experiments themselves. So, so this is the background. We have the MUSE experiment at the Paul Scherrer Institute. The picture on the top shows the Paul Scherrer Institute. The high intensity proton accelerator facility is the multiply wedge-shaped building kind of in the middle right of the picture. The red circle I've drawn on it indicates where MUSE is located in the PIM1 channel. It's a few tens of meters from where the CREMA experiments were located on the opposite side of the proton beam line. The picture on the bottom shows the PIM1 area with our experiment platform where the entire experiment sits. Located in PIM1, we fill up a large percentage of PIM1. This picture was taken in mid-2018 when we were starting to put electronics and systems on the platform. So at this point, it doesn't really have detectors, it just has collaborators in it. So we operate in PIM1. The way the system works is that the accelerator provides 2 milliamps roughly of roughly 600 MeV kinetic energy protons. They go through a graphite wheel and produce pions, muons, and electrons. The PIM1 channel is a series of quadrupoles and dipoles that transport beam in the range of about 100 to 400 MeV over C to the experimental area. So what we in MUSE in the experimental area get is a mixed beam of pi's, mu's, and e's. The beam's about centimeter sized, so about 100 times the size of a JLab or MINDS beam. It's up to about plus or minus 1.5% momentum byte. So it's about 100 times the momentum byte of a Jefferson Lab or MINDS beam. And we operate at 3.5 megahertz flux, which is about 100 million times less than the flux of a Jefferson Lab or MINDS beam. For the experiment, we only use the channel between about 115 and 210 MeV over C. The idea in the experiment is to have a low luminosity experiment with a large acceptance non-magnetic spectrometer. The fact that we have a limited flux of muons means we need a large acceptance spectrometer. because the flux of that 3.5 megahertz flux is in fact mainly pions and electrons. The experiment as designed is broader than a proton radius with muon experiment. The beam is mixed E mu pi, so we have muon and electron scattering at the same time from protons. So we get cross sections for both at the same time. We extract GE from data taken at the same time. We extract R from data taken at the same time. And that allows us to not only compare extracted radii, but directly compare the cross sections of the data, which removes issues of fitting and provides a more direct lepton universality test, and alternately a more direct radiative correction test, since the radiative corrections are different from muons and electrons. We also operate at both beam polarities, positive and negative charged beam. That's a direct measurement of two photon exchange and radiative corrections. We use a liquid hydrogen target, which is in a Kapton cell. That means we also measure scattering of muons and electrons, and these observables I mentioned above on carbon in the Kapton cell and in background measurements. The pion scattering is also done at the same time. It's a necessary evil because there's pions in the beam, but there's also interest in pi proton scattering for chiral perturbation theory. So it's an effective field theory test for QCD. Occasionally we have other ideas suggested to us, like narrow resonances at various energies in pi p scattering, or more recently inverse pion electroproduction. And these aren't driving what we're doing, but they may be there in our acceptance. Okay, so we came up with this idea back in 2011, actually, and we did some amount of testing. We got construction money from the National Science Foundation starting in 2016. We put the experiment together, and in fall 2019, we had the entire experiment assembled on the platform. This is a picture of the entire, I should say the entire experiment on the platform gets craned into or out of PIM1, depending on whether we have the beam time or not. So this is a picture of the platform, a couple meters in the air, hanging from a couple chains. Mostly what you see here is electronics, racks, cables, platform structure. If you look closely in the very middle, you can see a little black square. That's the first of our detectors that the beam hits. And if you look off to the left side, you can see a sort of red and black checkerboard pattern. And that is actually one of our scattered particle scintillators. So to show you the experiment more clearly, I'll go to the GÉANT simulation of the detectors with all the support structures removed. So the electrons, pions, and muons come out of the channel. They, because of the acceptance of the beamline, the large spot size and large momentum acceptance, we need to individually track each incoming beam particle. We do that with a beam hodoscope detector, a scintillator array that determines the time of particles and thus the species of particle. 3 gem chambers that determine the trajectory. Veto scintillator that's to eliminate pion decays in flight to some degree and scattering from these upstream detectors that might otherwise trigger our system. The beam then goes into a scattering chamber with a liquid hydrogen target. Most of the beam exits the scattering chamber largely unscattered and goes to a beamline monitor at the end of the beamline. The scattered particles go out windows on the side and go through straw tube tracker chambers and scattered particle scintillators to determine the scattering probability. So I will quickly go through the equipment of the experiment. This is the picture here is of the very first detector on the beamline, the beam hodoscope scintillator shown during construction on the lower left. It's made up of thin scintillator with Hamamatsu Psi-PM readout. We use constant fraction discriminators and the usual TDCs and QDCs to measure times and pulse sizes of particles. This technology gives us timing resolutions that, as you can see in the upper right, are of order 50 to 70 picoseconds for most of our detectors. This is about an order of magnitude better than we usually use in the field. And because it's so much better than we usually use in the field, that means that while it performs very well, that getting the last issues at the level of tens of picoseconds turns out to be difficult. So the system works very well, but we keep looking for potential issues in our timing and such at the tens of picosecond level. In the lower right, it just is a plot of the count rate in the scintillators versus time after we turn the beam off. One issue with scintillators is that beam particles come in, knock out neutrons from carbon-12, produce carbon-11 that has a 20-minute half-life. And so you have activity, background activity in the detectors just from the carbon-11 production. The SciPM scintillators, actually, we've written an article on them. It's appeared in NIM about a couple of weeks ago. And I just include for reference here in the talk the NIM article and the link to the NIM article if you want to find out more about these detectors. The next detector in the beamline is the GEM chamber, the set of GEM chambers. So the GEM telescope was actually used in the Olympus experiment, the two-photon experiment at DAISY. We've installed it at PSI a couple of years back. Its readout has been upgraded. Its geometry has been changed a little bit to better fit in our setup. There are various analysis upgrades. So it's an existing detector with some upgrades. And I just show in the upper left here, the GEM chamber in position after the beam photoscope. And in the lower right, a picture of the beam spot where you can see that the beam spot is indeed centimeter sized. The next detector in line is the Vito scintillator. It's an aperture through which the beam goes to reduce scattering upstream or decays in flight upstream. I don't have a good picture of it in the setup because once it's installed in the setup, the GEMs are immediately before it and the scattering chamber is immediately afterward. So it's hard to take a picture. So I show you a picture here of the assembled detector just prior to installation. It's conventional BC404 scintillator, I'm sorry, EJ204 scintillator, which is pretty much the same thing from a different manufacturer with Hamamatsu PMT readout. Okay, then we go to the liquid hydrogen target. The liquid hydrogen target has been operational since late 2018. The pictures on the left are mechanical drawings of the target system. The vacuum chamber has inside it a target ladder that has a full cell of liquid hydrogen and empty dummy cells so we can do background subtractions. Some solid targets below that for simpler geometry for scattering, and below that what's called a beam focus monitor to be able to get a measurement of the beam position right in the target position. On the right, is a plot of target temperature over time when we first got it operational in late 2018, and you can see that the temperature was stable to 0.01 Kelvin. Okay, the scattered particles go through a straw tube tracker. This is the straw tube tracker after being removed from the platform in January 2020. You can see in the middle of the picture on the right, the planes of straws. What we do is we take the straws, thin-walled straws, we overpressure them by 1 atmosphere. We run with 90% argon, 10% CO2 gas. Each side consists of 5 planes that measure the position horizontally, so the scattering angle position, 5 planes that measure the position vertically, so the azimuthal angle position roughly, and followed by another set of 5 plus 5 planes. So 10x, 10y planes on each side. They are read out with pass-direct cards and TRB3 TDC systems, again following the Honda straw chamber design. While this system was operated in late 2019, we decided that it was somewhat brittle. We had some issues with it that required fixing while running it. And we decided to redo some parts of the gas and electronics readout to try to have a less brittle system. Also, there's one chamber that was originally, the first chamber produced was a little bit damaged during transport to PSI. And we're rebuilding that chamber as well. So the connectors and gas system are all being redone this year, as well as that one chamber. The fixes have all been done, except they've not been assembled because there's been some issue this year called COVID that I'm sure you're all way too familiar with. The conventional scintillators after the straw tube tracker are shown here. And you can see again the red and black pattern on them. They're again EJ204 scintillator with Hamamatsu PMT readout. There are several details to the construction that I won't go into. They follow generally the JLab class 12 GeV time of flight system, and they obtain between 45 and 60 picosecond timing resolution using thick scintillator with the Hamamatsu PMT readout. This is taken in summer 2019 when the STT was not installed. I will note here that we have a bunch of protection brackets that go over these scintillators to try to avoid damage, and that crossbar you see in the middle is not there for data taking. It's just there when we're not taking data to avoid damage to the scintillators. I have a couple pictures here of the scintillator performance. The picture on the upper left shows measured time resolution along the bar for one of the larger back wall bars. And you can see that it's generally around 50, 60 picoseconds and better in the middle of the bar than at the ends. The front bars, which are thinner, only 3 centimeters thick, but shorter, get better time resolution by about 10 picoseconds or so. We calibrate the bars using room background, in particular the Compton edge from thallium decay, and that's shown on the right here. The energy is about 2.35 MeV, if I remember correctly, for the Compton edge, and the Monte Carlo simulation shows a nice reproduction of the Compton edge in the scintillator. The bar on the plot on the bottom right shows scattering data from the front and back wall that shows the correlation between the bar number in the front and the bar number in the back. The diagonal band is events that are coming from the target region. There's a little bit extra events you can see along the 2 axes, and in one case it's pion decays in flight that tend to be a smaller number back wall bar than you expect, and in the other case it's backscattering from the exit posts of the chamber and the beam monitor, which tend to show up with a larger back wall number than you'd expect. Okay, I want to move quickly on to the trigger system. One issue we have in the experiment, as I've, one benefit, one issue is that we have a mixed beam of Mu's, E's, and Pi's. And Mu's and E's have electromagnetic cross sections. Pions have strong interaction cross sections. So if we don't identify the particles as they come in through our system and use that in our triggering, our data set will be essentially all pions. So this is the start of the explanation. This is the top plot shows the time of hits in the beam photoscope detector compared to the time of our trigger. And what you see in the graphs, the out of time region, and to the left and the right is this repeated pattern, and that's the 19.75 nanosecond beam RF period. So the proton beam RF structure is a pulse every about 20 nanoseconds. If you focus in on that with better resolution, you see repeating structures of muons, electrons, and pions, as shown in the bottom right plot. I want to note that the in-time region has a structure to it as well. It's if you're used to some triggering systems, the trigger is timed with respect to the particles going through the detector, so you get a nice sharp peak. In our system, all the logic is done in FPGAs, and this logic signals are timed to the FPGA clocks, and they're asynchronous and out of phase with respect to the beam RF. So the in-time structure is wide. It's about 60 nanoseconds wide and has structure to it. Okay, so what we do is we, in an FPGA, we look at the RF, we get a signal from the RF, and we get signals from the detectors. We identify the time difference between them. We identify the particle type as mu, E, or pi. So the plot on the upper right shows the out of time RF spectrum and the in time RF spectrum when we had a trigger that was electron or muon, but ignored the pions. So the out of time spectrum in red actually shows a larger number of pions than electrons and a larger number of electrons than muons. When we trigger on electrons and muons, you see the electron and muon peaks go up relative to the pion peak, which goes down. The reason why there are still pions in the RF spectrum is that at our beam flux, there's a reasonable probability that you get 2 particles within 20 to 40 nanoseconds of each other. So they both show up in the analysis here of the in-time particles. If you do a background subtraction of the in-time triggered spectrum minus what you expect from the out of time, what you see is all the pions disappear. So we see that our FPGA triggering is working well. And the next step is to implement the pion as a veto. So we only see electron and muon events when there's no pion as well. Okay, that's it for the hardware. I wanted to move on a little bit to the radiative corrections and expectations for the experiment. The radiative corrections are small for muons. The point here is that people are used to electron scattering, are used to relativistic particles and something like 10 or 20% radiative corrections. We are operating at momenta where the momentum and the muon mass are similar in magnitude, And the muons, as a result, aren't highly relativistic and don't emit photons very much. So this is a calculation of the radiative correction factor for the muons in our kinematics from Andrei Afanasyev. I will note that often people show the radiative correction as 1 plus delta, and they just show delta. This is 1 plus delta in this plot. So the radiative correction for muons is generally a number around 1%, a little more precisely 1.2%. And you can see that the radiative correction lines here, as long as you're away from the peak, are very, very flat. So the muon corrections are about 1.2 plus or minus 0.2%, where I'll leave the exact measure of the uncertainty to your eye over a wide range of angles. And they're not quite at the level where they can be ignored, but they are at the level where they're a relatively minor effect.
4 minutes.
Okay. The other issue is the radiative corrections for electrons. They're much bigger. And on this plot, I show you a calculation. You see the elastic peak on the left panel up at the high lepton momentum, and you see the tail that quickly rises as you go towards zero momentum on the left side. And compared to that, on the right side, you see the photon momentum. The biggest thing that contributes to the tail in the electrons are these high energy photons that are emitted in forward directions, the red blob that appears to the lower right of the panel on the right. And we realized we could learn more about the radiative corrections and constrain the uncertainty by doing something about that tail. So we started assembling a lead glass calorimeter borrowed from detectors borrowed from Mainz. We did simulations to look at what would happen with the calorimeter looking at the forward-going photons. What you see here in red is the raw data, what happens to the radiative correction if you don't look at the forward-going photons, and in blue and green, if you apply cuts on forward-going photon energy, what happens to the radiative correction. The important point here is that it flattens out a lot and reduces the systematics reflecting, related to the radiative correction. We tested the calorimeter in Beam in late 2019. This is just an example with 210 MeV/C electrons for the response. What we see is we get relative knowledge of the momentum of the electrons at the 10 to 15% level at the range of our momenta. So the calorimeter seems to work well in initial testing. We've looked at the systematic uncertainties in the radiative corrections. The plot on the right is for muons, and it shows the uncertainties in the radiative corrections are estimated to be at the few hundredths of a percent level. So, so not that large. The uncertainties for the electrons are estimated to be at about the 0.5% level, which is what we've long expected. I wanted to note that we actually have a bit of a physics result. This is from Yevgen Lavrukin's PhD thesis and something he showed at the American Physical Society Division of Nuclear Physics meeting a couple weeks ago. This is actually for pion scattering. It's a ratio of pi plus p to pi minus p cross sections. This was taken last summer of 2019 in a few hours, and it's done as a ratio to get rid of many sins. And what you see is that the ratio of pi plus p to pi minus p roughly agrees with the partial wave analysis of the existing database. There's some suspicion of an S11 resonance that affects only the pi minus p. And you can see right at the energy of the S11 resonance, which is the upper right plot, there's a bit of a deviation between the partial wave analysis and the data. And I will not go any further than that in this discussion. Okay, so let me move on to the anticipated data again. This is the same plot I showed before, but now the MUSE data added to the bottom. This is the MUSE data shown here, a combination of the electron points we expect to measure and the muon points we expect to measure. They are pairs of points slightly offset in Q squared because of the mass differences between the particles. You can see they're similar in size, though they grow to larger in size at our largest angles to the previous data sets. If you extract the radius from our data, you come up with an estimated uncertainty of about 0.006 Fermis, 0.045 Fermis for muons and electrons. It depends on the fit function, and there's a lot more to say about fitting I won't say. And two photon exchange, I just want to quickly show this plot from the Olympus measurement. I think this is the world's best measurement of two photon exchange. We'll have about twice as much data with twice as good uncertainties, twice better uncertainties for the electrons, similar uncertainties with twice as much data for the muons. And so my final slide, full system was assembled in 2019. There's been some detailed work we've been planning on doing to upgrade it for some more tests and starting of production data this year. Of course, that was the plan, and then COVID happened. Most of us are not in Switzerland. We can't travel, so our fixes have been delayed to a large degree. We do have beam time upcoming in the next few weeks, and we will be doing some tests of various parts of the system. We are hoping to reassemble it in spring 2021 and test it and move on to production data taking in the next few years. The radius will take all the data to analyze. We're doing a blinded analysis. If it's consistent, we'll have other results coming out sooner. And thank you.
Thanks a lot, Ronald. And sorry for asking you to jump in prior to your original schedule. Time for questions. Randolph? Sorry, Jan,
Sorry,
you didn't
Jan.
raise your you didn't raise your hand. So Randolph.
I'm sorry. No, very briefly. I mean, of course, you know that I really love Muse as much as I love the compass muon scattering, because it's really the right thing to do. And in my talk, I briefly glanced over the discussions about the two-photon exchange effects. So if you say you have a factor of 2 more data and factor of 2 better sensitivity than the Olympus results from the two-photon exchange, can you quantify this a bit? What does this mean for the polarizability contribution for in our case? I don't know if that's fair question to ask.
We haven't gone that far, Randolph. The issue I would point out that concerns me, and I don't know if anyone's done this analysis, is that when you look at the theory calculations here, let's see, the calculations, I was just told my internet connection is unstable. The two curves, the red and the green curve that look most like the data, are based on fits to the data. The usual estimates of polarizability are based on theory, and the two theory calculations are the blue solid and blue dashed curve here, which don't look quite like the data. So, you know, it would be interesting if, I guess, if someone took the two sets of curves and did the polarizability calculation with them. And as far as we haven't done that, and I don't know if anyone has done that. I think at least one set of curves, as you can see, one set of the curves is done by Jan and the other by Tomaluk, and that's a good little study to do if Jan has any time available, for example. I will ask him if he's gone through the analysis, but I don't think he has.
Good luck for your data taking, and that COVID stops soon.
Thanks.
Forward.
I think we all feel the same way.
Yeah, Jan, go ahead now.
Just a short question. You had on your slides this inverse pion electron production. This I didn't get which background that is. Is that pion electron scattering in inverse kinematics?
This is a suggestion from Christian Weiss, actually, and he could talk more about it, that we, now I've missed the slide, that we do pi minus p goes to e plus e minus n. And if Christian is still here, maybe he wants to comment on it. What I've generally said for many of these things is the way we trigger it will be in our data set if it's in our acceptance. And then there's a question about what the cross sections are. You know, we trigger off a scattered particle and a beam particle.
So it's E plus E minus production.
Yeah.
Okay.
But I don't yet, I think what let's see, I don't know, we asked the person in our collaboration who talked with Christian about this, we said, talk to Christian about a calculation for whether the E plus E minus are on both sides of the beam or on opposite sides of the beam, both on the same or opposite sides. And then we can figure out whether it's in our acceptance or not.
And this would be only for the pi minus beam, probably.
Well, I think Christian's suggestion was particularly for pi minus p goes to e plus e minus n. Yeah.
Mm.
Christian,
Okay.
do you have a comment? You're here.
Christian wanted. Yeah.
Ron, I think you really said it all. This was just a suggestion that came up at the APS meeting 3 weeks ago. This would be basically the time reversed process of charged pion electroproduction. and that you say, for example, you do say pi minus proton going to an E plus E minus pair plus neutron, and the question came up both because I mean this process is it will take place at mu, so it might be a background or some kind of like whatever misidentification, and also I mean as you all know, particularly the people around mines, there has been a very considerable interest in pion electroproduction as a test of chiral perturbation theory, pion photoproduction and electroproduction, and this would be a chance to measure the same process in the time reversed channel. So it could provide additional information, much like we do, for example, in Compton scattering, where we have virtual Compton scattering on one side, and we have dilepton production from a real photon on the other side. But
yeah, thank you. I'm sorry, we have to continue.
Yeah.
Thanks again, Ronald, for the very interesting talk. And Eshel, are you ready to share?
Unshare window. Okay. Now let me try to share. So I usually do this really very elementary way, but now I don't see opening this.
Ashot, you have in the middle of the...
Do you see any screen of mine?
No.
No.
In the middle of your application, of your Zoom application, you have the share button. Then you have to choose the screen and then push share again.
Well, I am saying share screen, and which is interesting. Come Microsoft PowerPoint, yes. Okay, and then share again. Huh? Do you see anything? No.
No.
So Ashot.
Now yes.
Now?
Now yes.
Yes,
Okay.
perfect.
Yes, here it is.
All right.
Here it is.
Well, finally. So let me go to slideshow.
Yeah.
Okay. Better? Now it's
yes,
better, right?
That's perfect.
Okay, sorry about that. Looks like some Mark-related thing. But we always use this one for teaching and no problem. Okay, I'm going to talk about our PIRAT experiment and the results done at the Jefferson Laboratory. And for sure, this is on behalf of PIRAT collaboration all. And I want to thank organizers first for your interest to our experiment and for this talk. Now, given to current mood of audience, I think that you all expect from us to have a discussion of what we did differently for this new experiment, how we performed that differently, basically, and analyzed differently to get something basically different result. And that will be my major focus for this talk. And for sure, I will spend some quick few slides for the new upcoming experiment and how we prepare that. Well, without going too much on this, we've been doing many talks. So it's a reminder that proton radius is an interesting subject, which is connecting all three modern physics parts. That's atomic physics, nuclear physics, and particle physics in some part, right? Two types of measurement, and both are including a muon and electron. One is a bound state, atomic physics, and another one is a scattering, like a PIRAT recently and upcoming news. And I will spend more time on a little bit warming up here how we do that. In electron-proton scattering experiment, we do basically very simple scattering experiment. We send an electron with a very, very small angle to scatter from proton, all right? And that process has to be elastic. And when we measure cross-section, that can be described theoretically as a point-like cross-section that we know, and then 2 form factors, electric and magnetic, responsible for charge and magnetization of current. Now, everything is known except for these 2 form factors, and for sure, electric one depend from charge characteristics of proton, and magnetic one is magnetization. Now, there are several ways to separate these 2 unknown structural functions, GE and GM. Happily for us, in this type of experiments, we are going to work in extremely low Q-square, as small as possible, to touch proton very gently. And that's the whole idea. In that case, as you see formula itself, that factor of tau will suppress the magnetic part, and we were left mostly only electric form factor part. And that's actually we do in our experiment, not ignoring magnetic form factor, but at some higher Q-square few bins, we also include them from the other experiments or average of experiments, and that's tiny small 0.6% for last bin even contribution. So basically we can say that magnetic one will not play any role, and then next thing is that we can expand electric one with a small Q-square parameter, and the bottom one is a current correct, relativistically correct description, definition of a radius, which we are after, and that's a slope or derivative of electric form factor at a Q-square 0 point. And I want to go ahead and just make a bold statement. With this definition, that's not measurable thing. So we are trying to come up with something which is not measurable. We never can go Q-square 0. But what we do is, and what is coming out of this definition is that we have to go first thing, as small as possible to Q-square, right? That's first thing which is coming out from this logic. Next thing, since derivative depends not only from point, but it depends from a range, then we have to include also some reasonable Q-square range also. So these 2 things are basic for this physics of proton radius measurement. We have to have enough Q-square range, and we have to go as small as possible Q-square. Arguably, going small Q-squares coming with many, many problems, but in today's experimental physics, everything is problem. Now, before I go to our experiment, only flashing, which was flashed several times today, is a status of proton radius when we just start thinking about new experiment, right? This 2010, 13, and we already started our experiment 12, and that's discrepancy of muonic from other, and most importantly, when we did our experiment, 2016, 2, 3 new experiment came up. Actually 2, I'm sorry, I will show that. The one which was Garchik regular hydrogen experiment, smaller, showing smaller radius, agreeing with muonic. Another one came from Paris, 2018. No, actually, yes, but before our publication, I say. Paris result, which pushed back to right side again, but today's Randolph talk looks like changing this situation, and I will refer to his talk about a few minutes ago. Looks like it's going back. During our preparation for publication, we've been already submitted for publication, and then in last September, the York University result from Canada came up in a science journal, which shows that really looks like at least two hydrogen spectroscopy experiment agrees with a smaller radius. But by that time, the expected only new electron-proton scattering experiment was PIRAD, and it came actually exactly 1 year ago in Nature journal. So that was status when we published and when we started. Now I want to focus, as I said, what we did differently for this physics. In order to do something new, something differently, critical measurement, which will address some problem, and as we agree, proton radius in 2010-13 was a problem, which we call that puzzle to be safer, right? One has to come up a new experiment which has to be different from all other experiments done before. And we exactly look at problem like that one, that way. And first thing which we analyze that what's the weakness of magnetic spectrometer method? And as we know, all, if not most of them, proton radius measurements done, scattering measurements done with magnetic spectrometer methods. And right away, I can mention that the worst weakness is that in order to cover relatively large Q-square range necessary for fitting procedure, as we discussed, they need to change setting of angle and scattering momentum of magnetic spectrometer, and as well as initial beam energy. So these are change of several three parameters in phase space, and each change actually bringing itself new uncertain thing. For example, changing magnetic spectrometer to another angle, right away changing your target size, okay, effective size. So acceptance is different, slightly different, but it's different, right? One has to come up with a new calculation, and that's what happened with a recent MINDS experiment, state-of-art experiment done in 2010, as we always talking, which came with a larger radius, as we always refer to that. And that has today was already announced that it has about 14 different settings, 1400 different settings. And magnetic moment, also moment changing of acceptance is also bringing some uncertainty with it. And in general, this method has a 2 to 3% total uncertainty as an absolute cross section. Now, next thing is that it also has a limitation for a minimum angle. And that's a limit is in our range is 10 to minus 3 GeV over C square, right, for Q square. With that said, we also noticed that before I go to say what we did is that typical experiment did also with hydrogen, liquid hydrogen targets, most of them, and they always had a so-called background, beam background from windows. It's measurable, but since it's a larger, then it's one of a larger contribution in that budget of final errors. Now, as you see, I'm titling that a possible solution from this situation, and we call that the Pirat approach at Jefferson Laboratory. We tried to change completely that method. We said, well, if that's our weaknesses of method, then we come out with a new detection technique, and that could be large acceptance detector like calorimeter on front of beam. So that time we had a HiCal used in Primex experiments, right, which is high resolution and high acceptance hybrid calorimeter. And we decided to use that on just inside of beamline, and I will show that one. So this right away brings several advantages. Number one, access to smaller angles, scattering angles. And we will talk about that, why this probably is better, right? And also, it gave an azimuthal symmetry in experiment, which right away allowed us to measure some QED process like Mueller scattering the same time as our electron-proton scattering in the same real time and in the same acceptance, kinematical acceptance of experiment. This was a secondary but a big advantage for our experiments to control systematic errors. Now, next thing which we improved actually was changing that classical liquid or gas hydrogen detectors with windows and use for first time in these scattering experiments or fixed target experiments a windowless gas flow hydrogen target. That minimized a background, beam-related background. And with that, we went to our experiment as using 1 GeV, 2 GeV, 2 sets, mostly to check consistency of our experimental data set. A little bit timeline. As I said, we started already 2012 was approved our proposal. We start developing our experimental setup, mostly tracking part was new on target. In 2016, during 3 months at Jefferson Lab, we did this experiment. It was published exactly 1 year ago in Nature Journal, and most of you know. It was done in Jefferson Laboratory, as you see, at hole B, that you see that arrow, that smallest hole, and I'm going to show a little bit pictures about that. So major parts of this experiment are showing here schematically, three-dimensional 2D picture. And I want to agree with you that this is probably most simplest experimental setup for such an experiment, right? It has major two things, a target here, right? A scattering chamber long, about 5 meters long. And then we have a calorimeter on beam line, which on front of that has a position sensitive gem detector, right? One plane for now. And this is basically all for this experiment. We have some beamline elements, so we have a beam hollow blocker just before target to make sure that we don't have too much events from electrons coming with beam in radially different distances. And basically that was all. So I will go to, again, save my time and just go a little bit each element. The major part of this development was a so-called windowless hydrogen gas target, which I will go ahead and say it performed perfectly during experiment, very stable way, very reliable, and we've been happy with this development done by Jefferson Lab Target Group, mostly, and with our collaboration also. So very conceptual is very simple. Cryogenically cooled hydrogen at 20-25 Kelvin goes down through a pipe in a target cell, which is 8 centimeter diameter and 4 centimeter long. And it has a Kapton windows around on the way of a beam line, but 2 millimeter punch holes are on that Kapton for electron beam in and out. And through them, gas going outside, and through 4 high capacity pumps, we are pumping out the residual gas out of target. So there are some number ratio of pressure inside of cell. It was about 500 millitorr, and outside was a point, inside of chamber was 2 millitorr. So that ratio was good enough for us. And also there was some very small pressure on beam line and down to scattering chamber. So that was our target. And this is a picture installed in a hole B just before the experiment. Beam goes from left to down. And you can see scattering chamber and down the calorimeter, but I will show a little bit. This is scattering chamber, simple thing, but it has a engineeringly very challenging because it's long and wide. So I will focus on that a little bit. It's ending with about 2 meter diameter opening vacuum window, and beam line is attached to that aluminum vacuum 2 millimeter vacuum window. This was a challenging thing, but it worked nicely. So beam goes through vacuum all the way through our detection system and down to calorimeter also inside of vacuum. That's important engineering challenging task, was performed very nicely and it worked reliably. A major important thing in our experimental setup was tracking, not tracking that. So let's say position sensitive detector, which was a gem consisting of two parts of large gems. And our specialist UVA people said that this is the largest gem at that time, 2016. And it has about 72 micrometer position sensitivity and about 95% detection efficiency, which we measured together with HiCal combination. This played two roles. Number one, it's improved Q-square resolution about 20 times, which is critical for this physics at cross-section at smaller angles, very stiff cross-section. And also it improved second thing, which is a weakness of any segmented calorimeter. It has an ambiguity of coordinate resolution, other than resolution is not that perfect. So two function for GEM. The major detector is a hybrid calorimeter. We call it HiCal. An important thing is that beam, this 1 GeV, 2 GeV high intensity beam, relatively high, goes through the middle of this calorimeter, which has a 2x2 crystal removed. And that was interesting challenge for experiment to pass through that small area of high energy intensive electron beam and measure absolute cross sections. So only a few words about this one. It has a inner part of lead tungsten, out part is a lead glass detectors, and it was 20 years old. It was designed for Pi0 lifetime measurement, and this design came as a compromise between performance and price that time. Crystal part has a good resolution, and lead glass is not. A few words about analysis, right? We had a 1 GeV data and 2 GeV. Each one is together was 1.5 billion events, right? And if you look at this data set, first idea is that it's very simple to come up with cross section. You take what particular theta beam or Q-square beam, calculate the EP events, which is easier. Then you divide by all known parameters, you have that. But we have two problems here. Number one, stiffness of cross-section, very stiff. Therefore, the center of beam is a question, right? And second one is radiative corrections. As you see, we solved that problem, but we used also normalizing to Mueller events, which is basically here, this is asymmetrical Mueller, inner ring or theta angle, and the next is outer ring Mueller. Mueller was better measured in this experiment for sure. And with all these things come together, I will conclude few words that how we measured the cross section. Basically, we used iterative method, as we talked a little bit earlier, and we normalized the EP cross section to EE's cross sections with about 4 or 5 iterations. We went to plateau of that. I want to emphasize one minute about two important systematic errors. Systematic errors coming from beamline, still we have for sure, and our target was designed in up to perfect way to have about 5 different position or situation to measure background in beam. We did that and we subtracted beam. For example, here at 2 GeV, the very, very forward angles, we have about 10% background from beam, but we, with measuring, as you see bottom, this green points, it goes down to 1% or less. For Mueller, basically that background is limited to 0 because Mueller has a 2-arm and kinematically very well defined. Second part, which I want to emphasize in our case, was a so-called EP inelastic contribution. And this is where we pay price going from magnetic spectrometer to calorimeter, which has a much less energy resolution. In magnetic spectrometer, this part is perfect. But here we have to deal with trying to subtract some small contribution of EP inelastic. And we did that. You see that with lead glass part contribution in this blue line, basically it's come to 0. But for lead glass area, which is unfortunately high Q-square range, we still have some background, and that comes down to some part of percent uncertainty. So those two things, and we came up with cross sections. These were 1 GeV and 2 GeV on the right, as you see. Once you have cross section, then you can extract the electric form factor. It's here for 2 GeV and overlapping area, as you see. There is some normalization constant, which is very, very close to 1, as you see that. I will leave that question for questions if you have. And then next thing is a fitting the form factor. We did previously some investigation of good fitters, and we found that rational 1,1 is the best fitter for us. And as you see from that fit in this blue line and the blue points through that one, one is a linear way, another one logarithmic, as you see. And outcoming radius was found 0.831 with about 1.67% total uncertainty. Here's our point. Here's our point there, right? And as you see, it's sporting smaller radius, but it has a little bit larger uncertainty. But one thing I want to emphasize here that, however, it's comparable with regular hydrogen uncertainties, which was expected to be much, much better, all right? And one more thing, observation here, it is about 3 sigma lower than EP recent results, 3 sigma only. So for that reason, we want to have another experiment, and we want to squeeze out most of this technique to perform another PIRAD-2 experiment. And this experiment was approved several months ago in August in PAC 48, Jefferson Lab. We are preparing this experiment. Idea is to reach to about 4 times better total uncertainty. That will be dramatic result if we reach, basically. And that comes from a significantly better statistics. If you see that our statistical error is still half of our total error, and also hardware upgrade. Most of it adding another tracking detector to have another position detector to have good tracking for events. That will change a lot. And we also think about to upgrade calorimeter to all crystals. That will help our systematic errors for inelastic contribution. And we hope to have a best resolution for EP scattering. And also one thing which coming out here is that it will also allow us to go 10 to minus 5 Q-square range for the first time for EP scattering experiments. Where that point will be is projected value only. So we put it here, but most important thing is its error bar. If we reach to this, then we will actually challenge, depending where it's end up, challenge all regular hydrogen experiments, and probably it will come to contribute to averaging process other than muonic experiment, which will dominate for next probably 20, 30 years for that. That brings me to basically end. This is our part of collaboration. Real collaboration is about 2-3 times larger, this picture. In summary, I want to emphasize only one thing, that this experiment was kind of uniquely designed to address exactly proton radius problem measurement, another one measurement. And with that, performed that, and we hope that it is done in accurate way. It's also helped to come up with a new co-data recommendations by our preliminary results and maybe another talks. Next experiment, we want to have about 4 times better total uncertainty and reach to new Q square 10 to minus 5 range. Thank you very much. And
thank you, Eshat.
I will answer some questions.
Do we have any question? Please use the raise hand button. Randolph.
Yeah, of course, you would. Of course, Eshat, this is a wonderful experiment, and I'm really amazed about your results. And of course, the question is always about the future, right? And pre-RAD2 is a wonderful thing, because as you see, as I showed, the error bars in hydrogen are also decreasing, and we are thinking of improving the muonic proton radius. So maybe at the next level of accuracy, there is a question for discrepancy or finding interesting new things. Now, I was wondering what happened to DRAD. That's not a fair question, right? Because you're talking about PRAD2, but would it be possible to measure the deuteron and helium-4?
It's a good question. And it's hitting to our pain. We submitted updated, upgraded proposal for DRAD2 parallel to this PRAD2 in August, but PAC somehow didn't find that we are ready to do DRAD experiment at Jefferson Lab. And major concern, as much as I understood, was that radiative corrections are not understood on a level significant enough for that precision, for DRAD, for deuteron case. We agree on that is case, but experiment requires several years to prep and do, and during that time, most likely some new progress will come for the radiative corrections, and we could have that better. So mine's group trying to finish their measurement for deuteron. Maybe after that, we try to think about again. But I understand your question. With the same technique, deuteron will be much, much better measured, same way as a proton. It's a technique used, and we try to use that.
I mean, if I may add on this, because I think, we are past this point where we have to argue who's right or who's wrong, right? I mean, now we want to learn something from putting all data together. So maybe if you could consider measuring, these light nuclei, these gaseous targets like deuterium and helium, and then doing a combined analysis using the muonic results. Maybe we can learn from each other and can improve our polarizability panes by getting better results from elastic and also inelastic electron scattering. And you can learn something about the radiative corrections by plugging into the analysis, the results for the radius from the muons, right? So maybe putting it all together, we learn most about this physics.
Myself and our collaboration agrees on that point, but there is one difference here, and we have to always take into account realistic difference. Electron-proton scattering experiments are much, much difficult, involves money, involves time, involves commitment from laboratories, and it takes longer time. I don't want to hurt atomic physics experiment, but it's kind of industrial thing, and so we have to live with that. But again, we will come again, try to see after PRAD2 if we can push deuterons.
Okay, last question by Jan Bernauer, please.
Yeah, I actually want to comment on that. So first, I'm sorry I couldn't hear your whole talk. I'm actually organizing a different workshop at the same time, so I have to come in and out. But actually, on that, have you thought about? I think it was a big mistake of the PAC not to give you the time for that. But have you thought about just packing it up and shipping it to a different accelerator when you're done with PRAD2 to do DRAD?
We haven't thought about that, and one of our spokespersons looks like he also, Hayan can comment also, but we want to see first PRAD2 done. Really, we think that will be the most updated measurement of proton radius. For now, that will take probably 3 years plus minus, right? With all based on we feel that Jefferson Lab on our side, they are also interested. That's good. That it will most likely provide our success. Then after that, we will see. But for now, I will say, well, whoever is interested in this physics, we are more than welcome to join us. And then after that, we see where to ship, how to ship it.
Thank you.
Ian, if it's just 2 seconds to finish the comment, otherwise, I'm sorry.
I just want to add a comment to what Randolph was asking, and also Christian.
Okay, very short. Very short. Just a comment, please.
So in the Dupont case, in addition to the radial correction, there is also, if you remember, the current saturation in terms of the overall experimental uncertainty from the ED measurement as well as proposed DRAD. And we want to improve that by a factor of 2. So I think that the kind of margin for success, I think some people are a little bit worried. You know, they like to see even better measurement, but it's very difficult. So I just want to add this comment.
Thanks a lot.
Maybe that last word on that is that in case of Deuteron, we are introducing recoil detector, which makes additional uncertainty. That's the difficulty of that experiment.
Yeah. I agree, which is the concluding word. Thanks again for the very nice talk, Eshart. I would like to thank all the speakers of this last session. I apologize for cutting short the question sessions. I know it's a lot of frustration, but we are already behind the schedule. And I would like to give the word back to Anna.
Okay, thank you. I cannot share the screen. Ashot, can you share?
Yeah, I have to, yes, stop, sorry. I did already.
Ashot, if you can send us the slides.
Yesterday evening, I sent it. Did you get that?
Okay, I will check.
It's very, I could not find how to upload, so I send it. If not, let me know, I will send it.
Okay, I hope you can see the slides and also hear me. So we are discussing the remarks of this 17th International Workshop on Hadron Structure and Spectroscopy. And at the end of this new experience for us, on behalf of the local organizing committee, I would like just to thank those who contributed to the success of this workshop, starting from our sponsors, INFN for the financial support, EXAC, the European Center for Science, Art and Culture for the organization, but also the Trieste Physics Consortium, of 2020, and the Compass collaboration. Of course, we had a lot of help from our secretariat, in particular Serena Baldini, Anna Paola Cuccarollo, and Nadia D'Antoni, who did not join this meeting, but we want to thank them very much. And also the Servizi Teatrali for the excellent meeting and connections. We have not seen them in during the workshop, but they did really a very good job. Of course, we have to thank the International Advisory Committee for the essential help in building the scientific program, which I think was quite complete and relevant. Nico Bettoni and Stefano Fantoni, who gave us the very warm welcome at the beginning of the workshop. And finally, we want to thank all speakers and participants for the very enthusiasm for the high-level presentations with very nice review and new ideas and results, and for the very interesting discussion. We have a lot of material to think about, to look back again, and thank you very much. And of course, we hope to host all of you soon in Trieste. Thank you.
Thanks a lot.
So bye-bye to everybody.
Thanks a lot and bye-bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Goodbye.
Bye.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye-bye.
Bye-bye. Bye-bye. Die meisten sind hoch, ja.